Okay, I think it's time to start. I hope you can see me and hear me well. Welcome to the fourth edition of the real-world PIM tutorial. That's a real-world processing in memory systems for modern workloads. This is, as I said, the fourth edition. We are doing it with the micro conference that is happening in Toronto these days. But before this, we had the first edition at HPCA in Montreal, second one, ASPLOS in Vancouver, and the third one was in ISCA in Orlando. I have just a couple of slides in order to welcome you all and introduce the tutorial. And after that, we will start with the first talk that is going to be delivered this time by Geraldo Francisco de Oliveira, a PhD student of the Safari Research Group. He's going to give a whole overview about memory-centric computing systems, about the different trends on processing near memory and processing using memory, and a little bit of his research work as well. Just to give you a little bit of motivation for this tutorial, even though I think that this is already well known by many people, but probably all of you, data movement in computing systems is dominating performance and the energy consumption. Here, for some examples, you have some numbers about the total system energy. Data movement accounts for 62% in consumer applications, 40% in scientific applications, or 35% in mobile applications. And this happens because between all the different components that we can find in a computing system, there is a lot of data movement. So we believe that compute systems should become more data-centric, more memory-centric, and processing in memory is a way of doing so. Is a way of alleviating the data movement by computing where it makes sense or where the data resides. This real PIM tutorial has been prepared after several editions of our processing in memory course at ETH Zurich. Here on the screen, you can see now some links to the last edition that we had in spring 2023. As you can see, there is a website with all the materials and also a playlist with all the different lectures that we had in the course. Same as in the PIM course, in this tutorial, we are live streaming the tutorial, so all talks are going to be publicly available in YouTube, and all the materials are available or will be available, and most of them are actually already available in the website of the tutorial. So you can check the slides in advance, or you can even start the hands-on lab, the optional hands-on lab that we have at the end of the tutorial. And for your reference as well, I have here a couple of slides about the prior PIM tutorials. This one corresponds to HPCA 2023. As I said, we also had it in ASPLOS 2023, and the third one was in ISCA 2023. Over these 3 tutorials, we've had multiple interesting talks from invited speakers from Samsung, from SK Hynix, from Alibaba, also from academia, and in different places, people working with real PIM systems. So highly recommended to check the prior editions of this tutorial. And here in this screen, you can find a link to the current PIM tutorial in micro, and also the live stream where you're probably checking or watching right now. This is the agenda for today. You can also find it in the updated one is in the website. We are starting with this welcoming and the agenda, and as I said, after that we are going to have a lecture about memory-centric computing systems that is going to be delivered by Geraldo Francisco de Oliveira. He's going to introduce processing in memory systems, processing near memory, processing using memory, and after that, at 9:20, I will talk about real processing near memory systems. We will have an emphasis on the AxDIMM PIM architecture, a little bit of architecture characterization and programming, and after that, a short coffee break. After the coffee break, we have two exciting invited lectures by Professor Jong-Sok Kim from the Yonsei University. Is an implementation of the joint algorithm for the AxDIMM PIM architecture. I think is extremely interesting work that really get the most of the AxDIMM PIM system, which is the first real-world processing memory system. And after that, Dr. Abu Sebastian will talk about their research at IBM Zurich on PUM based on memristive devices. They have been doing a lot of amazing work for several years already. And then we'll have a lunch break, 1 hour. After the lunch break, we will continue with several interesting talks about processing using DRAM. We will talk as well about accelerating modern workloads on general purpose processing in memory systems. Here I'm going to summarize several of our recent works on machine learning, genomics, homomorphic encryption, and transcendental functions. And after that, we will continue with the different issues that need to be solved to enable the adoption of processing in memory, and a talk about a new work of us. There's SimplePIM as a software framework for high-level PIM programming. I think this is the first high-level programming framework for real PIM systems. That's really interesting and exciting work that we have just presented at PACT conference last week. After that, we will have Ataberk Olgun, is another PhD student of the Safari Research Group. He's going to talk about the processing using memory prototype called PiDRAM, which is probably the closest thing to a real-world system with processing using memory or processing using DRAM capabilities. And we will finish the tutorial with just a short introduction to the optional hands-on lab that is already available in the website. From the website, you can see, as you can see, you can access. You can already access the handout, and with the information in that handout, access a real AxDIMM system, a real AxDIMM server that we have access to today, thanks to AxDIMM folks who have prepared this for us. And it's going to be available for a few hours, still a few hours, about 20 or 22 hours from now. So you are all welcome to try and experiment with the real AxDIMM system. Okay, in this presentation, you also have the abstract and bio and the title, of course, of the invited talks, joint algorithm for commodity PIM DIMMs by Professor Jong-Sok Kim. I will introduce him properly before he starts his talk, and same for Dr. Sebastian's talk about PUM based on memristive devices. So this is all for now. I'm going to offer the stage to Geraldo if he wants to start his talk. Geraldo, feel free to go ahead and share your slides if you're ready to start.
Thanks, Juan. Just a second. Let me share the slides over here. Okay. So hopefully you can see the presentation.
Yes, I can see it.
And you can hear me well. Okay, everyone. Thank you so much for the introduction, Juan. Thanks everyone for joining our real-world PIM tutorial here at Micro. And today I'm going to give a brief overview about memory-centric computing systems. So I'm Geraldo. I'm a senior PhD student at the Safari Research Group. I've been working on processing memories since 2016. And so I'm really excited about this topic, and I'm really excited about sharing a lot of our research that we've been doing in Safari and other places as well with you guys. So without further ado, let's get started. So as probably everyone here knows, computing is mostly bottlenecked by data in today's systems. This happens for many different applications, and And this is happening, this is becoming worse over time. And this is particularly important for key applications like AI, machine learning, genomics, because those applications are fundamentally data intensive, and also the volume of data that they are processing to do meaningful computation is increasing over and over in time. So here I have an example, example of these particular applications. Here we have the machine learning, in particular transformers for large language models, which are gaining a lot of popularity since the attention is all you need paper. And in this presentation here, you can see on this slide here, you can see that the initial BERT large language model that Google has released in 2018 had around 1 gigabyte of memory required for the model, and now in GPT-3, the size of the model increased to up to 10,000 gigabytes. So it's more than 18,000 more compute, and also more than 4 orders of magnitude larger memory footprint required for that particular application in a short span of only 2 years. So, and the projection is increasing over time. Facebook has released the Lambda 2 large language model, and that language model is even larger than GPT-3. So this is just to say that applications are becoming more and more and more data-centric or memory-centric over time. And this is happening not only for large language model and machine learning workloads, that are several other applications like databases, graph processing, memory analytics, and data centers, where data is one of the main components of processing data, is one of the main components of the application. And that processing of the data leads to performance and energy bottlenecks in today's systems. So it's not only for the cloud, there is also edge applications that runs on your phone, for example, like Chrome or TensorFlow or YouTube or Hangouts, that requires a lot of data processing, and again leads to performance and energy bottlenecks in edge devices. Data itself is really important to unleash potential of applications in future workloads. So here I have an example of bioinformatics workloads where genomic analysis or genomic processing the genome information requires more and more data over time. And genomic analysis is particular key and we saw that happening in the pandemic time, for example, where doing the genomic sequencing of the virus itself led rapidly to the development of vaccines, and in the end of the season of the pandemic time. And that processing of data was key, and the speed that you could process the data was key for that development. And that we are going to see, you keep seeing that in other scenarios where, like for drug development or treatment of important disease. And again, for these key applications that have real world impacts really quickly, data is the main bottleneck and for the system. So why this happens, why data overwhelms modern systems? This happens because of the way that the system is split between storage, communication, and computation. We're going to talk a little bit more about this later. And this impacts the robustness, the energy, and the performance, and the cost that you can get from the system. So the way that we are designing systems today, the so-called von Neumann architecture, divides the system, as I said, in 3 main components: the computation, the communication, and the memory system. And data needs to move back and forth between those components, from storage to the using the communication to the computing system. And this model has been proposed many years ago from the 40s, and it has proven to be a successful model for many years, but is the key problem where we are seeing right now, this need of moving the data across all of these 3 components. So here is the example of what that particular model have created over time. So here is a picture of a multi-core processor with a deep cache hierarchy, and you can see that the majority of the system here in green is dedicated to either storing data or to moving data. The parts that are required for do actual computation It's just a small part of the core itself. Yet the system is bottlenecked by the memory bottleneck. So if you look at the the modern core, so that the picture that I just showed was from a old multi-core processor, but we can see over time that one way that memory manufacturers have tried to solve this memory bottleneck problem over time, while keeping this mononormal architecture, was to increase the cache hierarchy, or the depth and the size of the cache hierarchy, so that hopefully applications could the system could exploit the locality that applications possess, and then reduce the data movement traffic required in the system. So here, for example, I have AMD processor from 2020, which already have a quite large L3 cache, less level cache in the system of 32 megabytes. And processor manufacturers keep increasing this size of the cache. So in 2021, AMD released another processor where the less level cache went for 32 megabytes to 96 megabytes, and this trend continues. So this is another die from IBM that shows 120 megabytes less level cache. And again, this is a Apple One M1 chip, where you can see the majority of the chip is consumed from DRAM and storage. DRAM and SRAM for cache, sorry, and also storage. But this is still is not a good solution, or is a solution that has been proved to have reached a ceiling to today's systems. So studies that we have done in the past have shown that even though systems have increasingly been more complex, or increasingly having a larger and larger cache hierarchy, we still suffer from data movement bottlenecks, both in terms of performance and energy. So this paper that we did together with Google, we saw that 62% of the total system energy in modern consumer devices is dedicated only to data movement. And if you look at accelerators, the problem is even worse. So in ML accelerators, machine learning accelerators, also from Google, we observed that 90% of the total system energy, again, is spent of data movement for various reasons. Well, one reason is because the application itself are becoming more data-centric, and also predicting the memory behavior of applications is becoming harder and harder. So the problem that we have here is that data access, again, is a major performance and energy bottleneck. And the way that we are designing systems is the cause of that data movement bottleneck problem, which leads to significant drops in energy and performance in today's systems, and in general purpose systems and accelerators. The main problem here is that we are processing data far away from where the data actually is placed, because of that von Neumann paradigm that I just mentioned before. And this is not a new observation on a new problem. In the 90s, that was already foreseen to this memory bottleneck problem has already been foreseen to be a problem in modern systems. So in this seminar paper from research sites, it's called "Is the Memory Stupid?" It's already foreseen that the memory subsystem is going to be the most important component in the design of microprocessor, because of the difference of scaling of the core speed and the scaling of the memory subsystem back then. So that was already projected to this memory bottleneck problem was already projected to be a problem, and now you are in this problem and or facing that problem right now. Again, this is some experiments that was in Professor Onur Mutlu's thesis from 2003, where he collected some. He profiles several applications that were important from Intel at the time, or Intel microprocessors. And back then, he already saw that around 50% of the total execution time for those important applications was dedicated to moving data. So this is that was already a problem back then. So it's just becoming further and further a problem. And even though there are solutions for that, for example, the run-ahead execution paper that tries to mitigate that data movement bottleneck, in today's systems, that problem is still persists. So this is another paper from years later in 2015 from Google, where Google did some profiling of their key server-based applications and to understand where the bottlenecks were. And Google observed again that the majority of the bottlenecks faced for those really important server-based applications are due to the memory traffic. Particular here, like around 50% of the cycles were spent on cache stall for this particular workloads. So why this is happening? This is happening because we are designing really grossly imbalanced systems today. So processing is only done in a single place in the entire SoC. So processing is only performed on the cores. And if your data is far away from the core itself, because you need to think about the physics, the core the processor is becoming smaller and smaller, and you integrate more processors, and your memory is becoming farther and farther away as long as the die size of the processor increases or the SoC increases. So that requires a lot of data movement in that system, which creates energy efficiency, complexity, and everything results in lower performance. And this is also true for accelerators. We are designing systems that instead of fundamentally mitigating the data movement bottleneck in processor-centric systems, we are trying to tolerate data movement bottlenecks, which have in the past was a good approach, but nowadays have been proven to be a limiting solution. So in terms of energy, I talk a lot about performance so far, but if you think about the energy aspect of data movement bottleneck, everything becomes even worse, because even though for performance you can try to hide the latency of data movement, you cannot hide energy. Energy is a cumulative metric. So when you look at the energy that it takes to actually move data around, the energy that it takes to move some piece of data from outside of the core to inside of the core is around 100 times that of, or 1,000 times the energy to do a simple float point or deep precision arithmetic operation inside the core itself. So here I have another way of looking at the same information. So on the x-axis you have the energy of moving the data across the memory hierarchy, and also doing some computations normalized to the energy of doing a 32 operation. And as you can see here, in this with this other data, we can see that a memory access consumes 6,400 times the energy of doing integer addition operation. So energy is a key problem to the data movement bottleneck exacerbates the energy problem in today's systems. So to solve all of those issues, what we need is to think differently. So we cannot just try to hide the latency or to hide the energy of data movement, because that fundamentally does not solve the problem. So we need a paradigm shift which enable computation with minimal data movement. And that means that we actually need to do the computation where the data sits. So we need to do the computation where the data originally resides, or doing minimal amount of movement and place the data where it would make more sense. And this would require, instead of thinking in processor-centric architecture, to think about a data-centric architecture design. And our axiom to do that is that intelligent architectures that would be high performance and high energy efficient, are those architectures that handles data well. So that does the bare minimum data movement and process the data where the data sits. So how can you do that? So first, we need to ensure that the data does not overwhelm the other components of the system, so does not overwhelm computation and does not overwhelm communication in the systems. And we can do this with several different approaches. One approach is using intelligent algorithms. The other one will be using intelligent architectures, and of course with a system view, where we co-design algorithms and architectures together to minimize the data movement traffic. Another approach is to take advantage of large amounts of data and metadata that we have in the systems to improve the decisions that need to be taken to place data or to move data around. So right now in today's systems, a lot of the decisions of the algorithms that are placed in the cores for various reasons, for example, prefetching or branch information, or how you place data across the memory hierarchy, are based on ad hoc decisions that were done via profiling or benchmarking. But we can be smarter and actually try to understand better the data that we are have been processed in the core, and based on that understanding, design the algorithms and components that are going to make decisions inside the system itself. And that again leads to a better understanding of exploitation of the different types of data that you have in the system. So not all data is equal data in the system, even though in terms of representation, in the end we have bits and bits being stored as charge or as voltage level or as current, but in the end that bit has a semantic information that if you understand that semantic information, we can improve the system by improving algorithms and architectures around that information. So computer systems today, they are mostly processor centric. So all of the computation is done, everything in the core is there to support the processor itself. But we don't necessarily want that. We want a more data-centric view of the processor so that we can mitigate the performance and energy bottlenecks of this data movement in the system. So the decisions that are making the design of the system or by the system components themselves are design and dictated decisions. So again, there are ad hoc decisions that are placed in the system based on some previous benchmarking of important workloads, and not always leads to the best performance for newer application in particular. So we need to think more about data-driven decisions so that we can design better systems. And also components are quite myopic, so they only look at a specific component during a given time. A component only looks at itself over a given time to make a decision. But would be better to be more conscious of the data that is being processed so that the system could do more informative decisions. So basically, if you want to solve those problems and design more intelligent machines, we need to think about data-centric, data-driven, and data-aware architecture. And we have an overview paper that think about how can we fundamentally design these better intelligent architectures that I invite you to check over here. And basically, the takeaway that you get from the paper is that if you want to design those intelligent architectures, we need to rethink the entire computing stack from the algorithm to the device of the hardware device itself, going through programming language, software interface, and microarchitecture. And even though that is a laborious test, is what fundamentally would move on and remove this data movement bottleneck that you are facing today in today's system. So basically what we want to design is this data-centric architectures. So what are the properties of data-centric architecture that you want? So we want that data-centric architectures to process their data where it is. So we want also the memory arrays themselves to be as low latency, as low energy as possible. We want to move data from storage and processing with low cost. And we also want to manage data in an intelligent way. So that is robust, provide the security and reliability for a system while minimizing cost and improving performance. So let's think about the first thing on processing the data where the data resides. So processing the data where it makes sense. So again, this is the picture of a modern SoC, the Apple M1 processor from 2022. And as you can see, this picture again, the majority of the system is dedicated to either storage or to memory itself. So the question is, since that the system, the majority of SoC is dedicated to storage or memory, where does it make sense to process the data? Would it make sense to move the data to the smaller part of the chip where the cores are, or to store to do the computation inside or near those large memory structures that are placed in the SoC? So you need to think differently. Basically, what we want here is a mindset shift where we can incorporate some specialized computing capabilities nearby the memory components themselves, so we can minimize this memory traffic. And this, we can think about this as a conventional accelerator system. So we can see the memory as an accelerator device that accelerates data-intensive tests. Even though this is not a new idea, so moving computation nearby the memory arrays themselves, what is so-called processing memory, even though we are talking about this today in 2023, this approach has been proposed a long time ago in the 70s with those seminar papers called cellular logic memory arrays. And that evolved over time. There was a follow-up works that advocate for the use of computation nearby memory arrays themselves, late to the in the 90s. But we don't have those. Actually, nowadays we have those, but we are not those processing memory architectures. Even though were proposed many years ago, we still don't have them in our pockets, right? So what is happening? Why we are talking about in-memory computing today? So there are three main reasons why we are actually considering processing memory solutions today. And those involve both the device themselves, the way that we manufacture them, and the applications that are running on top of those devices, and the designer that are designing those architectures and those applications, and try to make everything efficient. So memory, the first one, the technology scaling problem, is due to how we are actually manufacturing the memory devices, right? So over time, memory devices, SRAM, SRAM devices, DRAM devices, flash devices, they are shrinking in size, so that that device becomes denser and denser, and the cost of the device decreases over time. Since the size of the device decreases so much over the years, we are now facing scalability problems that are leading to not only problems related to performance and energy, like leaking, but also as reliability issues that I'm going to talk about a little bit more later on. And many of those issues demand us to think about of intelligent device or intelligent memory systems so that we can mitigate the problem. In terms of application, I showed many examples here, right? Applications are becoming more and more data intensive and creating performance and energy bottlenecks in those systems where those applications are running. So what we want from as a designer at the same time is to design a system where we can provide high performance, energy, and sustainability, or of course, all of those three metrics together. And that is really hard to do if you don't think about mitigating the data movement traffic in those systems. So this is a nice time to think about processing memory, because processing memory have resurged because of the data movement bottlenecks that I just keep talking about in modern applications. And alongside that, because of these memory scaling problems that memory manufacturers have been facing, new memory technologies have been created to try to solve this problem. One of those technologies that enables processing memory, but not only because of those particular technologies, are the 3D stacking of memory devices. So Micro had created this consortium some years ago, where they make the case for stacking layers of 3D of DRAM memory together, using a new technology called a manufacturing technology called through silicon vias. And doing that, we can merge together memory technology together with CMOS-based technology, which is used for computation in efficient ways. And after that, many other proposals or many other memory technologies that follow a similar manufacturing approach have been proposed, like the hybrid bandwidth memory, HBM memory device that is available in many GPUs nowadays, for example. Micro have also designed this automata processor chip that is a processing memory architecture. The UPMEM architecture, which we're going to talk about a little bit later in this tutorial today, is another example of a processing memory solution using regular 2D DRAM arrays, where PIM cores are placed. And there are many other approaches: the Samsung HBM-PIM architecture, the SK Hynix, the Samsung AxDIMM architecture. Alibaba also has a process memory architecture. So there are, the landscape of process memory architectures have been increasing quite dramatically in the past 10 to 5 years. This because of both advances in manufacturing technology and the push from the application side and the system side of things. So process memory is regaining interest more and more and more nowadays. And again, I'm going to diverge really briefly here to talk about this scaling problem that memory architectures are being facing today, and how that problem not only affects performance and energy, but also affects reliability. So one of those problems that memory scaling has been facing is, in terms of reliability, is the so-called Rohammer effect, where one can predict or induce errors in DRAM chips by accessing DRAM in a particular way. So that is, again, was so-called Rohammer, and it works as follows. So this is an example of a DRAM array itself. We have rows of DRAM cells, and if you want to access a row of DRAM cells, you need to open a row. And once you are done accessing that row, you need to close that row. So if you keep doing that, if you keep accessing, opening, and closing a DRAM row, after some times, your DRAM chip is going to experience some errors in nearby DRAM locations, even though you didn't try to access those nearby DRAM locations itself. And those errors that they are there in the DRAM chips that you buy today can cause security leaks or security breaches that can be exploited to take over a system. So we did some experiments back in 2014 from three major DRAM manufacturers, and we saw that this effect was presenting all of those DRAM manufacturers or DRAM chips from those manufacturers that we observed. And again, a simple failure mechanism like this can be used and has been shown to be used to take over entire systems, which is quite problematic. So we first present this attack or this DRAM scaling vulnerability in 2014, and we continued doing research that for many years. And this problem is not being solved yet. So it's just getting worse and worse as the size of the DRAM chips decreases over time. So if you are more interested, in the secure aspects of this memory scaling problem, I invite you to check our tutorial on Rohammer and our video about the history of Rohammer and our lectures about the topic. So basically, not only because of performance and energy, but also regarding security, we need to think about better systems or better intelligent memory architectures and memory controllers. And one way to mitigate this is this block hammer approach, where we rethink the memory controller device, taking into consideration the security problem that memory scaling have caused for DRAM itself. And we are not only the only one thinking about this particular problem. Memory manufacturers also are thinking about ways of dealing with this DRAM scalability problem by designing better DRAM controllers. So this is a paper published by SK Hynix, which is one of the 3 largest memory manufacturers in the world in 2023, where they, again, redesigned the DRAM controller, taking into consideration the Rollhammer effects that DRAM chips are facing today. And this is a picture of their organization. Other memory manufacturers, this is from Samsung, the larger memory manufacturer today. Again, they are also looking at intelligent DRAM controllers to mitigate the DRAM chip itself. So you might think that over time, so the original DRAM Rollhammer paper was proposed or was presented in 2014, and research, academia, and the main memory manufacturers are showing solutions to mitigate this security problem. So that it's been many years, right? So one might think that this problem is solved, but that is not the case. Actually, we not only the Rollhammer effect is creating these security problems, but there are new effects that are being discovered. So recently, we published this paper in 2023, which is called row press, and in row press we show that there is another type of attack that one can perform, so that we can generate bit flips in DRAM rows themselves. So this is another what we call redistributed base attacks, and is different from Rollhammer, and it leads to similar security breach in today's system. So basically, this is just to show that not only Rollhammer is becoming a bigger problem as the scaling becomes is lower and lower, the RAM scaling sizes. So new problems are being figured out or being learned because of this because of this scalability that DRAM is facing over time. And this is not only so one of the solutions, for example, instead of try to just patch the problem, would be to change completely the memory system, the way that we are using the memory itself. So instead of using DRAM, we can think about other memory technologies to replace DRAM, that technology that would not face those scaling problems, as for example, phase change memory, a non-volatile memory device, but yet those emerged memory technologies face other problems that does not allow us to fully replace DRAM with them in today's system. So we still need to do research on how to fix the DRAM itself and how to improve those emerging memory technologies themselves. So this is just another example from a paper from Intel and Samsung together, where they are thinking and worry about those DRAM scalability problems that we are facing today, and is going to be worse in this system. So the main takeaway here is that we need to design intelligent memory controllers to avoid security failures and to enable better scaling of DRAM systems in the future. When you look back at the systems perspective and the application trend that we were talking about before, this scaling has a direct effect on performance, energy, and how we deal with modern applications in today's systems. So we as architects have several challenges and opportunities to improve those future systems, where we want to design a system having more than one metric in consideration. Actually, we want to design a system that is both high performance and high energy efficient, while we can provide a sustainable platform, sustainable system altogether in our design. And again, our goal over here to achieve that is to, for these data-intensive applications, do the computation where designed. So process the data inside the memory array themselves. So basically, instead of moving the data back and forth to the processor, I just want to send a query to my memory device and tell my memory, do a select of a database, or do a graph traversal of a graph. and give me the data back, the output data back, instead of moving back and forth each piece of data, so that I can process the computation in the core. So to enable that, as architects, we need to think about many questions, actually. So for example, so how much computation should we give to those memory devices themselves, and how efficient or how intelligent the controller should be, how we should communicate across the memory devices, how the software stack should look like, and how the hardware interfaces should look like, how we should program those devices, what type of compiler infrastructure do you need, and what changes in algorithms we need to do to efficiently exploit this type of architectures. So all of that, again, require a rethinking of the entire computer stack, so that we can enable those processing in memory type of architectures. And we are going to get there one step at a time. So the majority of the content that I'm going to present next about processing memory research that we have been conducting in Safari and in other research groups, you can find in this book chapter that we wrote in 2022 called A Model Primer on Processing Memory. So I invite you to give it a look if you are more interested on processing memory. So in this talk, I'm going to briefly talk about two approaches where two different approaches of doing processing memory itself. The first one called processing near memory, and the second one called processing using memory. So this is a brief taxonomy of processing memory architectures. We divide those processing memory architectures into two classes, as I said: processing using memory, where we are going to use the analog principles of the memory device to do computation. So we are not including new hardware to do computation. We are basically using the way that the memory device operates, so that we can do some computation itself. And the second approach is what we call processing near memory, where we are actually moving some computing capabilities, some logic to nearby the memory device to do a specialized computation. So let's then get started with those approaches, starting with the processing near memory approach. So going back to the applications, so we did this study in 2015, and we saw that for graph processing workloads, even though they a common approach of accelerating that is just putting more cores, because usually graph processing is a quite highly parallel workload or domain. Just including more and more cores does not lead to similar or scaling speed ups, because again, graph processing applications are quite memory bottlenecks. And we are our goal back in this paper was to actually design accelerator that could provide better scaling for this graph processing application. And when you look at the key graph processing workloads themselves, so here, for example, I have there is a simple code for a page rank graph processing workloads. We saw two main things from those applications. So the first one is that they provide when you're doing graph processing, we do a lot of random memory access across the graph, because you don't know. So when you reach a vertex, we don't know which vertex you're going to be accessed next, because of the way that we are presenting large graphs. And also the second observation is that we actually do really little computation when we are doing graph processing. And taking advantage of this new memory architecture that I mentioned before, in particular 3D stack memory, we designed this graph processing architecture that adds a simple in other cores in the logic, it's called logic die, or of a 3D stack memory device. So this is possible because when you look at the architecture of those 3D stack memories, they use a base die where they put the controller to control the upper DRAM layers, and in that die itself there is some free space that can be used to include some computing resources. So we actually look at that opportunities to accelerate graph processing, and based on that we create a new highly parallel system that use different techniques like message passing and prefetching to accelerate graph processing. And we saw that our proposed architecture called Tesseract provides way larger overall throughput, memory throughput than processor-centric architectures at the time. And because of that, we can largely speed up graph processing algorithms by 13 times, for example, and reduce energy consumption in the system by 8 times for those applications. So we published this paper in ISCA 2015 for the Tesseract paper for graph processing. And this is one of the first examples of processing near memory architecture. So we are moving those simple and other cores to nearby the memory chips themselves, so in the logic-based die of the 3D stack memory architecture. And there are other examples of this approach. For example, this JSTOR paper we published in ASCO 2022, where the goal here was to accelerate genome sequence analysis. So when you look at genome sequence analysis, we restore the genome, like for example, the reference genome for the human genome in the storage subsystem. And when you're doing a particular algorithm on top of that reference genome, for example, sequence alignment, we need to move the data from the storage subsystem to the computing units themselves. And it's a lot of data because the size of the genome, the reference genome is quite really large. So this creates computation overheads and also data movement overheads in the system. So computer-centric accelerators have rethink the way that this is done by redesigning heuristics, accelerators, and also filters to reduce the amount of data that is moved from the storage to the computing resource. So even though this improves the computing requirements of this genomic algorithms, still you need to move the data of the reference genome from the storage subsystem to the compute units themselves. And so we still have to fix the data movement problem created by those systems. So in this particular accelerator that we are designing here, we had the idea or have the observation that not all data is equal data when you're doing genomic analysis. So we can do some filtering previous to the alignment so that we don't need to move the entire reference genome to the computing units themselves. And there are two different types of filtering that we can do, exactly matching reads and non-matching reads. And we are going to use some logic nearby the storage itself to do those filtering. So we propose this work, which is called JSTOR, which basically adds some logic nearby the storage subsystem to do this filtering. And by doing so, we can improve computation performance and also reduce the data movement traffic from the storage to the computing device themselves. And our evaluation, we saw that using this method, we can significantly speed up the application while you're reducing energy at a really low cost. And again, if you are more interested in this, I invite you to check our paper. So yet another example of processing near memory architectures, now for more consumer workloads, is the work that we did together in Google. In this work, we analyze consumer key workloads in consumer devices like Chromebooks or Google Pixel phones, and we saw that energy was the main bottleneck. And so first, energy is the main bottleneck, right, for the type of device themselves. And when you look at those popular consumer workloads, we saw that more than 6% of the total energy was spent on data movement in the system themselves. And we did further analysis, we saw that the portions that was creating that particular data the portion of computation that was creating that data movement traffic was actually represented by really simple functions or simple operations in the applications themselves. So the key idea here is that we can create customized accelerators to accelerate those simple functions in memory. We can mitigate that data movement traffic. So in this particular work, we designed two different types of logic cores. So we either using small embedded low power cores nearby the memory, so using a more general purpose approach, or using small fixed function units to accelerate the key functions in those applications themselves and place them again in the nearby the memory device. So by doing so, we can reduce the energy and improve performance significantly for those key applications in consumer devices. Another example in the consumer devices over here is inference being running on edge devices by basically, in this case, using the TensorFlow framework. And again, it suffers from similar problem of data movement because of packing and unpacking quantization operation. And again, we propose accelerator to accelerate those key operations. And we saw that using those accelerators nearby the memory device, we can reduce energy by around 50% and improve overall performance for the entire application. So this is the work that we did together with Google. And there are many other examples of accelerating applications using this process near memory frame approach, where you are placing the computation near the memory device. So there are works in our group that shows how to do that using GPUs, also using other applications like linked data structures, accelerating dependent cache misses, speculative execution, key applications like climate modeling, approximating string matching, sequence to graph mapping, more bioinformatic workloads, time series analysis, graph processing, hybrid transaction analytical processing databases, neural network inference, and many other examples. I'm going to briefly talk about one of them, the one for accelerating neural network inference in edge devices. This is a work that we did together with Google. And the problem over here is that we observed that we took 24 different edge neural networks from that was running on the Google Edge CPU, and we saw that there is a significant variation in the on the memory requirement and in the operation and on the operation intensity of the different layers across the different models in those neural networks. So either across the different models that we analyze and across the different layers of the same model, we saw the similar variation in terms of memory and computing requirements. And the problem that we saw is that even though there is this huge variation, the edge CPU accelerator device itself is designed to be a monolithic accelerator that can accelerate different models. So basically, we have an over-provisioning of hardware resources over here for different types of neural network models, which causes energy waste and performance waste for the system. So we saw that by including heterogeneity in the game, so basically by taking the considerations of the properties of each layer for this neural network and designing a system that can accelerate those properties, we can provide a more balanced system. And again, we use the process near memory approach, where we add some logic near the in the 3D stack, in the logic layer of the 3D stack memory device to do so. So in this paper, we identify basically two different families of layers. So layers that were more compute-centric and layers that were more data-centric. And we designed 3 different accelerators that can accelerate the different layers that follow those properties. And we saw that by doing so, we can significantly reduce energy consumption in the edge CPU architecture while improving inference throughput compared to the baseline edge CPU accelerator. So this is the work that we did together with Google, again, a process near memory solution for neural network inference. And there are other ideas as well on the processing near memory architecture. So all of those work that I mentioned so far, they are proposing to include somehow there are simple functions themselves, but they require some coarse grain of computing elements inside the memory device themselves. So another alternative is asking ourselves, what is the minimum amount of computation that we need to add nearby the memory so that we can accelerate key applications? And this was the question that we asked in this paper, PIM enable instructions. And in that paper itself, we just add simple atomic operations near the 3D stack memory device to try to accelerate key applications, and we saw a large performance benefit. There are other works as well that we did, for example, accelerating FPGA, using an FPGA to accelerate data-intensive applications, and in particular for bioinformatics and climate modeling in this particular work. So all of those works that I mentioned so far are work that we did in academia, but process memory architectures, in particular process near memory architectures, are real actually in today's systems. So again, since the release of the HMC device, many other memory manufacturers have been pushing for process near memory solutions. And we are going to talk more about those real process memory architectures in this micro tutorial, in particular the UPMEM architecture in later on lectures, but I'm going to briefly mention them. So for example, in 2019, the UPMEM company, a startup in France, released this UPMEM PIM architecture where they include simple in other cores nearby the DRAM banks of a memory chip device. And this is the example of their system configuration, where they include more than 2,000 cores nearby the DRAM chips, allowing a really high parallel system while providing really high memory bandwidth and memory capacity in those systems. So we are going to see more on the UPMEM system in this tutorial today. I'm going to talk a little bit more and the work that we did together to understand this architecture and what are their benefits and their limitations. To do that, we create this PIM benchmark suite, which is available in our GitHub architecture. So we keep on trying to understand this UPMEM system. So we are trying to, this is a general purpose system, so we are trying to understand which type of applications this PIM system is capable to execute. So we also did some works on accelerating machine learning, classic machine learning workloads in this real process memory architecture. And in this work, we did some optimizations of those applications so that the applications can take advantage of the hardware that we have. Again, we are going to talk more about these systems in today's lectures. Other type of application that we accelerate in the UPMEM system is the sparse matrix vector multiplications, and also bioinformatics workloads here in the alignment step of bioinformatics that we port to this UPMEM system. So it's not only UPMEM that is providing real PIM architectures. Samsung and other memory manufacturers have put on commercially available process memory architectures, particularly for machine learning tests or neural network tests. So their first prototype is called the SimDRAM. Later on, it was renamed to HBM-PIM, which basically used those 3D stack memories to add computation simple vector processing engines to accelerate convolution in doing inference of convolution neural networks. So this architecture supports, again, a really simple instruction set, but is a instruction set enough to accelerate the applications that was the target for this for the SimDRAM architecture. And this again, just a picture of their chip. So Samsung keep working on this architecture. So later on in 2023, this is a recent presentation that they gave at Hot Chips, and they have created a version of the same accelerator targeting large language models, so generative AI. So basically, in generative AI, for example, in GPT-3, the generation step is a quite memory-bound step that takes around 80% of the execution latency of the inference for the networks itself. So based on this observation, they propose 3 different solutions. So one solution is using the HBM-PIM architecture together with GPUs, so that they can accelerate the inference of GPT at the cloud itself compared to GPU acceleration. Another solution is targeting edge devices. So instead of using 3D stack members together with GPUs, they are using low power DDR4, the power DDR4X devices. Again, using a similar architecture than the HBM-PIM by being placed now in a 2D organization rather than a 3D organization. And with that, they can accelerate GPT-3 in terms of performance and energy. And the latest solution uses memory expanders to accelerate generative AI, because usually particularly when you're doing training of generative AI, we require a lot of storage to store the model itself. And to scale the capacity of the systems, they are using this new interconnect-based consortium from CXL to provide some hardware devices that can accelerate those key steps for generative AI. Another solution from Samsung from 2021 is the AxDIMM architecture, but here now targeting is a PIM system targeting recommendation systems instead of targeting convolutions or generative or AI type of networks. Other memory technology or memory manufacturers like SK Hynix also have their own solution. For example, here is the AiM architecture, again targeting neural networks. And Alibaba again has another architecture targeting recommendation systems, and here they are using a different technology called hybrid bounding to merge computation and memory together. So this is a brief overview about these linear memory architectures. I went quite quickly on them because we are going to have more talks in these real world PIM tutorials that go deeper in their architecture. But just, I guess, the takeaway that I want to give here is that we are including some logic closer and closer to the memory arrays themselves to accelerate key applications, either by informatics or neural networks or AI. And those architectures are becoming newer and commercially available over time. So the other approach of doing computation is process memory is the process using memory architecture. So in this case, process using memory, again, we are going to use the analog principles of how you operate your memory devices to do computation instead of adding logic device. So we're going to start really simple. So let's say that you want to allow our memory to do data copy initialization by itself. So we don't want to involve the CPU in this data copy initialization, which is a key operation for data centers at all. So how this is done today? So if you want to initialize to copy one row in DRAM to another row, you need to read cache line by cache line through the memory hierarchy, do the copying, and then write back the results, again, cache line by cache line to the main memory. So this includes high latency. It quickly becomes a bandwidth problem because of the channel that connects DRAM and the memory. The processor is a quite narrow channel, and create cache pollution and also unwanted data movement. So for example, to copy 4 kilobytes of data inside the DRAM, you're going to take around 1,000 nanoseconds and 3.6 microjoule to do the computation. So what we want actually, so there's no reason for us to move the data around. So we would just want to tell the DRAM, based on this address, source address, copy this data to the destination address itself, and don't involve the CPU because the CPU is not doing any computation at all. It's just swapping data. So this, if you can do that, we can have low latency. We can better utilize the bandwidth between the processor and the memory. We don't create any cache pollution because no data is moved into the caches, and there is no unwanted data movement. So the data movement becomes minimal. We are not moving the data across the memory subsystem. So if you can enable this, the latency that it takes goes from 1,000 nanoseconds to 90 nanoseconds, and the energy reduces by around 3 orders of magnitude in that system. But to do that, I need to first give a really quick introduction of the organization of a DRAM chip itself. So a DRAM chip constitutes of a DRAM model, and a DRAM model has several DRAM chips, and a DRAM chip has several DRAM banks, and a DRAM bank is organized as several DRAM subarrays, which are to the arrays of DRAM cells. So DRAM cells are connected horizontally using a word line and vertically using a bit line. DRAM cells connected in the same bit line share a sense amplifier, which is a back-to-back inverter, and a collection of sense amplifier is called a row buffer. So a DRAM cell itself constitutes of a storage capacitor and an access transistor. So this is just another view of a DRAM chip itself. So we have, again, several DRAM banks connected, sharing an interconnect and a chip I/O. The DRAM banks share, again, a bank I/O, and the DRAM subarrays is connected as a collection of DRAM cells sharing a row buffer. So for you to access DRAM, the memory controller operates following three main steps. So, or three main commands. So activate, a read, and a pre-charge. So when the memory controller sends activates to DRAM to access a particular DRAM row, the DRAM chip is going to raise the word line, which is going to create a path between the storage capacitor and the bit line. So the storage capacitor is going to lose charge to the bit line, creating a perturbation in the voltage of the bit line. Then the DRAM chip is going to enable this amplifier, which is going to amplify the difference or this perturbation that was created by the charge stored in the storage capacitor, and is going to amplify that perturbation. The data is amplified either to VDD or to 0, and the data is restored back to the capacitor itself. So after that, the data is latched in the amplifier, and then the memory controller can send read and write commands to access the data. So the memory controller sends, they require read and write commands to read the latched data in this amplifier. And once all of the cache lines have been read, the memory controller issues a pre-charge command, which is basically going to prepare the DRAM array to following up access to a different DRAM row. And basically what this does is it disables the word line, disconnecting the storage capacitor from the bit line, pre-charge the bit lines to a reference voltage, usually half of VDD, and disable the sense amplifier. So this is important to understand how we are going to do processing using DRAM. So back again, what we want is to enable data copy inside the memory device at low latency, low bandwidth, no cache pollution, and no unneeded data movement, improving both performance and energy. So the key idea here is to use what I just explained how DRAM works to do this copy. So here we have a source row that's going to be activated. That row is going to be activated. The data is going to be copied to the row buffer, as I just explained in the DRAM background section. So now we are going to access the destination row, but instead of sending a pre-charge command and closing this row, I'm just going to send another activate to a different row, the destination row, which is going to connect the cells of that row to the bit line. Since the amplifier is stronger than the DRAM cells itself, the data that was amplified from the first activation is going to be copied back to the row that was just activated for the destination row, with de facto copying the one row to another by issuing two consecutive activates in the DRAM chip themselves. So this is a quite simple mechanism. Basically, by sending two consecutive activations to different rows, I can copy the data from one row to another by using the way that the sense amplifier operates to do so. This requires no hardware overhead at all and improves significantly the energy and the performance of the system. So this is just another way of visualizing what was happening here. So you activate the source row, the data is shared, the data is perturbates the charge cell, the charge in the cell perturbates the bit line. The simplifier is activated, enabled, and amplifies the difference. And then I send another activate to the destination row. This connects the destination row to the simplifier. And since the amplifier is stronger than the cell itself, the data that was previously amplified is going to be copied to the destination row. So by doing so, we proposed this book in Rowhammer in Micro 2013, and we saw that Rowhammer can significantly improve performance and save energy compared to processor-centric approaches. So after Rowhammer was published, other works have shown that actually you can implement something similar to Rowhammer using commodity DRAM chips themselves, and they do that by violating the timing parameters that DRAM operates with. we also have proposed some frameworks so that we can provide an end-to-end setup so that we can use these off-the-shelf DRAM chips to do this type of simple operations. And this is called the PiDRAM Works, where we use FPGA-based machine to control those time parameters of the DRAM chip itself. And this is open source, and we have shown that we can successfully do data copy initialization using real DRAM chips using this particular PiDRAM framework, which you can check on our GitHub and your extended paper or paper in archive. So there are other operations that can be done in processing using DRAM, or by using this, playing with the way that the analog properties of DRAM chip themselves, other than copy. For example, we can do NOT operations, for example, using that particular type of setup, and other type of data movement operations. So the main limitation of row clone is that the data movement, the efficient data movement is restricted to data movement inside a subarray in a DRAM bank. So we work on improving that and providing faster data movement across DRAM subarrays, data movement with different granularities inside the DRAM bank or across DRAM banks, and also by exploiting other primitives other than copy, for example, doing book bitwise operations or arithmetic operations. So for the first one, the one that increases the data movement reach of a row clone for also data movement across DRAM subarray, we have proposed LISA. So basically, we make the observation in this paper in LISA that the main problem that you have here is to move data around is that we have low connectivity across DRAM subarrays to move data in the book granularity. And your goal is to improve this substrate. Basically, the key idea of LISA is quite simple. We connect the neighboring DRAM subarrays using isolating transistors, basically creating a path for the data to flow from consecutive DRAM subarrays in the system. This enables LISA to accelerate further applications that row clone couldn't do it, providing larger performance speed-up, performance improvement, and energy savings for those particular applications. So this is our LISA the paper published in HPCA. The Figaro paper also improves this data movement by doing fine-grained data movement across DRAM banks. And the non-paper also improves the data movement to do this data copy across the DRAM banks in a chip. So let's say that now you can do data movement quite efficiently, or data copy and initialization quite efficiently inside DRAM. So what about other primitives? So can you support Boolean operations, for example, like and or not on majority? And we want to do that at low cost, and again, using the analog principles of the DRAM chip itself. So the key idea to do this in DRAM is to basically activate multiple rows. It's quite similar to row clone, right? To activate multiple rows together to do computation. But instead of activating 2 rows this time around, you're going to activate 3 rows, and I'm going to show what this is going to do next. This provides significant performance improvement compared to process-centric approach, and we have proposed this in this Ambit paper in Micro 2017. And other memory technologies also have shown to provide similar opportunities, like non-volatile memory resistive devices, which can enable both data movement and computation with minimal data movement. So the key idea of Ambit here, again, is the triple row activation. So we are going to activate 3 rows together at the same time. So here in this example, we have 2 rows that are with cells which are fully charged and one that is not charged. And when you activate those 3 rows at the same time, the 3 rows are going to perturbate the bit line at the same time, creating some perturbations. And the sys amplifier is going to amplify this perturbation to the majority of the voltage levels of those 3 different DRAM cells. So here, the majority of the 3 rows was VDD. So the amplification is going to go from for the VDD. So the final stage that we have after triple row activation basically is a combination of AND and OR of that particular of that cells of the voltage levels stored in the DRAM cells, and we can control that if it's AND or OR that we want by setting one control row either to 0 or to 1. So we proposed this idea originally in this call paper for AND and OR operations. When we further extend that in our ambit paper in Micro 2017 to also enable NOT operations using the way that the SimpliFier is designed to do the NOT operation inside DRAM. So by doing AND and OR and also NOT now, we have a functionally complete processing using DRAM substrates. They can accelerate any computation. We show that ambit can significantly outperform processor-centric architectures, both CPU-based and also GPU-based, and also significantly reduce energy consumption for those architectures. And we use this ambit architecture to accelerate many other many workloads that require book bitwise operations, as for example bitwaving databases or bitmap indices. And we show again for these real world applications we can significantly outperform processor-centric architectures. So this is the ambit paper, and we keep improving on this idea. So now with row clone we could do copy initialization. With ambit we could do AND or NOT. What about more complex operations like addition or multiplications, right? So basically this was the key problem of this paper that we proposed or presented in ASPLO 2021, SimDRAM, which is a framework that generalizes the computation of ambit and row clone so that we can compose more complex operations like addition, subtraction, or division. SimDRAM is composed of a 3-step framework. The first step generates efficient majority-based representation of a given computation. The second step translates this majority-based representation into sequence of DRAM commands, DRAM rows, activations, and precharge that can then execute the operation in DRAM. And in the third step, we have a control unit in the memory controller that transparently from the user executes that require computation in DRAM itself. So if you are interested in SimDRAM, I invite you to check our paper. Another primitive that we are enabled following similar approaches is, for example, using that approach to do physical unclonable functions in DRAM, so PUF, which can use a similar idea to create basically identifier to that particular DRAM chip. Also, we can generate true random numbers following processing using DRAM approaches, and we did several works in that regard in the many years. So we can do basically row copy initialization. We can do AND or NOT. We can do arithmetic operation in DRAM. We can do true random generation. What about so is it all now? Are we covering all type of computations that we can do using this idea of processing using DRAM? And the basic answer is not. So those other solutions were not able to do transcendental functions. So if you want to do sine, cosine, for example, or we need to approximate those computations using time series, which creates a lot of Taylor series, that creates a lot of latency overhead for the systems. So in this paper here, in this Pluto paper, we basically propose a different way of doing processing using DRAM by using lookup tables. So then we can accelerate transcendental function inside DRAM itself, again, following the process using DRAM idea. And if you are interested, later on in this tutorial, I'm going to talk about processing using DRAM with more details, and I'm going to talk about how this can be done with the Pluto framework. So this processing using memory approach is not limited to DRAM. We also have proposed to do processing using DRAM using other memory technologies, as for example, Flash in this Flash Commons paper, which shows that by doing multiple word line sensing, we can do and then or operations inside DRAM inside Flash device themselves. Again, improving performance and reducing latency. And I'm going to talk more about how Flash Cosmos does that in the later tutorial over here. But basically, the key idea is to simultaneously simultaneously sense several DRAM Flash cells at the same time. Other works from other groups has also shown how to do similar computation using other memory technologies, for example, to do bitwise operations using phase change memory architectures. And there are many other approaches. So particularly the literature on processing using memory for non-volatile memory is quite extensive, and they have been shown to be quite beneficial to accelerate particularly convolutions in neural network inference. And you're going to see why later on in my talk at 1 p.m. So I invite you to check out if you are curious on that. So basically, we talk about two different approaches of processing in memory, processing near memory, which add logic nearby the memory device themselves to do computation, and processing using memory, which uses the analog principles of the memory arrays themselves to do computation. So the question now is, okay, now we can do all of this, but how can we enable all of these in future systems, right? How can we enable processing memory? There are many barriers for the adoption of processing memory in future systems. Again, going across all of the computing architecture stack, from applications, from programmability, security, runtime, and also enable infrastructure for testing. But we can solve each one of those steps one step at a time with a changing mindset. So if you think that we can revisit the entire computing stack, we can enable those processing memory architectures in future systems without so much pushback. So we, for example, can start pretty simple. We can start by enable the bare minimal computing primitives that can accelerate many applications inside the memory device, as we did in the PEI paper in 2015. And we also can enable easy programmability by providing frameworks that can reduce the cost of or the learning barrier for processing using DRAM for processing memory itself, using for example, data parallel patterns, as we propose in this it was recently presented in PACT, and also in this work that Juan is going to talk later today here called SimplePIM. For processing using DRAM, we can leverage, for example, auto-vectorization in model compilers to enable efficient execution of processing using DRAM substrate. And this is the MIM DRAM work that is just recently accepted in HPCA next year. It's another problem that is common. So now that your memory can do computation and your processor can do computation, you need to maintain coherence between the two computing devices themselves, right? So coherence becomes the key problem right here. And but again, we have proposed solutions to fix that coherence problem for processing using processing memory architectures. So this was originally the lazy PIM work, and later on we further improved with the Conda paper. So how can we enable synchronization across the processing memory cores that are placed in your system? And for that we proposed SimDRAM. So how can we enable virtual memory? How can you enable code and data mapping? How can we figure out which application actually can benefit for processing memory or not? And for that, we propose the move analysis methodology that can indicate if what type of data movement your application suffers from, and also which memory, which type of processing, what type of solution can mitigate that memory bottleneck itself. And the move bottleneck basically is a 3-step bottleneck, which first profiles the application, then does some simulations to collect key metrics, both architecture dependent and architecture independent metric, do some classification, and then classify the memory bottleneck of your application. And based on this memory bottleneck, you can figure out if your application would benefit from process memory or not. So really briefly, in the first step of the move methodology, we use a hardware profiling tool to classify if application was memory bound or not. And then in the second step, we collect some architecture independent metrics to characterize how much locality, so both spatial locality and temporal locality, your application fundamentally have. And in the third step, we collect some architecture dependent metrics to see how is the interaction between your application and the system itself. And based on all of those metrics, we classify the applications into 6 different classes of data movement bottlenecks. And each class of data movement bottleneck correlates with a different data movement mitigation mechanism. So either prefetchers, larger cache hierarchies, or processing memory itself. So data move, based on that, we create a benchmark suite, and also our frameworks is fully available in your GitHub setup, GitHub account, and you can be free to give it a look and watch our talks about the move methodology. So to wrap up, what we want in the future is fundamentally energy efficient and high performance architectures with minimal data movement in the system. So then we can have improve all of those metrics together and enable future applications to run efficiently. So to do that, we need to design balanced systems, which requires intelligent systems that are data-centric, data-driven, and data-aware in its design itself. It's in its origin. We need to think about how to enable computation inside and close the memory device themselves. Because of that, we can have large improvement in terms of performance, energy, and energy efficiency for key applications. We can enable new applications and new types of computing platforms that are more memory conscious. And with that, if we have new applications, we can have a better understanding of our surroundings and this further discoveries in science itself, right? So if you have better and more robust and reliable and energy performance and systems, basically, this enables new classes of applications, which enables us as scientists to better understand the system, the environment we are surrounding. So basically, the future for memory-centric computing is quite bright. It's a great time to do research on processing memory architectures because of the push from both industry and the push from applications that we are having that are more data-driven and data-intensive, right? And as a research community, we need to do research in the entire computing stack so that we can enable better fundamental data-centric, data-driven, and data-aware architecture. And again, we can, even though it's a difficult task, we can do that one step at a time. With all of that, we can enable many things. We can enable flexibility, adaptability, better communication across the elements in the computer system. We can enable heterogeneity, and all of that just depends on us having open-minded for future systems. Again, if you are interested in process memory, I invite you to check our book chapter on processing memory, or or invited paper in date about intelligent architectures, and that's basically that. So I just want to briefly acknowledge the funding that we receive for many of our partners from industry, and the Safari Research group itself, or the members of the Safari Research group that have contributed for all of the work that we have talk about here in this presentation. So also if you are interested in the other type of research that we are being conducting in Safari, we can check our newsletter that we keep releasing from time to time with a summary of all of the main research that we have published in that particular time. Also, our lectures on introduction on research or reference papers on available at our website or GitHub's account for most of the tools that we work on or we develop that we are trying to make open, available, and provide support for the community. And the many lectures on processing memory that we give on peer conferences. This is an example I SI last year, or computer architecture class, or digital design and computer architecture class for undergrad, or processing memory classes that we keep giving on hands-on projects or processing memory, and also or real PIM tutorial in many major conferences. For example, the material for the one that we gave in HPCA and afterwards and ISCA is available online, and the material for the one that we are current right now on Micro 2023 is also online. If you are interested in other aspects of memory subsystems like SSD, again, we have classes on that, you can check. If you are interested in bioinformatics, again, we have materials that you can look on YouTube. Heterogeneous systems, hardware, software co-design, the Hammer problem that I mentioned, and also DRAM exploration, and also for exploration of emerging memory technologies. So thank you so much for listening. I'm a little bit over time, but it's an exciting topic, and it's an exciting time to do research on memory-centric computing, and I hope you will enjoy and learn a lot about this topic in today's tutorial. So thank you so much.
Very good, Geraldo. Thank you very much for
Thanks,
the
Juan.
great talk. It's amazing that you were able to fit so many slides in 1 hour, 30 minutes. Let me ask you, well, for people in Zoom, feel free to jump in and ask any questions that you may have. Give me just 1 second. I'm going to ask you a couple of questions,
Sure.
very interesting ones that we have here in the chat in YouTube. So the first one is from Fernando Fernandez. He thanks you for the excellent presentation. The question is, for GPUs, some applications are unsuitable, and in some cases, people still prefer to use a CPU. Is that a problem also for PIM, and how are those problems mitigated?
So that is an excellent question. It is the case for PIM, but there is a caveat on that answer. The caveat is that, as I mentioned here, there is not single PIM architecture right now, right? There is many different process memory architectures, and that was proposed in the past, and you can propose new architectures in the future, right? So if there is an application that has a particular requirement that is not efficient in a given process memory architecture, we can always propose a new one, right? And design around that, because what is fundamental of all of the process memory architectures is just that the computing units are placed nearby the memory device or using the memory device themselves, right? So the type of computation itself, for example, if it's like a SIMD type of computing unit, a vector type of computation, like GPUs, for example, or if it's a computing unit that would be more suitable for irregular memory accesses, for example, as some of the works that I mentioned here, like Tesseract, for example. all of those can change. So you can, PIM is quite flexible in that regard. You can adapt for different type of computing requirements so that the data movement bottleneck on the system can be alleviated. There are also, as I mentioned, a proliferation of different real processing memory architectures right now that one can go to, right? So, for example, the UPMEM architecture that we are going to talk about here is a quite efficient parallel architecture, but is unsuitable for example, neural network training, because neural network training requires, at least the way that is done in GPUs, requires a lot of float point operations and multiplications, which the UPMEM architecture does not fundamentally support or does not natively support. But you don't need to go to the UPMEM architecture if that is your key application, right? In comparison, Samsung have proposed or have been making commercial processing memory architectures where the main computation or main computer resources is float point multiplication and addition for convolutions, right? As the HBM-PIM architecture that I mentioned here. So you can change. So instead of going to one for the UPMEM architecture, we can go to the Samsung HBM-PIM architecture, which are two different processing memory architecture, but still processing memory architectures, right? So this is, let's say, this memory-centric approach is more flexible than traditional processor-centric approach, where like a GPU, for example, where the type of architecture is quite rigid itself. So I guess hopefully that answered the question.
Yeah, I think that was a good discussion. I would say that PIM is also a complement to existing systems like CPUs and GPUs. And
Yes.
in that sense, if a GPU is not good for some specific part of the computation, maybe PIM can help on that. Or CPU, that also applies to CPUs.
Yes, and collaboration has been happening a lot, particularly with this new AMD GPU chip with the Samsung HBM architecture, right? So that is an excellent example where some computation is done in the GPU because it requires really high throughput in terms of computation. But once the computation becomes data movement or intense, that computation is moved to the HBM-PIM inside the GPU SRC itself, right? So there's definitely opportunity for collaboration across different architectures.
Yeah, exactly. That's a very good example. Another example is, for example, the Alibaba PNM, where part of the recommendation system is executed on the GPU. The PIM system that Alibaba is proposing has a goal to replace the part that is still computed on CPUs. You have already introduced Alibaba, and we are going to talk also briefly in the next talk. There is another question here. This one is with respect to PiDRAM. It says why it needs RISC-V in the FPGA demo.
So the RISC-V over there is basically it's to ease the computation, right? So the goal of SDRAM was to, I'm sorry, not SDRAM. The goal of PiDRAM was to provide the end-to-end framework so that we can use off-the-shelf DRAMs for processing using DRAM computation. So the RISC-V there, so basically we encapsulate instructions, like let's say copy or initialization, using some custom instructions, and the RISC-V processor is the one responsible to dispatch those instructions to the memory controller, the custom memory controller that is placed in the FPGA itself. So it's basically because of that we want to have the whole goal of the PiDRAM work was to have an end-to-end framework for processing using DRAM exploration. So we need a core so that the core can dispatch instructions to the DRAM chip itself.
Mm-hmm. Okay. One more question. Well, this is in YouTube. We also have one more question. what's PNM compared to PUM? I think that you can very briefly summarize what's the difference between both.
Yes. Yeah, that is that is a really good question. Is I guess is really important to get that from this presentation. So processing PNM, processing near memory, as the name say, near. We are basically taking logic. So imagine your processor, and instead of keeping it far away from the memory, we are moving that processor core closer and closer and closer to the memory array itself. So it can be like inside, so you have the DRAM model, for example. It can be in the PCB of that DRAM model, or it can be inside the DRAM chip of, for example, of the DRAM model, or nearby the DRAM bank, as the UPMEM architecture that Juan is going to talk about later. And so it's always closer and closer, and the closer that you get to the memory, the larger the memory throughput that the PIM core can enjoy. But still you have logic. You still are designing logic to do computation. In processing using memory, we are not adding any logic. We are just changing the way that the DRAM operates to do computation. So in the ambit example that I explained, for example, you are going to basically do and OR operation by simply activating 2 rows at the same time. So to activate 3 rows at the same time, fundamentally, you don't need to add new hardware to do that. You can just send 3 DRAM commands to DRAM activate commands to the DRAM chip itself. And because of that, we are not adding logic. So you're using the DRAM themselves to do computation. So this is the, let's say, the most fundamental processing in memory type of architecture, because in that case, no logic is being added to the device. It's just pure memory that instead of just storing data is also doing some operations itself by itself. So I guess hopefully that was more or less clear. If you are still confused, look at the near and the using. That gives an indication of what's happening.
Okay, yeah, thanks for the answer, Geraldo. I have 2 more questions. Let's try to solve them quickly so that we can move to the next presentation. From in the YouTube and the Zoom chat, we have a question. Well, thanks for your presentation. I want to ask if PUM architectures can potentially suffer from row hammer or row press.
That is a really good question that you're keeping getting being asked about. For row hammer, is unlikely that we are going to suffer from row hammer, because every time that we basically so the way that one way of mitigating row hammer is by refreshing rows, refreshing the rows to their original values, so that we minimize the leaking of the data. So when you're doing processing using DRAM, we do a series of activate and precharge of DRAM rows. And when you do that, we are basically refreshing the data. Of course, we are refreshing the data with new values, but it still is a kind of a restoration process. And because of that, it's unlikely that that memory, by doing processing using DRAM, we are going to incur row hammer effect in the DRAM chip itself. We didn't evaluate row press yet, but it's pretty likely that is a similar. It's even unlikelier than that effect is going to happen because of processing using memory. Because what row press does is that it keeps the row open for a longer time, and by keeping that row open for a longer time, we experience bit flips. And here we are not keeping the row open for a longer time. Once the computation is done with the minimum, we just want to keep the row open as needed, because that is latency for computation, right? So the quicker that we close that row, the faster we can move to other computing primitives. So it's unlikely that row press is going to incur bit flips. But really briefly, I want to say that there are other ways that other security or reliability problems that processing using memory DRAM faces, that are really good research points that needs to be solved, and is a really hard problem because ECC itself does not solve those problems for processing using DRAM. So yeah, so hopefully that was a quick answer for that.
I think so. Yeah, thank you, Geraldo. And one more question is, thanks for the talk. If PIM with PNM becomes prevalent, should the architecture and design of the main CPU be adapted for such a system?
Definitely yes. So there is so it needs to be adapted to first efficiently support the processing using processing near memory architecture itself with ways of, for example, runtime support for that system, identifying candidates for offloading, partitioning computation. All of those are things that require cooperation with the for the processor in the chip itself. And second, we need to think how much do you need the amount of computing power in that processor core itself now that we have computing capability nearby the chip, right? So the basically we need to one of the things that I try to convey in the talk is that we need to have a balanced type of design where the power is distributed more evenly across the computing units or the computing engines in the system. So basically, would be also required to rethink how much, if I really need aggressive, I don't know, aggressive parallelism in the core, for example, in the main processing core, now that we have parallelism available nearby the memory device itself. So there is a rebalancing that hopefully is going to happen when the processor near memory architectures become more and more integrated to commercial cores.
Yeah, I agree. I think that, I mean, your answer makes a lot of sense. I don't think how close are we from that, given that at the moment, manufacturers of CPUs and GPUs are different from those working or developing processing in memory systems. But I think that at some point, both will evolve together.
Okay.
Okay,
thanks so much
great.
for the questions.
Yeah, definitely. Thank you very much for the talk. Great, Geraldo. Thank you again. I think, well, we'll have you again in a couple of hours talking about processing using DRAM. So looking forward to your next presentation.
Thanks so much, Juan. Thanks everyone for the questions again.
Oh, great. Now we are going to move on to the second lecture today, which is about processing near memory systems. I hope you already see my slides. I think you should be able to see my slides. We are going to talk about real-world processing near memory architectures that are those that are already in the market or have been presented as prototypes and are already showing pretty promising results for different important applications. Again, same as before, feel free to ask any questions over Zoom or in the YouTube chat. I will keep an eye on the YouTube chat and we'll try to answer everything. This is going to be a relatively quick presentation. We will spend about 30 minutes, and I'm going to briefly recap on the existing real PNM architectures, and I will also introduce with a little bit more detail the UPMEM PIM architecture and how to program it, because you guys need a background if you want to try the optional hands-on lab that we have at the end, and as I said before, is already available in the website. So this is a slide that Geraldo already showed. There are two main PIM approaches. One is called processing using memory, when we take advantage of the analog operation of the memory cells in order to perform computation, memory cells or other components, for example, the sense amplifiers. And there is the processing near memory trend, where some sort of processing element or compute capability is placed near the memory arrays. And existing PIM systems, those PIM systems that are already real, are of that type are processing near memory systems. The first one that appeared in 2019 was the UPMEM PIM architecture from the French startup UPMEM, but later in 2021 and 2022, several prototypes have been presented by Samsung, by SK Hynix, or by Alibaba. And all of them are very interesting. We are going to briefly talk about them here. We are going to highlight what are points in common and what are differences in these systems, starting with the applications, the main applications that they target. The first of them was the UPMEM PIM architecture. This is a slide that Geraldo already showed. Since 2019, we have access to this system that is based on DIMMs, based on DDR4 modules. The key difference with respect to conventional DDR4 modules is that inside the chips, inside these so-called PIM chips, there are memory arrays, there are DRAM subarrays or DRAM banks, but also small processors that are called DRAM processing units or DPUs. And this is how the DIMMs look like. As you can see, they are at first sight conventional DRAM DIMMs, but as I said, they have small processors inside called DPUs. There have been a couple of generations already of this architecture with more, at least a higher frequency of the DPUs, and the system keeps improving. Actually, more recent generation that we have tried ourselves that runs at more than 400 megahertz. And this is how one of these UPMEM-based PIM systems look like. Current UPMEM systems that you can buy because they are commercially available. They have more than 2,500 of these DPUs. Is a system with a dual socket CPU, and connected to the dual socket CPU, we have conventional DRAM DIMMs, because still there is a main memory, or there is a standard main memory without PIM capabilities next to the PIM DIMMs that have the PIM cores, as I said, 2,560 PIM cores, and up to 160 gigabytes of PIM-enabled DRAM. This is some architecture that we have already studied with a lot of detail. Gerald already mentioned the benchmarking and characterization work that we published already last year, and is the basis of some of the contents of this course. UPMEM filed a patent back in 2019, and I think it's interesting to check the abstract of this patent, because it basically explains the very briefly what the system is about. It's a memory circuit with a memory array and a first processor. As I mentioned before, this first processor is called DRAM processing unit, or DPU, and the memory has a control interface for a central processor, the CPU, to access the memory banks. Access the memory banks, to copy data, and also to launch the computation on the first processors on the DPUs. When the first processors finish the computation on the data that resides in the memory banks, those memory banks become again accessible to the central processor in order to fetch the results, to gather the results, and move them to main memory. And this is from a picture from the patent, where we can see the central processor, system on a chip, CPU, and the memory arrays next to which we have the small processors. This is like the first view of the first overview of the UPMEM system organization. As I mentioned before, the host processor has access to main memory, to standard main memory, and also to PIM-enabled memory. And this PIM-enabled memory is composed by chips. In each PIM DIMM, there are 8 or 16 chips. The most recent generation, there are 16 chips. These are 2 ranks of 8 chips. And inside each PIM chip, we have DRAM banks that are called main RAM or MRAM of size 64 megabytes, and there are the processors, the DPUs. So we have one of these processors next to the each DRAM bank, and in total we have 8 DPUs and 8 DRAM banks per chip, so 64 DPUs per rank. The DRAM processing unit, as you can see here, has access to the memory bank, and it has a pipeline, an instruction memory, and a local memory. Indeed, we have a more detailed view here of the PIM chip, where you can see the DDR4 interface for the host to access the DRAM banks, the control and status interface for the host to communicate with the DPUs, and then in each of these 8 slices that you can see here on the slide, we have the 64 megabyte DRAM bank or MRAM bank that is accessed through a DMA engine. And with this DMA engine, we can either move instructions to the instruction memory of size 24 kilobytes, it's called IRAM, or data operands to the scratchpad of size 64 kilobytes that is called WRAM. And then we have a pipeline. It's a pipeline of 14 stages. It's an in-order pipeline. More recent DPUs run at a frequency of up to 425 megahertz. And this pipeline is an in-order pipeline, but it's also fine-grained multi-threaded. It can run up to 24 hardware threads over these 14 pipeline stages that are to select a thread, to fetch an instruction, access the register file, perform operand formatting, perform the operations or in the ALU, or the accesses to the WRAM, to the scratchpad memory, or finally resolve formatting. So those are the 14 stages, as you can see in the slide. Fine-grained multi-threading, I think, is, as I get, it's well known by all people attending this tutorial, but if you want a little bit of background on fine-grained multi-threading, you have a couple of slides here, and also a link to a lecture with more details about fine-grained multi-threading. It's a hardware technique where we deploy multiple threads, multiple thread contexts, including a program counter and registers. And in each cycle, the fetch engine fetches an instruction from a different thread. The advantage of doing fine-grained multi-threading is that there is no logic needed for handling control and data dependencies within a thread. Of course, it also has its drawbacks. For example, single thread execution suffers because you would not be filling the entire pipeline, but that's something to take into account when using fine-grained multi-threaded architectures. They have the advantage that they can hide latency, for example, memory accesses, by fetching instructions from different threads, and this way keep the pipeline fully busy all the time. As I said, if you want to learn more about fine-grained multi-threading, I would refer you to this lecture from Professor Mutlu from one of the courses that he teaches at ETH. The DPU pipeline, as you have already seen, is one of these sort of fine-grained multi-threaded pipeline. In this case, there are up to 24 hardware contexts, so up to 24 hardware threads, each with its own program counter and with its own registers. And yeah, you can learn more about the DPUs and about the ISA, the instruction set architecture of this ISA. If you check the UPMEM programming guide, there are a lot of details there about the different instructions. What you need to learn for now is that it has specific 32 ISA. Is not RISC-V. Is a question that we all usually get, is if it's a RISC architecture, why not RISC-V? Well, UPMEM folks had their reasons, and they have explained that in the past to design their own ISA. It's a scalar ISA that allows the compiler allows compilation for 64-bit C code with their LLVM clan compiler, and but is natively 32-bit. Actually, it's natively 32-bit. What it natively supports, as we'll probably will see later, are integer operations. Floating point computations, for example, are emulated. And here you can see some example code. At the top, you can see the C-based code. At the bottom, you see the compiled code for the UPMEM DPU ISA. So this simple code corresponds to a micro benchmark that we develop in order to evaluate the 32-bit integer addition, the throughput of 32-bit integer addition. So as you see, we have a for loop going over an array and performing computation, in this case, an addition on the values that reside in the WRAM, in the scratchpad that we have previously allocated here. So one by one, each tasklet, each thread running on the PIM core, on the DPUs, accesses the data, accesses a data element from the buffer in the WRAM, in the scratchpad, performs some addition, and then writes back. And this is the compiled code where you can see the necessary instructions for the for loop, these add instructions for index update, or this jump conditional to check the end of the for loop. Are there any questions in Zoom? Feel free to ask if you have any questions. Any questions are welcome.
What's the password?
Hello, I cannot hear you. May I know your question? Sorry. Okay, maybe. We have someone who is accidentally unmuted here. Okay, so feel free to speak up if you have any questions. I'd be glad to discuss anything. As I was saying, the threads executing this micro benchmark would first need to access WRAM in order to fetch data from the WRAM, move it to the registers before performing some computation. That requires us to first calculate the address and then load from WRAM. Then we perform the actual addition, is these add instructions that you see here, and finally store to WRAM or SW operation to store the result back to the scratchpad memory. Well, you can learn much more about the architecture of the UPMEM PIM if you check many of our past lectures, also past tutorials as well, many details as well in the book chapter that I mentioned before. That's not, sorry, the book chapter, the paper that we published last year that I mentioned before. There are some interesting takeaways of this paper that I would like to share with you. First one is one of the analyses that we did was measuring the arithmetic throughput versus the operational intensity in a similar way as the roofline model does. And here we perform experiments for different number of PIM threads from 1 to 16, each corresponding to each of these dots that you see here. One thing that we realize is that there is a memory bound region and a compute bound region. In the memory bound region, we see that the throughput increases with the operational intensity, while in the compute bound region, the throughput is flat at its maximum. The most relevant observation from these analysis is that the throughput saturation point is extremely low. Even for integral additions that are natively supported, the throughput saturation point, the transition between the memory bound region and the compute bound region, is as low as 1/4 operation per byte. And it's pretty likely that real applications, real-world applications, will have higher operational intensity than that. So we can say that the UPMEM PIM architecture is fundamentally compute-bound, and we expect that the most suitable workloads for this UPMEM PIM architecture are memory-bound in conventional processor-centric systems like CPUs and GPUs. We perform in our work comparison to CPUs and GPUs for the different applications. Geraldo already mentioned these PRIM benchmarks that we released with the paper with our characterization analysis. We found that there are some more PIM suitable workloads, some other that are less PIM suitable or less suitable for the UPMEM PIM architecture. There are some key characteristics of these workloads that are more suitable to UPMEM PIM. The first one is that they mostly have streaming memory accesses, because that's a way of maximizing the bandwidth that the DPUs are going to get. The second one is that there is no or little inter-DPU synchronization, and that's very important because whenever we need to communicate from DPU to DPU, communication will need to happen through the CPU, through the host CPU. So it takes time, and if it's very frequent, that's definitely going to affect the performance negatively. And the third characteristic is that there is no or little use of integer multiplication, integer division, or floating point operations operations, because these type of operations are emulated. 32-bit computation, 32-bit integer computation is natively supported, but not multiplication and division, because the hardware doesn't have a powerful 32-bit multiplier. So needs to emulate through a shift and add operation. So with these three characteristics, a workload can be potentially suitable for the UPMEM PIM architecture. The other key takeaway is that, well, I just mentioned, out of these characteristics, second key takeaway is that those workloads that perform the best on the UPMEM PIM architecture have used no arithmetic operations or only simple operations, bitwise operations, or integer addition and subtraction, and they have little or no communication between DPUs. Here you see just some summary of result, the comparison that we did to CPU and DPU. What we observed is that for most of the PIM benchmarks, the UPMEM PIM-based system outperformed the CPU, the state-of-the-art CPU that we use for comparison as a baseline by 23 times on average, while the GPU, not in all cases, the UPMEM PIM system outperformed the GPU that we use, was an NVIDIA Titan 5, but for 10 of the 16 PIM benchmarks, we observed an average improvement of 2.54 times. And the analysis in terms of energy efficiency was more or less along those lines as well. Wherever we see performance improvement, we also see energy savings. All codes that we use in our study are publicly available in the repository. You have a link to this one. But the UPMEM PIM architecture is not the only real one. Geraldo has already mentioned a few of them in his talk, but now I want to briefly recap on them again. The UPMEM PIM architecture, Samsung developed HBM-PIM, or it's called HBM-PIM or DRAM function in memory DRAM. It replaces some of the layers in HBM2 memory with special layers where there are small processors called PCU blocks. These PCU blocks have access to 2 memory banks, and this way they can perform very efficient computation, enjoying very high bandwidth when accessing data from the nearby banks. These PCUs, or these PIM units, are SIMD units with 16 lanes. They are designed for machine learning, artificial intelligence workloads. So it makes sense to have SIMD units there because, as we know, there is a lot of parallelism usually in layers in neural networks. One interesting thing of PIDRAM or HBM-PIM is that it's compliant with the JEDEC standard, so it can work with and modify JEDEC controllers. We have prior lectures about PIDRAM and HBM-PIM. Here you have the link about one of them from the past fall 2022. So if you are curious and want to take a look, want to learn more about this, please check this lecture. There is also another proposal from Samsung. It's called AxDIMM. In this case, is a DIMM-based solution. The idea is to expand this AxDIMM buffer with some reconfigurable units, sort of FPGA, small FPGA that we can configure, that we can program for different operations that can be accelerated when computing near the memory. Here you can see one example. This was the one development that Samsung did for recommendation systems, in particular the SLS operators that are sparse operators, so need to access data in a sparse data in the memory ranks, and so because those accesses tend to be irregular, is good to perform the computation near the memory in order to enjoy higher bandwidth. And here you can see, in a similar way as it happens in UPMEM as well, the host first needs to copy data to these ranks, and then launch the computation on these near memory processors or near memory accelerators to fetch the data from the rank, perform the corresponding computation, that in this case mostly vector addition and reduction, and at the same time the CPU is continuously checking some configuration registers in order to check when computation has already finished and gather the results. We also have lectures about AxDIMM, so please take a look if you are interested. There are also proposals. There is also this interesting proposal from SK Hynix that is called Accelerator in Memory, or AiM. It's similar to HBM-PIM or SimDRAM in the sense that it targets as well artificial intelligence and neural networks. And in this case, it's based on GDDR6 memory. So the idea is to place one processing element, one PU, near the each memory bank. And this PU is again kind of a Cindy unit with multipliers and another tree to perform multiplication and additions, because those are key operations inside the in the neural networks that this architecture targets. Here you have a link to a recent lecture about accelerator in memory. And Alibaba, we already talked about Alibaba HPNM. This one is targeted at recommendation systems. In this case, we have a DRAM die and a logic die that are glued together with hybrid bonding. And as we discussed before, some of the operations, some of the steps in the recommendation system are still running on the GPU, but some others, which typically run on the CPU, are good candidates for PIM. So that's why Alibaba develops this HBM-PIM architecture with specialized engines or accelerators for this coarse grain matching and fine grain ranking that are necessary for the recommendation system that they target. Also, a lecture about HBM-PIM. So as you can see, there is a variety of real PIM architectures. There are some differences between them because some of them are proposing a near bank solution, others a near chip solution. Some are general purpose, or in other cases, we see the units are more special functions, and they also have different execution paradigms. Fine grain multi-threading in the case of UPMEM, or SIMD in the case of DRAM or AiM, or even systolic arrays, as you can see in HBM-PIM. And they have also support for different operands, different data types, integer, floating point, depending mostly on the type of applications that they target. And same way they have there are differences in the type of memory that they are specifically using, or the DRAM technology that they are using. All of them are DRAM for now: DDR4, LPDDR4, HBM2, or GDDR6. But more interestingly, there are also some common characteristics between these PIM units. The first one is that there is a host processor, a CPU of a GPU with access to standard main memory and PIM-enabled memory. The PIM-enabled memory contains multiple PIM processing elements with high bandwidth and low latency memory access. These PIM processing elements run only at a few hundred megahertz and have a small number of registers, small or no scratchpad or cache at all. And they usually need to communicate, the PIM processing elements usually need to communicate via the host processor. This is how one of these systems look, where you see the standard main memory, the PIM-enabled memory, and in PIM-enabled memory, we have near memory arrays and some PIM processing elements nearby. I'm going to take about 10-15 more minutes in order to introduce how to program a general purpose PIM system. I will share also some links are already in this presentation about for longer lecture about how to program the UPMEM PIM system, which is definitely recommended that you take a look if you want to try the hands-on lab that is available in the tutorial website. The UPMEM DIMMs follow the accelerator model in their integration in a real system where UPMEM DIMMs coexist with conventional DIMMs. And when we talk about the accelerator model, that what we mean is that we need to explicitly move data between the main processor and the accelerator, in this case, the UPMEM DPUs, and we need to explicitly launch the computation onto the UPMEM processors. If you think about it, this resembles GPU computing, because in GPU computing, we first move data data from the CPU memory to the GPU memory, perform computation on the GPU cores, and then we moved back the results to the GPU memory. This is how the patent from AxDIMM explains all this process. The CPU or the SoC copies data to the DRAM banks, to the MRAM banks in the PIM DIMMs, and then computation happens in these DRAM processors or DPUs, and at the same time, the CPU keeps checking until the computation is done, and then the memory bank becomes accessible to the CPU again. We have already seen this slide, and I want to show you the first programming example, vector addition. In vector addition, as you know, what we are going to do is performing the element-wise addition of two arrays, A and B, and write the result in an array B. If we want to compute this vector addition on a system with AxDIMM DPUs, the first thing we need to do is partition the array across DPUs. For example, this first chunk of the array goes to DPU 0, this one to DPU 1, DPU 3, DPU 4, and then because we have threads running on the DPUs, these threads are called tasklets in AxDIMM terminology. We are going to partition further in order to give each thread the corresponding chunk of the array so that they can operate in parallel. For your reference, you can access the AxDIMM SDK documentation. It's definitely a pretty good resource, but I would like to give you some general programming recommendations that are well known about how to get advantage of the AxDIMM PIM system. First of all, if you have a system with multiple DPUs, one thing that you probably want is that you want to execute on the DPUs portions of parallel code that are as long as possible, because this way you can take advantage of these so many DPUs, more than 2,500 that you can have in current AxDIMM systems. Ideally, the computation assigned to each DPU is going to be independent of the computation assigned to other DPUs, because that would avoid the need for communication between DPUs. Then remember that this communication needs to happen through the host CPU, and that's not desirable. And again, because we want to parallelize the execution of our workload, we are going to use, or we should try to use, as many working DPUs in the system as possible. The last recommendation, it relates to the length of the pipeline. Remember that it's a fine-grained multi-threaded pipeline, so we want to keep all pipeline stages busy. One recommendation from the AxDIMM documentation, and that's also something that we confirm with our analysis of the AxDIMM PIM architecture, is that we need to launch at least 11 tasklets or PIM threads per DPU in order to fill the entire pipeline. When programming an AxDIMM PIM system, the first thing is to allocate DPUs. This is creating a DPU set. It's something as simple as using this DPU alloc and deciding how many DPUs are we going to use, because we are going to need. And the good thing is that we can allocate multiple DPU sets at the same time. For example, if we have multiple applications making use of the AxDIMM DPUs, or if we have inside the same program, we have the need to use different number of DPUs over time, or even we want to run tasks in parallel on different DPU sets. Same as we can allocate DPUs, we can also free DPUs. And here is you have a brief example where we do this in every iteration of the algorithm in Needleman-Wunsch, where we create a two-dimensional matrix and compute it anti-diagonal by anti-diagonal, because the size, the length of the anti-diagonals changes over time, over the execution. We need more or less DPUs because we have more or less parallelism. Next thing to do after allocating the DPUs is loading the program onto the DPUs. Remember that each DPU has an instruction memory, and what we need to do is to explicitly copy from the host CPU the program to the instruction memory, to the IRAM in each DPU, and that's something we do with this DPU load. And we can have different binaries, different programs at the same time in different DPUs if they are in different DPU sets, and that's what we want, for example, to enable task level parallelism. Next thing to do, we have to copy data from the main memory to the PIM enabled memory. Remember that The UPMEM DIMMs can be seen as an accelerator, a coprocessor that has its own memory. So that's why we need to copy data from the CPU to the DPUs, or vice versa for the results. And there are different ways of doing these transfers. There are serial, parallel, and broadcast transfers. And here in the next slides, you see the specific syntax that we need to use for these different type of transfers. This is, for example, for the serial transfers, copy to when it's from the main memory to the PIM-enabled memory, or copy from when it's the other way around. There is in the UPMEM PIM system, in the DPUs, we don't need to explicitly allocate data. We just use an offset with respect to the beginning of the memory, let's say of the NRAM, that is this DPU NRAM heap pointer name. So from there, we can start placing data that will be used by the DPUs. And for example, with the serial transfers, what we are doing here is copying these buffers of certain size onto the MRAM, starting from this MRAM heap pointer, either from the very beginning, that's why the offset here is 0, or from whatever number of bytes that in this case corresponds to the size of the buffer A that we are copying to each of the NRAM banks. And there are also parallel transfers. In this case, we target multiple DPUs at the same time. Syntax is slightly different because we first need to prepare the transfers and then execute the transfers either from CPU to DPU or vice versa. But again, we use offsets and we need to define what's the size of the transfer that we are performing. One important characteristic of these parallel transfers is that all buffers need to be of the same size. So whatever we copy, we can copy different things to different DPUs, but whatever we copy to each DPU should be all of the same size. And there are also broadcast transfers. In this case, we are transferring a single buffer to all DPUs. That's why they are called broadcast. And as you see, its syntax is again very similar, pointer to main memory and transfer size. And we evaluated how fast these data transfers are. This is just one example in this slide about coexisting different types of transfers in different workloads, in the same workload, sorry. For example, select is an operation where we can have parallel transfers, but then we might need serial transfers because the selected or filter elements are different. The number is different in different DPUs. So in that case, buffers cannot be of the same size. So we need to use serial transfers. And for inter-DPU communication, as I said, we need to use these serial or parallel transfers because there is no direct communication channel between DPUs. In our work, we have also analyzed how fast these data transfers are. I'm not going to spend time right now on this. What I can tell you, the main conclusion of this analysis that we did is that the maximum bandwidth of these transfers is, as you could expect, is limited by the maximum bandwidth of the DDR4 interface. Remember that the UPMEM PIM system is based on DDR4 memory, and as a result, the maximum bandwidth that these transfers can have or can achieve is limited by this maximum bandwidth of DDR4 memory. Very briefly to mention as well, if you think about the way that data is usually mapped when we use DDR DIMMs, we usually chop the bits or data elements into a certain number of bits, let's say 8, that go to different chips, right? But now we want entire words or also entire buffers to go into the same chip and in fact go into the same memory bank. Why is that? Because we want each DPU to have access to all the data that needs in the same DRAM bank. And that's why the runtime library of the UPMEM system performs sort of a transposition in order to place data in the desired way for the DPUs to have access to the necessary data in their own DRAM bank. We did a lot of analysis of the UPMEM system. Here you have a link, for example, to the micro benchmarks that we use to analyze CPU, DPU, and DPU, CPU communication. One more thing, as after you have copied the data, well, you first allocate the DPU set, then you load the program, then you copy data to the DPU, to the DRAM bank of the DPUs. Now it's time to launch the kernel and perform the actual execution. And this is the instruction that we need to use, DPU launch, as simple as that. This can be done synchronously or asynchronously. Basically, the main difference is that if it's synchronous, the CPU will wait until the execution on the DPUs finish, and it will do nothing else. But if it's asynchronous, the CPU can continue doing things, something that enables, for example, heterogeneous computation, concurrent heterogeneous computation on the CPU and the DPUs. You can find all the details about how to use synchronous or asynchronous execution in the UPMEM programming guide. And for passing parameters to the kernel, we use exactly the same APIs that we need to use for either serial transfers or parallel transfers, but in this case, the transfers are directly to the WRAM, to the scratchpad, usually because we are just transferring a few parameters, so we don't need to store them first in the MRAM. We can copy them directly to the WRAM. But you have, in the hands-on lab, there are some templates that already do this for you. Okay, so this is the vector addition example. Now, if you take a closer look at the kernel itself, you'll see that it's pretty simple. It's a SPMD, so single program, multiple data, kind of similar. For example, if you're familiar with CUDA programming or OpenCL programming, you will see that is very, very similar. We need to use a tasklet ID or a thread ID for the thread to access the data that corresponds to each. That's why we have some base address that defines where the arrays start. Remember that this is a vector addition, so we have two input arrays, A and B, and this is where they start. Remember that one of them starts in the beginning of the MRAM, while the other one it starts right after the first one, right? So B is after 8. Here we allocate WRAM for both array A and array B, and then we have this outer loop, this outer for loop that distributes the computation over the tasklets depending on what's their ID. First thing that we have to do is to transfer chunks of the array A and B from the MRAM to the WRAM, because the threads need to access the data from the WRAM. Then we perform the actual vector addition, and finally we write back results to the MRAM, because the MRAM is later accessible by the CPU. And for vector addition, the code is, as you see, is very, very simple. I'm going to stop here. There is much more information in this presentation, for example, about how to do intra-DPU synchronization, because the DPU or the UPMEM system provides ways of synchronizing threads with mutexes, with handshakes, barriers, or semaphores. If you're familiar with parallel programming, all of these should be well known. You have a few more slides about how to perform, for example, reduction or scan operation. But if you really want to, learn in detail about how to program, or with more detail about how to program this PIM system, I would recommend you these lectures from several editions of our PIM course. This one corresponds to fall 2022. This one as well corresponds to our computer architecture course. So they are available in YouTube for anyone who is interested about learning more about this UPMEM PIM system. This is all for now. We're going to have a break, about 10-minute break for a quick coffee. And after that, we will continue with interesting talk by Professor Johnson Kim. Really, for sure, exciting work that he's going to present. And I would definitely recommend you to stay for a few minutes and watch the lecture, the talk by Professor Kim. So thank you very much for your attention. I don't see any questions in chat. Feel free to keep posting your questions if you have them there. We can answer them offline as well. So yeah, let's see you in about 10 minutes. Okay, welcome back, everyone. I hope that you can see me and can hear me. Now we are going to move to the second part of this PIM tutorial. We have two super exciting invited talks. The first one is by Professor Jong-Sok Kim, and the second one by Dr. Abu Sebastian. Let me first go with Jong-Sok, with Professor Kim. Professor Kim, please feel free to share your slide.
Okay, let me try.
In the meantime, I would like to very briefly introduce Professor Kim. He is a professor, assistant professor at the Yonsei University, and his research interests span computer architecture and system software with an emphasis on architecture-conscious database management systems, performance modeling, and architecture support for deep learning. He received his BSc and PhD in computer science and engineering from PostTech, and he was a postdoc. He was a postdoc researcher at Seoul National University before he joined Yonsei University, and was an intern at Consumer Hardware, Google Inc., and SLSI Business, Samsung Electronics during his PhD studies. If you're ready, please go ahead. We are really looking forward to your talk.
Hey, thanks for the great introduction, Juan. So welcome everyone. I'm Jong-Sok Kim at Yonsei University. So in this talk, I will present our recent work on accelerating the joint operation of in-memory databases using commodity PIM-enabled DIMMs. So I will be using processing in memory or processing in DIMM multiple times throughout this talk. But to clarify, what I mean by processing in memory or processing in DIMM actually refers to processing near memory. So let's begin. So this work would not have been possible without a tremendous amount of efforts put into by my graduate students, Chaemin, Suhyun, Jinwoo, Jungwoo, and Seongyeon. And I also thank the collaborators from Professor Hanjun Kim at Yonsei University and Jino Lee at Seoul National University. So in-memory databases or in-memory DBs process a given query by accessing the tables stored in the main memory, not disks. Storing the tables in the main memory can achieve much higher query processing throughput than storing the tables in the disks by replacing all the slow disk accesses with fast main memory accesses. Due to the significant performance benefits over the disk-based DBs, in-memory DBs are becoming more and more popular. Example in-memory DBs include MonadDB and DuckDB. Among many relational operators, the join operation combines columns from one or more tables into a new table, and thus serves as a key relational operation of the in-memory DBs. The join operation is not only important, but also incurs high execution latency, so in-memory DBs strive to optimize the performance of the join operation. Here is an example SQL query involving a join operation on two tables R and S. The query specifies a join predicate R.key equals S.key, and three columns to be merged R.key, R.name, and S.quantity. Executing this query results in a new table consisting of the three columns and the rows combined with the columns from the two tables, satisfying the join predicate. Since the join predicate specifies that R.key should be equal to S.key, only two rows are included in the resulting table. The join operation can be seen as a memory-intensive operation as it accesses multiple columns of one or more tables. As in-memory DBs store their tables in the main memory, the join operation on in-memory DBs is a memory-intensive operation incurring frequent main memory accesses. To achieve fast join executions, therefore, the underlying system architecture of an in-memory DB must provide high memory bandwidth. Providing higher memory bandwidth will allow the join operation to access more columns and rows in the same amount of time. Conventional systems employ dual inline memory modules or DIMMs to implement the main memory. However, as the join operation itself is performed by the CPU cores, the limited memory bandwidth between the CPU cores and the DIMMs becomes a key performance bottleneck. One may think that adding more channels and more DIMMs per channel would resolve the performance bottleneck. However, as in-memory DBs involve terabyte scale tables, performing a join on such terabyte scale tables incurs excessive numbers of main memory accesses, which far exceed what the memory bandwidth between the CPU cores and the DIMMs are capable of. Therefore, the memory wall, often referred to as the data movement bottleneck between the CPU cores and the main memory, has become a key performance bottleneck of the in-memory join operation. Among possible solutions, processing in memory, or PIM, is a promising solution to resolve the data movement bottleneck imposed on the in-memory join operations. PIM implements in-memory processors located inside the memory module and allows applications to offload their memory-intensive operations onto the in-memory processors. Executing memory-intensive operations on the in-memory processors can mitigate the memory wall, as the data do not need to be transferred between the CPU cores and the memory. In addition, the in-memory processors can exploit the high internal memory bandwidth of the DIMMs, which is much higher than the one between the CPU cores and the main memory. To demonstrate the potential benefits of PIM, we profiled the memory bandwidth of two systems having 4 DDR4 2400 channels. One of the systems is equipped with standard DIMMs, and the other is equipped with UPMEM DIMMs, currently the only publicly available PIM-enabled DIMMs made by UPMEM. We increased the number of DIMMs on the systems from 1 to 8 and compared their memory bandwidth. This graph shows the measured memory bandwidth on the two systems with varying DIMM counts. We can see that as we increase the number of DIMMs, PIM-enabled DIMMs achieve much higher memory bandwidth than standard DIMMs. The PIM-enabled DIMMs achieve 9.3 times higher memory bandwidth than the standard DIMMs when the DIMM count is 8. In addition, we can see that the memory bandwidth offered by the standard DIMMs saturates at low DIMM count. This is due to the limited bandwidth between the CPU cores and the DIMMs. On the other hand, PIM-enabled DIMMs achieve scalable memory bandwidth by exploiting their high internal memory bandwidth. The experimental results clearly demonstrate PIM's ability to achieve high and scalable memory bandwidth. The high and scalable memory bandwidth is exactly what in-memory joins demand to their underlying systems. Therefore, in this work, we focused on utilizing PIM to accelerate in-memory joins bottlenecked by the data movement between the CPU cores and the main memory. In fact, there exist some prior studies which seek to accelerate in-memory joins using PIM. However, we find that none of the prior studies are compatible with commercial PIM-enabled DIMMs, making it difficult for in-memory databases to employ the prior studies for accelerating in-memory joins by exploiting PIM. The table below summarizes the characteristics of the prior studies on PIM-assisted in-memory join acceleration. We identified two key limitations of the prior studies. First, the prior studies target 3D stacked memory, such as hybrid memory cube. However, the architectural characteristics of the 3D stacked memory greatly differs from those of PIM-enabled DIMMs, which I will elaborate in the later slides. As a result, the prior studies become incompatible with commercially available PIM-enabled DIMMs. Second, as real PIM-enabled 3D stacked memory is not available, the prior studies rely on cycle-level timing simulations to validate their findings and proposals. Unfortunately, the timing simulations are inherently error-prone due to hardware modeling errors. Motivated by the limitations of the prior studies on exploiting PIM to accelerate in-memory joins, we propose PiDRAM, a processing in DIMM join algorithm, which targets commercial PIM-enabled DIMMs and has been prototyped, evaluated, evaluated, and validated on a real system. In addition, unlike the prior studies, the artifacts of PIDRAM are publicly available through GitHub. Before going into the details of PIDRAM, let me first share the architectural characteristics of commercially available PIM-enabled themes, which PIDRAM builds on top of. The first architectural characteristic of the PIM-enabled themes is the per-memory bank in-memory processors. If you are familiar with the internal architecture of a theme, you would probably know that a theme employs a hierarchical architecture consisting of ranks, chips, and banks. The hierarchical architecture allows a theme to provide high memory bandwidth by serving a memory request using multiple banks. On top of the hierarchical theme architecture, commercial PIM-enabled themes associate an in-memory processor to each of the memory banks. The figure below shows the internal architecture of UPMEM themes, the commercially available PIM-enabled themes. UPMEM themes extend each bank of a theme by associating an in-theme processor and a working RAM with a memory bank. The in-theme processor executes a PIM kernel offloaded from the CPU cores and handles data transfer between the working RAM and the memory bank. Since the in-theme processor can access only the data stored in the working RAM, it needs to manage the working RAM by loading the input data of a PIM kernel to the working RAM from the memory bank. The second architectural characteristic of PIM-enabled themes is that they implement a shared nothing architecture. Recall that the themes associate an in-theme processor to each of the memory banks. Since an in-theme processor can only access the data stored in its working RAM and memory bank, to transfer data between in-theme processors, the host CPU must mediate all interbank data transfer due to the lack of native hardware support for fast interbank communication. To transfer a piece of data between the in-theme processors, the host CPU must collect the data from the source banks and then distribute the collected data to their destination banks. The third characteristic of PIM-enabled themes is byte interleaving. The byte interleaving is a common practice in standard themes as well, as it allows themes to achieve higher memory bandwidth by distributing sequential bytes of data to multiple banks. However, when it comes to transferring data between in-theme processors on PIM-enabled themes, the host CPU must not only collect and distribute the data, but also perform a transpose on the collected data before distributing the data to the destination banks. The transpose is necessary as the goal of an interbank data transfer is to preserve the order of the sequential bytes of data from the source memory bank as is on the destination memory bank. Based on the identified architectural characteristics of PIM-enabled themes, we set our design goals toward enabling fast in-memory joins on commercial PIM-enabled themes as follows. First, we should propose an in-memory join algorithm which is compatible with stock PIM-enabled themes such as UPMEM themes. This design goal addresses the limitations of the prior studies. They only target and support 3D stacked PIM architectures and rely on timing simulations to validate their findings. Second, to achieve fast in-memory join on an in-theme processor, we need to develop fast single in-theme processor join algorithms. This serves as our second design goal as, at the time of writing the paper, how to optimize the diverse types of in-memory joins on in-theme processors remained as an open research question. When developing single IDP join algorithms, we should consider the fact that each IDP can only access the data stored in its working RAM and memory bank. Third, we should scale the developed single IDP join algorithms to utilize all the available IDPs of PIM-enabled DIMMs. When it comes to scaling from a single IDP to multiple IDPs, interbank data transfer is necessary. Therefore, we should optimize the interbank data transfer bandwidth to minimize the impact of interbank communication. In addition, we also target to optimize the data transfer between the host CPU and the DIMMs by assuming that the input tables of a join is initially placed in the host memory rather than the PIM-enabled DIMMs. To this end, we present PIDRAM, a fast in-memory join algorithm which exploits PIM-enabled DIMMs. PIDRAM has been prototyped and evaluated on a real system equipped with UPMEM DIMMs, currently the only publicly available PIM-enabled DIMMs. I will first present an overview of PIDRAM, followed by its challenges and key ideas. PIDRAM tackles three key challenges which stem from the architectural characteristics of commodity PIM-enabled DIMMs. The first challenge is the limited compute capabilities of the in-DIMM processors. In particular, the IDPs offer limited computational throughput and lack native hardware support for complex arithmetic operations such as multiplication and division. PIDRAM resolves the challenge by designing and prototyping three types of IDP-optimized joins, namely hash join, sort-merge join, and nested loop join, all optimized to fully exploit the IDPs. The second challenge is the slow interbank communication involving host CPU resources. PIDRAM overcomes this challenge by proposing rotate and stream, a fast interbank communication mechanism which exploits the vector instructions and host CPU cache bypassing. The third challenge is the slow data transfer between the host CPU and the DIMMs. PIDRAM tackles the challenge by proposing unordered scatter and gather. It exploits the fact that the join operation itself does not impose any strict ordering on its input and output rows. The figure below illustrates an overall working model of PIDRAM. It starts by distributing the rows of the tables to all the IDPs with unordered scatter, followed by performing global partitioning on the IDPs, exchanging the rows between the IDPs with rotate and stream, performing single IDP joins, and lastly, collecting the result table on the host CPU with unordered gather. The first challenge is the limited capabilities of IDPs. First, the lack of native hardware support for complex arithmetic, including integer multiplication and division, leads to low performance. Our experimental results show that the XOR-based tabulation hash shows nearly 7 times higher hash throughput than the multiply-based murmur hash function. Second, the random accesses to the memory bank leads to significant bandwidth degradation. This results in 89% lower bandwidth compared to sequential accesses, while access to the working RAM only shows 20% degradation compared to the slow main memory accesses. This difference is due to the row activation of the DRAM banks, which internally activates its data at a larger granularity than the main memory access sizes. Based on the architectural characteristics of the IDPs, we built our first key idea, the optimized single IDP joins. In case of hash join, we optimize partitioned hash join by enforcing sequential memory accesses to the memory bank, filtering random accesses to the working RAM, and exploiting the XOR-based tabulation hash function to maximize hash throughput. Single IDP hash join starts with filtering the random accesses of the partitioning pace when storing the partitions into the partitioning buckets. It also filters the random hash table lookups of the hash table build and probe pages and only sequentially store the output into the main memory bank. In this way, single IDP hash join achieves high join performance by considering the architectural characteristics of IDPs. We also optimize sort merge join and nested loop join with similar key ideas. Sort merge joins have random memory access patterns at the sorting pace. So we apply range partitioning on the SRAM and sort each partition inside the IDP. In case of nested loop joins, they have an inherent streaming memory access behavior. So we stream each table R and S buffers to the working RAM. The second challenge of PID join is the slow interbank communication, which arises from two key limitations. First, interbank communication relies on the host CPU due to the shared nothing architecture. Second, rows from the banks require byte-wise transposes to adjust the data layouts between the IDPs and the host CPU due to the memory interleaving. Accordingly, the conventional interbank auto communication process involves 5 steps. First, the rows stored in the source bank are loaded and transposed to the host memory. This is performed with the standard UPMEM SDK API. Then, the host CPU performs shuffling of the rows for auto communication. This incurs high memory random access. The host CPU then performs another transpose in order to send back the tuples to the PIM-enabled DIMMs. This is also performed by the UPMEM SDK API. And finally, the rows get stored to their destination banks. These extensive steps contribute to the low interbank communication bandwidth with high computational overheads and random memory accesses when performing all-to-all shuffle. To overcome this challenge, we implement two key ideas to optimize low interbank auto communication. First, we alleviate the host CPU's burden by cooperating shuffling with the IDPs. Second, we exploit the fact that both the source and destination banks employ the identical data layout. Based on the two key ideas, we propose rotate and stream, our fast interbank auto communication method. First, the IDPs rotate the storing order of the partitions, matching with their chip numbers in the partitioning pace. And then the host CPU performs a single AVX byte rotation for shuffling without adjustment of the data layouts. In this way, rotate and stream enables fast interbank auto communication. It works with only a single byte rotation and streaming tuples using the vector registers without accessing the host memory. Our third challenge is the slow host PIM data transfer. Like GPUs, it must transfer input and output rows between the host and PIM memories. Conventionally, the data transfer is performed at the granularity of a bank, aiming to store a sequence of bytes in a single bank. This results in per-bank region splitting being performed in the host memory. Conventional host PIM data transfer starts with collecting tuples from different memory regions to construct the data blocks, and the data blocks are loaded to the vector register. Then the host CPU performs transpose and stores the tuples into the destination banks to adjust the data layout. This results in slow random memory accesses to collect data from the different regions, finally lowering the host PIM data transfer bandwidth. To address this problem, our third key idea is unordered scatter and gather. It exploits the fact that joins do not impose strict ordering on the input and output rows. So we remove region splitting on the host memory and perform host PIM data transfer in a rank-wise approach rather than a bank-wise approach. Rather than collecting data from different regions, the data blocks are directly loaded into the vector registers, and the host CPU directly transposes and stores the rows to their destination banks. In this way, unordered scatter and gather enable fast host PIM data transfer. Similar to the rotate and stream, it works with sequential memory accesses with a large access granularity and a single vector instruction. For more details of our key ideas, please refer to our paper. From now on, I will share some key experimental results of pit join, followed by the conclusion of this talk. To evaluate the performance of pit join, we prepared two system configurations. The baseline system consists of an Intel Xeon Gold CPU and 5 channels equipped with standard DIMMs. The PIM system includes 4 channels with PIM-enabled DIMMs and 1 channel with standard DIMMs. The picture on the right shows our PIM system equipped with 8 UPMEM DIMMs. As benchmarks, we used a combination of synthetic benchmarks and 4 TPC-H queries. The synthetic benchmarks perform two-way joins with 32-bit integer join keys and row IDs. We varied the R to S ratio and adjusted the size of the relation S and considered both uniform and skewed row distributions. The 4 TPC-H queries involve a single two-way join. We first compared the performance of pit join against recent CPU-based join algorithms. As the baseline nested loop, sort merge, and hash join algorithms, we chose MonadDB, MPass, and PRHO respectively. The figures show how fast the join algorithms perform a two-way join with 512 million row R and S having uniform value distributions. As can be seen, pit join completes executing a two-way join up to 2.43 times faster than PRHO, a histogram-based CPU-optimized in-memory parallel radix join algorithm. Overall, pit join achieves 1.92 times faster hash join, 4.79 times faster sort merge joins, and 83.22 times faster nested loop joins over the baseline CPU-based in-memory join algorithms. The large speedups of pit join are possible thanks to the high internal memory bandwidth of PIM-enabled DIMMs and the optimized interbank and host PIM data transfer mechanisms. To demonstrate the effectiveness of our rotate and stream and unordered scatter and gather, we compared pit join's interbank and host PIM data transfer bandwidths against those of conventional mechanisms. The figure on the left shows the interbank communication bandwidth, and the figure on the right shows the host PIM data transfer bandwidth. The results clearly demonstrate the high effectiveness of pit join's interbank and host PIM communication optimizations, allowing pit join to greatly outperform the existing in-memory join algorithms. Pit join's rotate and stream achieves up to 6.42 times faster interbank data transfer, and unordered scatter gather achieves 3.91 times faster host PIM data transfer. We then examine how much the key ideas of pit join contribute to the overall performance improvements. The figure shows how the join execution latency changes as we incrementally apply pit join's key ideas on top of PRHO. Interestingly, Offloading the join operation onto the in-DIMM processors alone incurs higher execution latency compared to the baseline PRHO. However, as we apply PIDJoin's communication optimizations, PIDJoin achieves 3.03 times faster join execution over PRHO. We find this ablation study especially interesting as it emphasizes the importance of interbank and host PIM communication optimizations. We now examine the scalability of PIDJoin by varying the R2S ratio and by examining how robust PIDJoin is to skewed tables. Uneven and skewed tables are common in real-world scenarios, so it is important for PIDJoin to achieve high skewness against the skewed tables. The figure on the left shows the scalability results with uniform tables, and the figure on the right shows the results when setting the skewness of table S with a ZBAP factor of 0.5. The results show that PIDJoin achieves high scalability with more PIM-enabled themes, even with the uneven and skewed records. Such high scalability is expected as PIDJoin employs global partitioning to balance the load between the in-DIMM processors. This slide shows a sensitivity study of PIDJoin. When performing hash joins, choosing which hash collision handling mechanism to use is an important design choice. By default, PIDJoin employs linear probing, or LP, which probes the next entry in the hash table upon a hash collision. For the sensitivity study, we implemented not only LP, but also quadratic probing and double hashing, both of which are widely used in many hash join algorithms. The results show that LP, PIDJoin's default hash collision handling mechanism, performs the best despite incurring higher hash collision rates. This is due to the fact that the other two hash collision handling mechanisms involve multiplication and modulo operations, the complex arithmetic operations which are not natively supported by the in-DIMM processors. This slide shows the potential speedups of PIDJoin with the 4 realistic TPCH queries. To examine the potential speedups, we profiled the join execution latency of a query on MonetDB, a prominent CPU-based in-memory database, on the standard system, and replaced the profiled join execution latency with that of PIDJoin. The results show that applying PIDJoin can achieve up to 3.41 times faster join executions and up to 26% faster TPCH query executions. The results are quite promising in that accelerating end-to-end query executions is an important design goal of any in-memory databases. So, to summarize my talk, PIM is a promising solution to many application domains, and in-memory databases can be a great target of PIM acceleration due to their memory-intensive natures. Motivated by the potential benefits of PIM, we conducted the first study on accelerating joins, a key relational operator of in-memory databases using real PIM-enabled themes. Our efforts have led us to design and propose PIDJoin, a fast processing in-DIMM join algorithm, which has been prototyped, evaluated, and validated on UPMEM DIMMs, the first real commodity PIM-enabled DIMMs. So thank you for listening, and please refer to our paper and artifacts for more details. I will be happy to answer any questions you have.
Yeah, thank you very much. Also, very interesting talk. Was great, and also perfect timing. I don't see any questions in the YouTube chat, but I would like to ask you several questions. I think, well, the whole work is really interesting, but I think that where you really, set like a key novelty with respect or prior works and with the UPMEM PIM architecture is in these rotate and stream approach and also the unordered scatter gather. And I think the large speed up that is coming from these two, you have, I don't remember the slide number, but you have a slide where you clearly show that thanks to these two, the AxDIMM system is competitive for the joint operation. Without these two optimizations, it is not even possible to outperform the CPU, right? So my question is, do you think that there are also other applications that can benefit from these two techniques, or maybe not in the exact same shape, but generalizing them in some way?
Sure. So that's a great question, Juan. So although we designed rotate and stream and unordered scatter gather specifically for the join operation, what we later realized is that the rotate and stream operation itself actually corresponds to the auto shuffle operation, which are typically common in MapReduce applications, as an example. And also the unordered scatter and unordered gather, they are essentially scatter and gather operations. So to answer your question, I believe that there can be many potential PIM applications which can also benefit from rotate and stream and unordered scatter gather, especially if they involve frequent shuffling and also scatter and gather operation. And in particular, the auto shuffling, the rotate and stream can help if the shuffle happens between the processing in DIMM processors. And also, especially the unordered scatter gather can benefit if we want to distribute and collect data from and to the processing in the memory banks. But one thing I want to clarify is that the intention of this slide is not to show that whatever we do, we cannot make the join operation faster than the CPU counterparts. This actually stems from the fact that we assume that all the tables are initially stored in the host memory, but as you can see from recent papers presented in DAMON 2023 workshops, if we can somehow place the tables and rows in the PIM-enabled DIMMs initially instead of the host memory, then of course there is an abundant room of performance improvements the PIM-enabled DIMMs can further achieve. So to clarify, this is just a case where all the input data are initially stored in the host memory. So I wish to clarify that before concluding my answer to your question.
Mm-hmm. Yeah, that makes sense. Thank you very much for the answer. And actually, what you just said connects to the second question that I wanted to ask you is, because it's something that, a question that I usually receive, and also some criticism with respect to the AxDIMM PIM system is that can be seen as an external accelerator rather than processing in the standard main memory, right? Or in the main memory. So where do you think that, I mean, yeah, I guess that it connects to the end of your answer, right? You could save significant amount of time as well if the PIM system was in the main memory itself, right? Instead of being in a separate separate channels. But could that only save gather and scatter times here, or you think that could also be beneficial for the inter-IDP communication?
So that's also a great question. So as you mentioned, the UPMEM DIMMs in particular, which are the first commercially available PIM-enabled DIMMs, they do have several challenges when it comes to optimizing applications to fully exploit their architectural characteristics. And one of them is, as you mentioned, they are not really fully integrated into the main memory of a system, right? Because they have to be attached to separate channels and so on. But I think there can be, even with the current UPMEM DIMMs, the UPMEM DIMMs themselves can actually still serve as part of the main memory because they somehow they perform mmap on the memory banks of the unmem DIMMs to the address space of the host operating system. So that's actually one of the reasons why we could develop rotate and stream and order scatter gather as well, because the data stored in the unmem DIMMs were actually exposed to the host CPUs through the mmap operation. But the thing is, when we were trying to achieve maximum bandwidth or interbank communication and unordered scatter and gather, the key limitation of the current unmem DIMM implementation was that the data stored in the memory banks of the unmem DIMMs are not really sequentially placed in the host memory address space. They are somehow separate from each other. I guess the block size was something like 256 kilobytes or so on. So if we can resolve that discrepancy between the actual standard DIMM's sequential memory address space being exposed to the host CPUs, then I believe we can not only accelerate both interbank and scatter and gather operations between the host memory and the unmem DIMMs, but also make much wider range of applications to easily adapt or easily exploit the unmem DIMMs that are already optimized for the memory space where all the memory contents are linearly placed in the address space.
Mm-hmm. I see. Yeah, that makes perfect sense. Okay, yeah, thank you very much again for the great talk and the answers to our questions. Yeah, no, it's great to have you here and hopefully we will be in touch and collaborating in the future.
Sure. See you soon.
Thank you very much, Johnson.
Thank you.
Okay. Yeah, thank you everyone for attending this tutorial on real processing in memory systems. Now we have another invited speaker. We are going to have Dr. Abu Sebastian. Abu, if you're there, could you please share your slides? Yeah, thank you, Abu. In the meantime, let me very briefly introduce you. Dr. Abu Sebastian is one technical leader of IBM's research efforts towards the next generation AI hardware, and he manages the in-memory computing group at IBM Research Zurich. He is the author of over 200 publications in peer-reviewed journals and conferences, and he has more than 90 US patents. In 2015, he was awarded with an European Research Council Consolidator Grant, and in 2020, he was awarded with the ERC Proof of Concept Grant. He was an IBM Master Inventor and was named Principal and Distinguished Research Staff Member in 2018 and 2020, respectively. In 2019, he received the Ovchinsky Lectureship Award for his contributions to phase change materials for cognitive computing. And in 2023, he was conferred the title of Visiting Professor in Materials by the University of Oxford. He is a distinguished lecturer and fellow of the IEEE. Abu, if you're ready, feel free to start. I will also would like to invite everyone attending the talk to ask questions in Zoom, either in the chat or directly or in the YouTube chat as well. The stage is yours, Abu.
Thank you, Juan, for the very kind introduction, and I'm extremely glad to be part of this effort. I mean, it's a very nice tutorial so far. Right, so what I will talk about is, the processing using memory based on memoristic devices. I mean, many of the things have been covered with respect to PIM, and here I will try to cover this particular segment later to that. Right, so I have essentially three parts to my talk. The first part is basically introduction to processing using memory or in-memory computing in the context of deep learning acceleration. So that's the first part. The second part, I will have a detailed introduction to the IBM Hermes project chip. It's one of our latest chips. And in the last part, I would like to give an outlook into the future, like, what next, right? I mean, what are the research directions towards a next generation AMC chips? Right. So just to recap, I think already I've heard a lot about processing in memory. And as was explained multiple times, there are two flavors of processing in memory. Right? The first flavor is processing near memory or near memory computing, where you read back the memory contents and then you process it in close proximity to the memory array, often in the same memory chip. Then we have the processing using memory, where we perform the processing in the memory array itself. In this case, the key distinction for me is that we are not individually reading out each memory cell content. So we are kind of collectively processing in memory, and reading out the individual memory content is not part of the bargain, right? So as long as you perform the computational task, that is good enough. It's not essential that you have to be able to decipher each of the memory contents with high fidelity. So for me, that is kind of the key distinction between the two approaches. And when you talk about, and in my talk, I'll be talking about processing using memory, we also, it's typically also referred to as in-memory computing in many domains, especially in the device world. And how do we achieve this processing using memory is clearly by exploiting the physical attributes of the memory devices, the way in which they are organized in an array level, the peripheral circuitry, and maybe even some of the control logic that you have around it. So this is how you would perform processing using memory. And interestingly enough, processing using memory can be achieved using a range of memory devices, charge-based memory devices like SRAM, DRAM, and flash, as well as resistance-based memory devices, the so-called memristive devices, such as metal oxide-based resistive RAM, phase change memory, magnetoresistive RAM, and so on and so forth. So, I mean, in 2020, we had written a review article which appeared on the cover of Nature Nanotechnology, where we cover a wide range of processing using memory techniques. And I would strongly encourage those of you interested to take a look at it and to see how these various types of memory devices are being used for very specific tasks, ranging all the way from in-memory logical operations all the way to arithmetic operations and whatnot. One of the most promising applications for processing using memory is deep learning acceleration, right? As many of you know, deep learning has essentially revolutionized AI in recent years. And we have this very powerful tool that helps us learn representations from unstructured data, like images and videos and even the web data. And as you very well know, almost every day we have a new DNN model that is being proposed, or a variant of a DNN model. But fortunately, there is a recent consolidation of DNN models around convolutional neural networks and long-term, short-term, short-term memory networks and transformers. And that's kind of interesting. And the other thing is that to kind of see is that CNNs are kind of being primarily used for computer vision, whereas transformers and LSTMs have become the dominant neural network models when it comes to natural language processing, time series analysis, etc. And more recently, that transformers in particular are becoming, even more dominant in a range of tasks, right? I mean, transformers are also getting into some of the other domains, typically in the realm of CNNs, for example. One of the issues with deep learning, right from the very beginning, has been the hardware problem, right? As you very well know, deep learning, including backpropagation, was all settled as early as in the 1980s, algorithmically. But then, of course, we didn't have the right hardware for that, right? So that's what led to this so-called lost decades, right? So we essentially had, several decades where we had the algorithms in our hand, but we didn't have the right hardware. And eventually, the hardware maturity had to reach a certain point that it became successful in the 2010s. And even with more specialized hardware, like the GPUs, of course, it had a significant impact on how DNNs are implemented, and it kind of revolutionized, it kind of paved the way for this recent AI revolution. But even then, for example, you have this very interesting story here whereby Google had this project to find cats in YouTube videos, and for that they used 16,000 CPUs, and in a couple of years you could do the same task with 48 GPUs, right? It kind of shows the impact of GPUs in the whole in this whole scenario. But even with this kind of the arrival of specialized hardware, like GPUs for deep learning, as you can see from this well-known game, right, between AlphaGo and Lee Sedol, that there was still a huge disparity in terms of energy consumption, right? So you had to use thousands of GPUs and over or up to 200 thousands of CPUs and over up to 200 GPUs to match this human performance here. So clearly, deep learning is still facing this perennial hardware challenge to some extent. So where do we stand now? So we are in this age of custom digital accelerators, right? We all know that there's this explosive growth in the number of custom digital accelerators for deep neural networks, both on-chip as well as discrete accelerators. In fact, here is an example. We have a AI accelerator on the IBM's Z Tellum processor here. I don't know if many of you know about it. And more recently, IBM Research has announced an IBM Research Artificial Intelligence Unit, which kind of packs several of these AI cores. And this is an active area of research in IBM. In fact, one of the pioneering works in this domain, in the towards custom digital accelerators, came out in 2015 from IBM team, our colleagues in Yorktown Heights, where we showed this key conceptual leap, which was basically the observation that you can perform deep learning with with much less precision, right? So that is one of the key conceptual steps here. But in addition to that, of course, there are other interesting ideas being explored, like better data locality, compound instructions, better use of sparsity and whatnot, right? So these are all the kind of tricks that people are playing in the domain of custom digital accelerators for deep neural networks. But despite all these developments, we are still struggling to dramatically improve the energy efficiency associated with the deep neural network deployment. So here is this list of the latest deep neural network accelerators, along with GPUs that span the entire spectrum, all the way from edge device accelerators to data center systems. And in all these cases, what you see is that it's extremely challenging to break through this 100 femtojoule per operation barrier, right? Especially in scenarios where you want your peak performance to also be competitive, right? It's going to be a huge challenge. It remains a huge challenge despite all these advances that I talked about earlier. And we all know the reason for that. The primary reason for that is data movement, right? So clearly you could do all you can with all the compound instructions and whatnot. But the truth of the matter is, as long as we have a physically separated synaptic weight storage and processing, we'll always have the difficulty or the need to move around data from the synaptic weight location, wherever that is located, to the processing elements. So there was this very nice study done by Professor Boris Merman. He showed that assuming that the processing elements themselves consume almost no energy, then just the fact that you need to feed them data, or basically the synaptic weights from the SRAM to the PE, and then if the SRAM capacity is not sufficient, then you need to bring in from DRAM to the SRAM as well, right? So all that will eventually plateau your system level performance to something like this hundreds of femtojoule per operation that I again talked about, that we observe from empirical evidence. And this kind of disparity becomes even more stark when it comes to the more advanced CMOS technology nodes. There is very nice data from Bill Daly and co, where they show that performing 32-bit add operations in state-of-the-art processing technology takes only 20 femtojoule and 150 picoseconds. But just moving the two 32-bit words to feed this operation over a distance of 1 millimeter will take 1.9 picojoules and 400 picoseconds. And note that if you now fetch these two 32-bit words from main memory, then you're talking about nanojoules of energy, right? So there's this huge disparity between processing and the data movement. And this is not getting any better because this problem is going to be aggravated by the dramatically increasing model sizes, right? So if you look at the models that have been proposed over the years, you can see how the model capacity is increasing, right? There's almost an exponential increase in the model sizes. Along with this curve, we have also plotted the memory capacity of accelerators, and this is, by the way, the DRAM capacity, the accelerated memory. And you can see that even that is struggling to catch up with the model size, right? I mean, it's almost impossible to keep track of it. And now if you look at the on-chip memory, that is orders of magnitude lower than the model size already. Like if you look at NVIDIA's A100 for an 800 millimeter square chip, it has only 40 megabytes of on-chip memory. So clearly, we are really struggling, and this struggle is going to be even worse in the coming years. So as you all know, the most prominent arithmetic operation when it comes to deep neural networks is matrix vector multiply operations, right? So every neural network layer is essentially performing an MVM operation. And hence, this is precisely the operation that we would like to implement in the most efficient manner using memory. And that is also why that's also where this in-memory computing or processing using memory comes into play. So how we go about in-memory computing? So before I get into analog in-memory computing, I just want to briefly mention digital in-memory computing, because this is also very much, I mean, there's no reason why in-memory computing has to be analog, right? It's just kind of a little bit of a misnomer. It can be digital in-memory computing too. The only litmus test is that you should be performing computations with the memory in a stationary manner. That means you're not moving content from the memory. So for example, if you want to perform a matrix vector multiply operation, then essentially you are supposed to implement these operations here, right? So you have y is equal to wx, you store all the w in the memory array, and then x is the input, and then you want to perform the, this y is equal to wx matrix vector multiply operation. So what you could do is you can actually redesign an SRAM array in such a way as shown here, right? So you could have all the memory, the synaptic weights stored in SRAM as shown here. Your x's are coming here, and then you perform the individual scalar multiply operations by reading it in a slightly different manner or whatever, right? With minor modifications here. And once you have the result of the multiply operation, then you can have a distributed adder tree, which will take the results of the computation, and then it will spit out the y value right here. So this is very much in-memory computing, and this is typically what you would call digital in-memory computing, right? So we are not exploiting any mixed signal approaches here. There's no analog really coming into play. And this is also the most mature form of in-memory computing. It's all based on conventional CMOS. There are no exotic materials. Everything is pretty clean here. And there are also some startups which are doing digital in-memory computing in a very aggressive manner. But one of the challenges here would be that the on-chip weight capacity in this approach would be limited by the SRAM and the adder area, right? So that is kind of where the limitation comes. But having said that, for many of the edge applications, this is a very interesting approach nevertheless. So we could go further. We can say, okay, you know what, let's try to get rid of the adder tree by now bringing in some analog. So that's where analog in-memory computing comes in, right? So here, your data or your compute element, your memory element is still SRAM. In this case, typically we use SRAM with a switch capacitor. So this is what acts as the compute element. Here, what you will do is, if you want to perform the y is equal to wx operation, then you would do it in like 3 steps. First of all the w's will be stored in the SRAM memory cells, right? And you don't read them out. And then depending on the x values, you will chart the switch capacitor here. That's the first step. And then based on the value of the W11, you will either retain the charge there or you'll discharge the charge, right? And then finally, what you do is you will turn on all these switches so that you'll have a capacitive charge sharing along the wires, which will do the accumulation operation for you. So this is where analog comes into play, right? So you have your data stored in SRAM, but your computation is mixed signal, and then you are able to obtain the Y1, Y2, Ym in a mixed signal manner. This is a very interesting approach, and there have been very, very interesting publications, especially from the Sprinson group and Naveen Verma's group here. And they have also shown some very impressive energy per operation numbers using this, analog in memory computing or a mixed signal in memory computing approach. But here again, we have the challenge of on-chip weight capacity limited by the SRAM area, right? So SRAM area will eventually limit how much on-chip capacity you can have on a realistic chip size. But again, a very interesting approach. And here again, there is quite some commercial activity going on. So that's where non-volatile memory comes in, and in particular memory state devices. And how will you now do the exact same Y is equal to WX operation using memory state devices? So here we will organize the memory state device in a crossbar array, which is shown here. And then each of the conductances of these memory devices, they will be now programmed to be proportional to the W values that you want to store, right? So that's what you do here. And then your V1 value, which is a voltage value, will be now proportional to the input. Now if you now simultaneously bias this crossbar array with this V1, V2, and Vn, then we are essentially performing a matrix vector multiply operation. Why? Because we'll be doing, because of Ohm's law, you'll get the multiplication G11 times V1. And then because of the Kirchhoff's circuit law, so the current summation law, you would be able to get your accumulation, right? And to get your I1, which will be now proportional to the Y1 that you're looking for. So different physics, but still analog, and you're able to perform your matrix vector multiply operations by exploiting the physics, essentially, right? That's what happens here. And if you look at the energy per operation, it's not too far away from what you could get from the SRAM-based in-memory computing approach that I mentioned earlier. It could even be slightly less, to be frank. But unlike SRAM, the big advantage is that there is a potential for ultra-high weight density and capacity, right? So you can create these crossbars in a much more dense manner, almost independent of the technology node that you're on. And moreover, unlike SRAM, this is non-volatile, which means that it is highly amenable to power gating, right? Which would come in very handy in certain scenarios. So what I showed earlier is kind of the easiest way to understand how we perform matrix vector multiply operations using memory state crossbar arrays. But in reality, no one does it that way, right? So in reality, what you do is you have a crossbar array, which is typically a 1T, 1R. And that means that you have a memory device and a transistor. And then instead of modulating the voltage bias signal, which is not so nice for many reasons. For one, these devices are typically nonlinear, right? So you don't want to get into a scenario where your voltages are changing and then your conductance is changing accordingly. Moreover, these DACs can be very costly in the peripheral circuitry. So what you typically do is you keep a constant read voltage, but then you translate your input into a time signal, right? So the duration of the pulse, and then you integrate the current over a certain fixed time. And then, as you can see from these equations, you are still doing your MVM operations, Gij in this case times Tj, but the only thing is that you're now looking at the charge and not the current, right? You're looking at the integrated current. So this is the right way to do analog in memory computing using memory state devices. And in this mode of operation, it is not at all dissimilar to how this would be done with a flash memory. Assume that you have a crossbar array with flash memory devices, then this is pretty much what you would also do, right? So in that sense, analog in memory computing with memory devices and that with flash memory devices are very similar when it comes to the way in which they are implemented. So that was all about the tile, but how would, just the crossbar array, but the real analog in-memory computing tile or a core has many more components to it, right? So this is your crossbar array. but you would need some kind of an input block. You would need an output block. You need some programming circuitry, some control logic, the I/O interface and whatnot. And the input block is mostly the digital to analog converters, which I say normally you don't use. Instead, you typically have the digital to time converters, the one that modulates the width of the pulse. The output block comprises of analog to digital converters and some digital compute units which are required to process the post-processed analog or ADC output, and some output buffers, right? So these is what you call the periphery of this compute core. Now, how will you do deep learning inference with analog and memory computing? Let's assume that you have a very simple neural network looking at the picture of this cow and declaring it's a cow. Then all you do is you take each of these layers, you map them into a in-memory compute core. So the pixels from the cow, you translate them into the right signals, then you feed into the first crossbar array, you perform the corresponding MBM operations, take the output of it, feed into the next one, and that goes into the next one, so forth, right? As you can imagine, since all the weights are stationary here, it has a potential for this very good latency and energy per inference. So you have a fully weight stationary kind of implementation here, very amenable to spatial pipelining and whatnot. So why is deep learning with AMC considered neuromorphic? Again, many circles, this kind of computing is referred to as neuromorphic, and there are very good reasons to it, right? So all of us know that historically, deep neural networks have this strong link to computational neuroscience. In fact, much of deep learning came out of some of the initial attempts to getting these very simple abstract models of how neurons and synapses work. But besides algorithmic connection, the physical implementation of these neural networks were always very different, right? They were all implemented on conventional computing systems where we had a physical separation between synaptic weights and processing units, and this was not all the way things were implemented in the biological neural networks. But now with the approach, the analog in-memory computing approach, clearly we have physically stationary neurons and synapses, and we have less precise analog computation. Both of them are hallmarks of how biological neural networks compute, and that is why in some circles, analog in-memory computing with non-volatile memory is kind of used in conjunction with neuromorphic computing. Okay, so now I want to talk a bit more about, go a bit detail into the IBM Hermes project chip. So recently, IBM published two analog in-memory computing-based inference chip prototypes. Both of them are fabricated in 40-nanometer CMOS technology node, and they have embedded phase change memory in the backend. It's monolithically integrated, right? So these are the two chips here. They are essentially having two different architectures. So the first chip, which I'll talk about in more detail in today's tutorial, is a Hermes project chip, and here it has 64 tiles with 256 by 256 crossbar arrays, and each of these arrays have the ADCs which are integrated onto them, along with some digital processing units. It also has some additional digital processing unit. I'll talk to it a bit later. And it also has a digital communication fabric. Whereas the second one, it's a more exploratory one where we have 34 tiles with 512 by 512 crossbar arrays. Here the ADCs are not integrated per tile, so it's almost a full analog chip. And the communication is also performed in the analog domain, right? Here uses 2D routing mesh to transmit data in duration formats. So I would strongly encourage you to look at this paper and read more about it. But in the rest of the tutorial, I'll be talking about the chip just shown here. So the IBM Hermes project chip, if you look at the architecture overall, it has 64 cores. As I said, it has 256 by 256 crossbar arrays, so unit cells, synaptic unit cells, and associated peripheral circuitry. So let's zoom in into that. And if you look at each of these unit cells, that comprises of 4 phase change memory devices. That means it has a total of 16 million phase change memory devices. It also has, as I said, some on-chip, local processing as well as some global processing units here and a communication fabric. And the PCM devices themselves are integrated in the backend of a 40-nanometer CMOS technology. So the key compute element is phase change memory. I would argue it is the most advanced persistive memory technology out there. So it is based on the property of certain compounds of germanium, tellurium, and antimony, such that in the amorphous state, in the disordered atomic state, they have a very high resistivity. And in the ordered crystalline state, they have a very low resistivity. So if you take this material and if you now sandwich them to metal electrodes, then depending on the phase configuration, you'll have very different resistance values. So if you're in the fully crystalline state, you have a low resistance. If you're in the amorphous state blocking the bottom electrode, then you have a high resistance. And the nice thing is that you can apply electrical signals and induce Joule heating and switch them back and forth between the low resistance state and the high resistance state. And once you are in these phase configurations, it's non-volatile, right? And it doesn't, it doesn't just slice at low temperatures, at room temperature, and maybe even up to 85 degrees or so. And then you can now decipher the phase configuration by reading with a low bias voltage. So the low field electrical resistance will kind of help you decipher in which phase configuration you are. But that's not just it. I mean, you can even have a continuum of conductance values in these devices. So in fact, what you could do is you can either melt quench larger and larger volumes of these amorphous regions, or you can start from a large amorphous region as shown here. Then you can progressively crystallize and get smaller and smaller amorphous regions. And in both cases, you will get a continuum of resistance values. So this is how when you create large and large amorphous regions, and this is when you do the reverse thing, right? You start from the reset state and then you crystallize. So this analog storage capability is quite nice and very well understood in phase change memory. That is also the reason why I would say it's the most advanced resistive memory technology. The physics is pretty well laid out. So if you now look at the memory devices which we have in the Hermes project chip, they also have this programming curve, as we call it, right? The conductance versus the programming current. And these are cross-sectional TM images of these devices, which show how the phase configuration evolves depending on the programming signals that you apply. The nice thing is that you could use a program and verify approach to go and achieve a target conductance value. You can program these devices to a certain arbitrary, I would say, conductance value between the set and the reset conductance. So what is program and verify? You basically go and program the device to reach a certain conductance value. You compare it against a target conductance. You look at what the error is, and based on that, you find out your next programming pulse. And that manner, you can progressively achieve the target conductance value. But unfortunately, when you try to program them, you'll always have a distribution. So you won't be able to go and say, let me get 6.7 microsiemen, right? I mean, you could of course reach it when you program it, but soon after that, it will spread out to give you a distribution of conductance values. And that's why we say it has a non-ideal analog storage. I mean, it's an analog storage device, but with some non-idealities thrown in there. So why do we have this non-idealities? I won't go into the details of it. It's too much device physics, but there are a lot of reasons why we have this, right? So for once, we have something called conductance drift. It comes from structural relaxation of these atoms. These atoms are not so happy to be in that, in that disordered state. So they keep trying to move around and try to find energetically more stable states. There is some amount of read noise, which is there. There's a lot of temperature dependence. There's also something called bipolar asymmetry. All these physical attributes, they all contribute to this non-ideal analog storage. And if someone is more interested in these aspects, they can look up these papers from our group. Now coming back to the synaptic unit cell, right? So as I said, phase change memory device is a central element of this whole thing, but a synaptic unit cell has 4 devices. So we have a differential configuration to facilitate storage of bipolar weights. So clearly there is no negative conductance in phase change memory. So we need to organize them in a differential configuration to be able to map negative numbers. And we also have a provision to use up to 2 devices to encode the synaptic weights per polarity. This is mostly for accuracy reasons. So, in theory, you could also encode it on 1 device, but if you want more precision, then you encode it on 2 devices. And the devices in the conductance pair, they are all weighted with equal significance. So you could, it's almost like averaging that it happens when you encode on multiple devices. So how will we go about mapping synaptic weights? Assume that we have a target weight between -1 and 1. This is what you get after training or whatever. Then you translate that into a corresponding target conductance value. Then you use program and verify, and you will map that target conductance value onto a synaptic unit cell, right? Onto the 2 or 4 devices that we have, you program onto that. And that is your G of T0 at the time of programming. Unfortunately, there'll be some programming noise which will get added on as a part of the programming, the one I talked about earlier. So that will be your true conductance value. Then that would, but then there's another catch to it, because you may not be performing your inference operation soon after programming, right? Because it's non-volatile. You could even do your inference after a month or a year, but unfortunately, these conductance values, they won't be stationary. There'll be some amount of drift happening, and there'll be some read noise which gets added onto that, right, at the time of inference. So here is just a look at the programming noise. I mean, one thing to point out is that, as I said before, if you use two devices from Polarity, then you can actually have much less programming noise as when you use one device. But again, that's again consistent with what you would expect. When you look at the child periphery of the project chip, it has pretty much all the components that I mentioned earlier. So you have the PCM crossbar array, then you have some DAC for programming. These are some programming units. Then there is the pulse width modulation scheme right here for the inputs. It's just reversed now, so just don't get confused by that. Then you have the ADCs, and then you have the LDPU. Then you have some other additional components here. So you see that many of the components that I talked about earlier, they all appear in this project chip. One of the key innovations we had was very compact current controlled oscillator-based ADCs. So this is the one which allowed us to have 256 ADCs operating in parallel, right? Because they are extremely tiny. They essentially convert the current directly to oscillations, and then you count them in a digital domain. That way you avoid this kind of area expensive current to voltage conversion, right? And this is a very interesting innovation, and you can read more about it in this paper. And this is what kind of allowed us to do all these operations in parallel for the first time. So once these synaptic weights are now programmed into one of the cores, then you can perform an MVM operation. So the input vectors, in this case, 256 dimensional vectors, each of 8-bit resolution, they come in, and then your synaptic weights are preloaded, right? And they remain stationary. And then you will perform an MVM operation in this analog manner. And then your ADCs will convert them, and then we'll do some post-processing on the LDPU, and they get you 256 dimensional output vectors of 8-bit resolution. So it's an 8-bit input, 8-bit output core with some analog compute in the middle, right? So it's a digital input, digital output system with analog computation. Each MVM operation takes either 128 nanoseconds or 512 nanoseconds, and then this is kind of a example of 248 such MVM operations, right? When we do a careful analysis, you see that the compute precision is something between 3 and 4 bits, again depending on whether you encode in 2 bits, two devices or one device, and so on. So that's kind of what we have. Now, clearly, this is not floating point precision, right? So which means that we have to do some custom training to get ISO accuracy and deep learning inference. So that's what we have here. So for that, what we do is we have a additive noise training approach to deal with this low precision MVM operations. And the key idea here is to inject noise to synaptic weights in proportion to synaptic weight noise during the forward passive training. So you kind of make train in such a way that you are used to being in this noisy, when you're used to having synaptic weight noise. In fact, recently we showed that many large-scale deep neural networks can be successfully retrained to show ISO accuracy with this kind of noisy analog computing. And that's, I think, again, you can look it up in this paper here. And more importantly, we also have open sourced this library, the hardware kit, which has all kind of device models, and soon we will have some real hardware as well. And this is a great venue for people to contribute to the effort, and also to play with the various algorithms and to develop algorithms to kind of advance this field. So I would strongly encourage you to take a look at that. So once we do the hardware-aware training, then we can map networks. So here we have a image classification network mapped onto the project chip. So it's a REST at 9 CNN, with so many parameters. All the convolutional layers are implemented with fully on-chip analog and digital computations. And the key thing to point out here is the on-chip accuracy. So we get an accuracy of 92.81%, which is by far better than anything that has been shown in with AIMC using memory devices. So one key thing that we want to do with the Hermes project chip was to show that we can achieve close to ISO accuracy inference, right? Even though we are performing the bulk of the computations in the analog domain. We went ahead and implemented an image captioning network. So here's an LSTM network, which will caption images. And here again, the LSTM and the dense layer computations are mapped onto the Hermes chip. And we see that we can get the blue metric scores, which are matching the software equivalents. So which is really amazing. So it looks like we can map these kind of networks and achieve software equivalent classification accuracies. So we have also built up a reasonable software stack for deploying a range of networks on Hermes. So it's at a stage where we can, absorb networks and we can map on them. But of course, clearly it's still a very exploratory chip, right? And many of the operations are not yet supported. So those ones we will be implementing on an FPGA board or the host CPU. But still, you can see how mature the technology is. And if anyone comes to IBM Research Lab in Zurich, you can come and have a look at the Hermes chip in operation. So how do we compare against the similar in-memory computing chips? So it has the largest on-chip bit capacity, out there compared to almost everything else. And as I said, a big task for us was to get the highest NPM and inference accuracy, right? And we are not doing any application-specific retuning. I mean, you just do the hardware-aware training, the additive noise training. That's all done in software. And once you get your synaptic weights, you map onto the chip, and thereafter you don't do any fiddling around, right? So it's a very elegant way of doing it. And we also could show that we can seamlessly interface this analog compute with other residual digital compute units, right? So this is another key aspect of this particular chip. So finally, in the last few minutes, I just want to quickly talk about the next generation AMC chips. So as you can imagine, we have, this whole effort is highly multidisciplinary in nature, right? Going all the way from the memory technology to the compute cores, system level architecture, the software stack, and in applications. So when it comes to the memory technology, our focus is primarily on improving the compute density, how dense we can integrate these memory devices, improving the compute precision, and more importantly, on improving the on-chip weight capacity. So in theory, non-volatile memory can be extremely, you can pack a lot in a given area, right? So that's where we're going at. And in the space of AMC cores, we are looking at more efficient data converters as a big part of reducing the energy consumption of the compute core. For the architecture, we are exploring heterogeneous compute architectures with different kinds of analog and digital compute units and efficient communication fabric for activations. Then we're always developing better and better hardware-aware training algorithms, and the software stack is also getting more and more mature. And application-wise, we are exploring, we are employing neural architectural search for deep learning inference, and we are also looking at applications that go beyond deep learning inference that can leverage these kind of AMC chips. I think I'm running a bit short on time, Juan, so I'll probably go over it very quickly. So in terms of the memory devices, as I said, one of the key things that we are trying to do is dense integration of memory devices, right? And especially in the case of phase-change memory devices, one thing which prevents us from having even denser memory device integration is a relatively high reset current or programming current in phase-change memory devices. And to overcome that, we are exploring this idea of using nanoscale confinement of simple materials. So this is something that we have been looking at and looks extremely promising. The other thing is the compute precision. As I said, we have something like 3 to 4 bit compute precision now. So we are trying to push it to the 5 to 6 range by using this concept of projected phase change memory. Again, showing a lot of promise, and you can look up more about it in these papers. But for weight capacity, what do we do? I think the most effective way of doing it is 3D memory, right? So 3D memory will be a game changer for AMC, because then your on-chip weight capacity can be remarkably high. I mean, just look at your flash drive, right? I mean, you can see what kind of weight capacity you can have in a given area. So that is the place where we believe that we can have full weight stationarity even for very large networks. So it's a big part of the work that we are looking into. For the architecture, I won't go into too much detail. As I said, already with the Hermes, you saw that there was some integration of analog and digital compute cores, and showing how we can seamlessly marry them. More recently, we have proposed a heterogeneous and programmable accelerator concept with these kind of analog compute cores and different flavors of digital compute cores, and also a dense and efficient circuit switch 2D mesh connecting all of them, right? And again, I would encourage you to take a look at it for more details to see how exactly these are all coming together to map different networks, and exactly what is also shown in that paper, right? How you could take like different networks and you can use this heterogeneous compute architecture to implement, in an end-to-end fashion, these different networks. So I think it'll be very interesting to look at that. So finally, in terms of the algorithms and applications, so as far as deep learning inference is concerned, most of the networks, most of the models we have now were designed to be well suited for the GPUs. But clearly, with this new type of architecture, there's an immense opportunity to really search for deep neural networks that are particularly well suited for this new type of architectures. So that is where the neural architectural search comes in, where you want to search for these architectures in a very automated manner, neural network models rather. The other point to bring up is that deep learning inference is definitely the primary application right now, but with very minor modifications, you can actually do deep learning training as well, right? So you can, for example, if you swap the columns and rows, then you can do a multiply operation with the transpose of the matrix. You can also use some of the other physics, like in place updates. By applying programming pulses, you can actually nudge the synaptic weights back and forth on these crossbar arrays. So that is again something extremely interesting, but I don't have the time to cover it. But you could probably look up these papers to get more information on that. And finally, deep learning alone is probably not going to solve general intelligence, but we may want to tie in deep learning with other paradigms. And in our group recently, we have shown that you could tie in deep neural networks with, say, vector symbolic architectures or hyperdimensional computing to tackle problems like few-shot and continual learning, analogical reasoning, etc. So this is again extremely fascinating area. And why it's interesting in this context is that many of the compute primitives, even in the context of VSA or hyperdimensional computing, are highly amenable to the in-memory compute fabric. So, and we have shown in multiple occasions how this could be leveraged. So that's it. So when you look at the next generation AMC chips, so you kind of see that we are working across the stack, right, innovating on every front to kind of arrive at the next generation AMC chips, which I believe will fundamentally change the way we'll be doing deep learning in the future. And to summarize, processing using memory or analog in-memory computing with physically stationary synaptic weights and analog processing, this has a potential to revolutionize the deep learning market, I believe. IBM Hermes project is a milestone in that sense, right? It serves as this test vehicle to show that indeed it is feasible, and we also show the efficacy of analog in-memory computing. There's a lot of ongoing work going on in memory technology, heterogeneous architectures, algorithms, and whatnot. So finally, I would like to thank my group in IBM Research Zurich, but we also work collectively with the IBM research teams in the US in particular. I'd like to thank all of them, and I would also thank the N number of academic collaborators that we have and then we work with. And we'd also like to thank you and the rest of and the Swiss National Science Foundation for all the support along the way. So with that, I'd like to conclude, and I'll be glad to take questions.
Great, Habu, thank you very much. Amazing talk. I think it was really nice how you started from the general idea of processing in memory and then narrow down to processing using memory architectures and with this focus on the Hermes project. I don't see any questions in the chat, but I would like to ask you a couple of questions. So the first one is that you mentioned in the first part, you talk about flash memory as another way of doing kind of similar processing using memory that seems similar to what you can do with memory stores. What are the specific advantages of using memory stores over flash?
Yeah, so the main advantage of, so by the way, both of them are interesting on their own right? So if you want to get on-chip weight capacity, I think Flash is a very good approach, right? And especially 3D Flash, I think it's definitely something that, people are looking into and should look into. So memory devices will be particularly useful for, where you want to embed onto a processor, right? Or an SoC. Because in Flash there's a technology mismatch, right? It's kind of difficult to marry high-end digital process, like higher CMOS technology node with flash memory nodes. So there's a technology mismatch there. Whereas a phase change memory can be seamlessly integrated into a high-end CMOS chip in the back end. Just like with resistive RAM and whatnot. In fact, this NeuroSoc project that we have, where ST Microelectronics is a partner, we are exactly trying to do that, right? So we are going to have phase change based in-memory compute cores on their microcontrollers, for example, right? You could do it with other chips too. So that's one big advantage. But Flash could be very interesting where you want standalone accelerators with a lot of on-chip weight capacity. But of course, there are a lot of technical challenges to be overcome there as well.
I see. Yeah. Yep, that makes sense. Thank you. I think I have a couple more questions. Also, comparison to another technology that you mentioned, the SRAM-based crossbars, right? That they use, say, similar operating principles, but in terms of precision, how do they compare to the memristors? Do they have any advantage in terms of the precision that you can achieve?
Yes. Yeah, so SRAM definitely, I think let me just bring it up. If you look at SRAM in memory computing, I think it has a lot of advantages going for it, right? The analog one, I'm not too sure how much compute precision they can get, but at least for the digital, right? If you look at it, it's clear that you can get whatever you want pretty much, right? It's just that we blow up the size of your chip, but you can get your compute precision, right? So it's a very interesting approach in that sense, but the challenge would be this: at the end, can we have full weight stationarity or not? Probably not, right? Because then you would need to blow up your chip size to get that. So you'll again be having, so the goal of having a full weight stationarity is probably not achievable in this scenario, correct? But for many edge applications, I think it's a fantastic choice, right? And it also scales the technology and whatnot.
Yeah.
But I'll also be very interested in seeing in the mixed signal how far they can push it. Because here, of course, there are some compute imprecision that could happen because of mismatches and all kind of stuff, right? And it'll be interesting to see where they land up.
Yeah, I agree. Okay, good. You mentioned that the Hermes chip, the chip already exists, but do you guys have any plans of commercializing it in the near future?
No, the Hermes chip is a prototype chip. It's a research prototype, so it's not meant for commercialization. I think what Hermes did was to serve as a it was helping us understand the technology better. And of course, we have offshoots on there. And what I showed in the last part of the talk, right? There are definitely work going on the next generation of that chip, as well as some other commercial engagements, right? Which are more geared towards commercialization. But Hermes is meant to be a research prototype. And we still use it for developing algorithms and trying out stuff.
Okay, good. And I think that this is my last question, because only at the end you mentioned transformers, right? And
yes.
Now we all are looking at large language models, how to accelerate them. Processing in memory is a pretty good candidate. As far as we can see, it's not that easy to exploit batching, or it has, as it has been done so far for other deep neural networks. But how about in transformers and LLMs, the attention layers are key for good performance. So how about these attention layers? Would usually require soft NC. Is it something that you can handle with the crossbars or with external units or?
Yeah, the vanilla attention with the quadratic complexity, no, right? Because we are operating on the activation signals, right? So which means that we don't have the endurance, right, in these devices to deal with that. Even if you use SRAM, I believe it may not be the right approach because of the energy that you take to load the weights. So right now, at least in this architecture that we proposed, we are doing the attention in specialized compute units, right? So it's done digitally. Whereas all the, when I say attention, it's only the attention, right? I mean, even the projection layers can be implemented in analog, right? All the projection layers, the WQ, WK, everything can be implemented in analog as well as the WO. But the attention compute itself, we are doing it in the digital domain. But of course, as you very well know, there are new innovations coming up, right, in that domain. I mean, even in the digital world, that's a huge challenge. So people are coming up with ways in which you can improve the attention compute, and we can easily absorb that into any architecture that we have. But I think the current thinking is that we will do the main attention compute still in the digital domain, and won't do it in the analog domain.
Yeah, that makes sense. The heterogeneous architecture is necessary here and for many other applications as well. And I agree with you that there are more and more innovations happening. So hopefully also alleviating what's the cost of these softmax or similar operations.
Yeah, exactly. Yeah.
Okay. Yeah, thank you very much, Abu. I think it was a great talk. It was really nice having you in this PIM tutorial. And hopefully, well, we will keep in touch, and hopefully we will hear more of your great talks in the near future. So yeah, thank you. And to all people attending the tutorial, we are going to have a break right now. We're gonna come back in 45 minutes. We will continue talking about processing using memory. Geraldo will do that, but he is going to focus on processing using DRAM, because in our group we are also doing a lot of research in the direction of processing using DRAM. So this way you guys are going to have like the whole view with non-volatile memories, as was the focus of Abu's talk, and also with DRAM memories, as Gerald is going to explain. So thanks everyone, and I hope to see you in about 45 minutes.
Thank you.
Thank you, Abu. Hello, everyone. We're back for the second part of this tutorial on real-world processing in memory systems. And now we have another exciting talk, again by Geraldo, a PhD student of the Safari Research Group. He's the expert in our group about processing using memory systems, processing using DRAM specifically. So yeah, I'm really excited about having Geraldo today. Go ahead, Geraldo. Feel free to share your slides if you're ready to start.
Thanks a lot for the intro, Juan. And let me quickly share my slides. Hopefully you can see them.
Yes, we can.
Okay, welcome again, everyone, to this part of the talk about processing using memory. This particular subject is really dear to my heart because it's the majority of my PhD thesis is on this subject. So I'm going to be talking about a lot of my personal work over here, and also some work that we have been using to build up on top of it. So let's get started then. Again, feel free to ask any questions on the chat or over YouTube. I'll be glad to take any of the questions. So in the first talk that I gave about memory-centric computing, we broke down processing your memory architectures into two main categories, right? Processing near memory, where we were adding logic elements inside the memory device to do some computation, and processing using memory, where we were using the analog properties of the memory array itself to do the computation, right? So now I'm going to elaborate a little bit more about this processing using memory architectures, right? So there are many benefits of doing processing using memory other than processing near memory. The main important one is that if you are doing processing near memory, independently on how close you get to the array itself, you are fundamentally bottlenecked by the interconnect networks that are placed inside the DRAM array or the memory array itself to move computation, right? Because you have a large amount of DRAM cells or memory cells connected together and accessed together. But when you need to move that large amount of data from the memory cells out of the DRAM array, there are buses and there are different types of interconnects that are going to sooner or later create either a performance or energy bottleneck for the system, right? So when you are doing processing using DRAM, you are using the entire throughput of the peak throughput of the memory array themselves, because you're going to operate using the cell. So you're not going to move, or we're going to try to move the data around the minimum amount as possible in this principle here. And one of the common approaches to processing using DRAM, from what we're going to see in this presentation, is to perform computation in bulk. So this can be bulk bitwise operations, like simple logic operations like AND or XOR, or more complex operations also in bulk, like additional multiplication. But you need to consider that this additional multiplication is being performed over all of the DRAM cells at the same time in a DRAM array, which a DRAM chip itself has around 65,000, like the R4 DRAM array has around 65,000 DRAM cells themselves. So when you're doing addition, you're doing 65,000 addition per unit of time, of units of latency that the addition takes. So this is an important feature of processing using memory architectures. So before we talk about processing using memory, and in particular processing using DRAM, I need to give a brief overview of DRAM, how DRAM works again, and so we are all in the same page, and we all can understand how you're going to use those operation principles to do computation. So again, if you joined the first talk that I gave, this is like the same background about the DRAM chip itself. So just as a reminder, a DRAM model is composed of several DRAM chips. The DRAM chips are composed of several DRAM banks. DRAM banks are organized as 2D arrays of DRAM cells called a subarray. Horizontal DRAM cells are connected horizontally to a word line and vertical through a bit line. The DRAM cells, they share a bit line. They are connected using a sense amplifier, which is a back-to-back inverter. A collection of sense amplifier is called a row buffer, and the DRAM cell itself constitutes of a storage capacitor, which stores information based on charge, and also access transistor, which allows you to connect the storage capacitor to the baseline and then to the amplifier. So in order to access DRAM, the memory controller performs 3 main operations: activate, read and write, and pre-charge, and those operations work as follows. So first, when the memory controller wants to start, initialize the access of some data in a particular DRAM row, the memory controller sends activate commands for that particular DRAM row. So the activate command is going to basically raise the word line connecting the storage capacitor to the bit line, and this connection is going to create a perturbation in the bit line and is going to make the storage capacitor lose charge to the bit line. Then the sense amplifier is enabled, which is going to make it start working basically, and it works by amplifying the deviation in the bit line, either if the to VDD or to ground, depending on the original storage, the original value stored in the storage capacitor. After this process, since the word line is still asserted and the storage capacitor is connected to the amplifier, the capacitor charge is going to be restored to its initial state, either VDD or 0. And after that, the data is latched in the row buffer, so in this amplifier. After this data is latched in the row buffer, the memory controller can send read and write requests to read chunks of data from the row buffer. So after sending all of the read and write that required for that particular DRAM row, the memory controller sends pre-charge commands to prepare the DRAM array for access to another DRAM row. And this pre-charge command is going to lower the word line. It's connecting the storage capacitor to the bit line. Then it's going to pre-charge the bit line to its original state, usually half of VDD, and it's going to disable this amplifier. So let's start simple. Let's say that we want to do simple operations inside DRAM, and the simple operation basically is DRAM row copy and DRAM initialization. So there is no arithmetic being performed. We just want to move data around inside the DRAM without the intervention of the CPU. So basically, these operations, a book data copy, where we copy a source row to a destination row, or a book data initialization, where we copy a value to a destination row, is a key operation for many systems, in particular cloud-based systems. So there are many accelerators that have been proposed to accelerate this particular type of book data movement in the cloud, for example. And those are examples of those. And again, those operations are not only important for the cloud system, but also other tests in the system, like the operating system, heavily uses book data copy initialization for operations like forking, zero initialization, checkpointing, page migration, virtual machine cloning, and many more. And there is a paper from Google in ISCA 2015 where they profile the key applications in their servers, and they saw that data movement created by the operation that was being performed to data movement in book, move and copy was accounted for 5% of the total cycles of those applications in Google's data center. And you might think that 5% is a low number, but you have to scale this up for how many data centers Google has, right? So if you can actually make this 5% zero, you're going to gain a lot of performance, and not only this, you're going to save a lot of energy. So how this book with data copy operation is performing today's system. So here there's a representation of a processor-centric system. And in processor-centric system, basically you need to send activate and a read command for each cache line in the store in the source page, and the cache line is going to be moved from my memory to the CPU via the cache hierarchy. And later on, you need to precharge that row, the first row, then activate another row, which is the destination row, and then again, then data needs to be moved to main memory to the cache hierarchy. Then the copy is performed by the CPU, and the data needs to be written back to the main memory device. So this operation leads to a high latency operation because you need to do this data copy cache line by cache line in the system. High bandwidth utilization because you need to move the data from main memory to the processor. Cache pollution because now you're bringing you're populating the cache hierarchy with cache lines that are going to be used really briefly and then move back to main memory. And one other data movement. So there is a lot of data movement that is going to happen in the system that you can ideally would like to mitigate. So if you want to do a 4 kilobyte page copy via DMA, and this operation in a processor-centric system would take around 1,000 nanoseconds and 3.6 microjoules. So how you want to do this operation? Basically, I just want to tell my memory device that give two addresses, a source and a destination, copy the source to the destination without the involvement of the CPU at all. If you do that, this operation is going to be quite low latency because we don't need to move the data from a memory to the CPU. It's going to be low bandwidth. You're going to require low bandwidth utilization of the memory channel or the memory bus because there is no movement from main memory to the processor itself, and there is no cache pollution again because no data is being moved through the memory hierarchy, and there is no one anti-data movement. So if you do this operation inside DRAM, you can do this data plus 4 kilobyte data copy. You can reduce its latency from 1 nanosecond to 90 nanoseconds, and further and reduce the energy consumption for the operation for around 2 to 3 orders of magnitude. So the mechanism that is going to enable this is Workload, which is a mechanism for in-DRAM data copy. And Workload only works in a really simple way. And the key idea here is just leverage the operating principles that I mentioned before, how DRAM is accessed, the activate and precharge, to do this data copy. So how it works. So in order to do a data copy operation, Workload first activates the source row, in this case A. It's going to copy the row to the row buffer in the DRAM array. Then, if you want to access another row in this array, the correct precision would be to send a precharge command, right, as I explained earlier, and then activate the other row. But instead, we are not going to issue that precharge command. We are going to send another activate, but to activate to the destination row, in this case, B here. So since the strength of the sense amplifier is much larger than the voltage level of the strength of the capacitor cell, the DRAM cell itself, what is going to happen is that the sense amplifier is going to push the data that they had currently being amplified. So the data in row buffer, in the data that was copied from row A into the row B, which basically de facto copying the source row to the destination row. So the main idea here is to issue two consecutive activate commands to the source into the destination row without a precharge. And because and based on that, we can do 4 kilobytes or row-wise data copy inside the DRAM array with basically no hardware cost, because note here that we didn't include any hardware device to do this internal data movement at all. So by doing that, we can reduce latency by 11 times and reduce energy consumption for data copy operations by 74 times. This is just another representation on how this operation is being performed. So let's say that you have source A and destination B. and source A and destination B share are connected to the same bit line, and they share this amplifier. Again, we are going to issue a sequence of commands, which is to activate. And after that, to activate, you can finally pre-charge the row. So we call the sequence of commands activate, pre-charge, and it works again as follows, right? You activate the first activate, the data is going to be from row A is going to be sensed by the sense amplifier, and then without pre-charging the DRAM array, we send another activation to destination row B, and the data that is currently amplified by the sense amplifier is going to be copied to the destination row B. And once the operation is done, you can finally send the pre-charge comments to disconnect both rows, and then put the DRAM array into its original initial state for further operations. So as you see, this is quite a simplistic, quite a simple mechanism, which enables quite exactly what you want, right? To copy data across the DRAM array without having the intervention of the DRAM of the processor itself, or other than sending, deactivating, pre-charge commands, right? So this operation that I mentioned here is to do row clone or data copy inside when the source row and the destination row are inside the same subarray. So inter-subarray data copy. So what we do if the operations are across different DRAM banks, right? So since DRAM banks share internal bus that connects those DRAM banks through the chip I/O and the memory channel itself, we can use the same principle of row clone to move cache line by cache line in one bank, one subarray in one bank to another subarray in another bank. So basically here we use send activate to activate the first row in one bank, and take the other row in the other bank. And then we send several what we call transfer commands to transfer the data from one row to another row in another bank through this shared internal bus. So by doing that, our performance benefits drop a little bit, but still we can reduce latency by almost 2 times and improve energy by 3 times compared to a processor-centric approach. So we can further generalize this to other operations, right? So to do row copy inside the same subarray, we send the to activate to those source destination row inside the same subarray. If you want to do interbanks, we do what we call pipeline mode. Pipeline serial mode in the row clone paper to copy the data in pipeline manner from one bank to another bank. And we also have a mechanism to do inter-subarray. So when you want to copy data from rows, when they're the source row and the destination row are in different subarrays in the same DRAM bank. For doing that, we use a similar procedure as the inter-DRAM bank data copy. So all of these incur really low area cost, 0.01% area cost on top of the DRAM chip. And this area cost is here not for adding logic. This is really important to see, show. We are adding some peripheral circuitry here just to help in the operation, in particular of this pipeline serial mode inside the DRAM chip itself. But that logic is not added for doing computing. So it's not the logic is not added for. It's not a hardware accelerator for the data copy. The chip itself is the accelerator. So again, this is we evaluate row clone compared to a processor-centric architecture, and then we see that we can reduce latency and improve energy quite significantly compared to that processor-centric architecture. So the same approach can be done. The same idea can be applied to do row initialization. Basically, if you keep one of the source row pre-initialized with zeros or ones, we can copy that row quickly using the same approach, the activate pre-charge approach, in using row clone itself. So if you want to use those mechanisms like zero initialization copy, we can accelerate many important workloads. So here in the x-axis, we have workloads, and then in the y-axis we have the fraction of memory traffic they are spending doing zero initialization, data book data copy, reads and writes. And you can see that, for example, for a fork bench, almost 60% of the memory traffic is due to data copy, right? So if you accelerate this application using the row clone idea, we can optimize those applications quite significantly compared to a processor-centric approach in an end-to-end way. So if you are interested in row clone, of course, I'm invited to check our paper and also our lectures on row clone. And again, this is enable us to do data copy using in three different locations in the DRAM chip itself. So as you may have noticed, I went quite fast through it, but you might have seen in this plot here that the most benefits that we get from row clone is when you are moving the data inside the same. So we have the source and the destination rows inside the same subarray in the same bank, and the performance benefit to row clone start decreasing when the data movement starts happening across different elements in the DRAM chip. The worst performance being given to moving the source, moving data across two different subarrays inside the same DRAM bank. And this is why this happens, because we need to actually copy the row to an intermediate bank, and then using the transfer operation to copy the data to the destination row, which is quite it can be inefficient. So we went to analyze what was the problem, and again, this is just an overview of how the DRAM array is organized. And again, the DRAM array is organized using several subarrays, and those subarray shares narrow interconnect to move the data from the subarray, from the DRAM bank outside to the bank I/O itself. So this low connectivity in the DRAM subarray or in the DRAM bank itself, it becomes a bottleneck even for row clone if you want to move data in bulk, because now you are limited by this 64 bits internal bus. And our goal is to provide, our goal was in this work to provide a new substrate that can enable better connectivity between the DRAM subarrays. So to solve this problem, we implemented Lisa, low-cost interlinked subarrays, which has a really simple key idea. So the key idea of Lisa is to connect adjacent subarrays using isolation transistors, which incurs low area cost on top of the DRAM chip, 0.8% on top of the DRAM chip. So now we have a direct path, right, from one for the rows in one subarray to the row in the other subarray in the same DRAM bank, and it enables us to do bulk data copy more efficiently than row clone originally can do it, and also to accelerate other applications like DRAM caching and faster DRAM pre-charge. So if you are interested in Lisa, feel free to check our paper from HPCA 2016. So there are also other ways of moving data. So let's say that you don't want to move the entire row, but you just want to move portions of the row across different banks. So that was the main task that we went to solve in this figure paper. And this figure paper enabled us to do data reallocation in a column granularity across different rows in different DRAM banks in the same DRAM chip. So this is for data movement, right? So we can copy data quite efficiently inside the DRAM chip across DRAM subarrays, across DRAM banks, even across DRAM chips. We didn't explain here, but and also different granularities, right? And what about other more complex operations? Let's say that we want to do operations like AND or NOT and majority. How can we do that at low cost, exploiting the same principles that I explained of how DRAM works in the past? So the idea to do that is quite similar to the row clone idea. So instead of activating 2 rows at the same time, we are going to activate 3 rows at the same time. So when you do this activation of 3 rows at the same time, we can basically do the majority operation of the data inside that 3 rows. And I'm going to explain why later on. And this type of mechanism further improve performance by 30 to 60 times compared to performance and energy compared to a processor-centric approach. And we presented this idea in the Micro 2017 EMBED paper. So there are other memory technologies that also allows us to do similar operations like that, book bitwise operations, including memory resistive devices, ReRAM, phase change memory, and I'm going to briefly talk about them as well. Also flash devices, and they can operate on the data movement with minimal overhead. So what is the key idea behind this book bitwise majority operation, right? So the main idea here is triple row activation. So let's assume again that you have 3 rows, row A, row B, and row C, and those 3 rows are connected through the same bit line sharing a sense amplifier. And these 3 rows have varying degrees of charge storing over there. So in order to do a majority operation of the 3 rows, we are going to create a command sequence, which is called activate, precharge. So it's 3 activations and a precharge, but for the way that the EMBED paper usually proposes it, it's just activate, precharge, and I'm going to explain why over here is a single activate. Basically, we are going to redesign the row decoder in the DRAM array, so that with a single DRAM, the single address, we can activate 3 rows at the same time. But the underlying principle is the triple row activation mechanism. So we send the activate command, this special activate command, which can activate 3 rows at the same time. And then all of the 3 rows, A, B, C, and D, are going to simultaneously perturbate the bit line with their respective original voltage stored in the DRAM capacitor itself. So the bit line is going to be pulled based by the amplifier based on the majority of the cells of the voltage levels stored in cells A, B, and C. And this happens because this amplifier that we have in DRAM is a differential amplifier. So it's basically by design. So when you do the majority of, in this example here, of A, B, C, and D, we are going to have the majority of, in this example, VDD, VDD, and 0, and which is equals to VDD. So the majority of a 3 input majority is 1 only, or VDD only if at least 2 of the inputs are VDD and 0 otherwise, or ground otherwise. So an important feature of this operation is that since all of the 3 DRAM cells are still connected to the DRAM sense amplifier, the result of the majority operation is going to be copied back to the DRAM cells themselves, and then the data is going to be overwritten in the 3 DRAM cells. So after that operation is completed, we can send a precharge command to activate to precharge the 3 to prepare the sense amplifier or the DRAM array for further operations. So by doing if we use this approach for triple activation, and if we set one of the inputs to a constant value of 0, basically what we are going to have is the end of the 2 other inputs. And if you set one of the inputs to 1, what we're going to have is the OR of the other 2 other inputs. So basically, EMBED proposes this mechanism to do AND and OR operation. So EMBED proposes a specialized sub-array organization, which I briefly mentioned, where we are going to have some designated rows for triple row activations. Also some designated rows with pre-initialized constant values of 1 or 0s to control if you want to do a AND operation or operation, and then the regular DRAM rows to store processors, to store data values from the applications or the user. And the regular rows and the constant rows are be connected to the regular row decoder that is responsible to assert the word line, but the but the computing rows or bitwise designated rows are going to be connected with a specialized row decoder, where with a single address we can activate 3 rows at the same time. So this redesign led us to less than 1% overhead on top of existing DRAM chips. Again, it's really important to state that this overhead here is important to highlight. This overhead is added here not to do the computation. So you can still do ambit processing using DRAM operations without this special row decoder. And this is a common misconception for many follow-up works. The redesign of this specialized row decoder here is not a fundamental limitation of ambit. So the way that the original ambit paper is proposing, or what the main idea that ambit is being proposing here, ambit is proposing, is to activate 3 rows and then allow the activation of the 2 rows to perturbate the bit line at the same time. The redesign of this bitwise decoder and this area overhead that is added to do that is just optimization so that we can do this operation more efficiently. But again, this is not area being added so that we can do the bitwise AND and OR operation. Note that here we didn't include any gates to do AND and OR. It's basically all of that on the operational principles of the DRAM array itself. So originally, ambit was proposed in this call paper in 2015, and what was missing was basically a way of doing NOT. So if you can do AND or majority operation, we are one step to be functional complete. So if you can do AND or and NOT, we can do any. We can combine that to do any operation. So the way of us to enable NOT operation in ambit itself is by studying how the DRAM sense amplifier is designed. So as I mentioned earlier, the DRAM sense amplifier is basically 2 back-to-back inverters connected to the bit line. And one of bit line is going to have the original value, and the other end of the bit line is going to have the negated value. So the key idea here is to create a path between the negated path of the bit line back to the DRAM cell using dual contact cells, so that we can control if you want the bit line value or the bit line bar value. So we are not including yet another NOT gate to do NOT operations. We are just reusing the NOT gate that is already available in this amplifier to do the computation or the NOT operation. And this enables us to again do a NOT operation. So we evaluate several book bitwise operations, the throughput of several book bitwise operations of ambit compared to processor-centric architectures, both accelerator processors and GPUs, and we see that ambit significantly provides significant throughput improvements compared to those architectures for NOT, NOR, NAND, NOR, XOR, and XNOR. And also ambit significantly reduce energy consumption when doing those operations inside DRAM. So book bitwise operations are available in many key applications. You find book bitwise operations in database applications, in web searching, in DNA sequence analysis. And we took some of those applications and accelerate them using ambit to see what was the end-to-end performance improvement and energy savings that ambit would provide for those applications. So one of these examples here is the bitmap index application, which is an alternative to bittrees in databases. And it's quite efficient for us to perform range queries and join operations. And again, since this is for querying, there is a lot of bitwise operations that requires to perform a query. So here we have an example of one of those operations. Let's say that you want to filter basically users that have age in a particular category, and then you can use basically a combination of Boolean operations to do that filtering. So we implemented this bitmap index on ambit, and we see a significant performance improvement. So 5 to 6 times performance improvement compared to a baseline CPU when you're doing this application using the triple row activation approach. And also This is another application, bitweaving, which is also a database operation. And again, we see quite significant performance improvement. So this is the Emmett paper from 2017. And we later on explain it further in a book chapter, which is more extensive and has a really good DRAM background. If you're particularly interested on DRAM organization, I highly recommend checking out this paper. So, okay, we can do we can do data copy, data initialization, and or not the majority operations in DRAM, right? So what is missing? So basically, we are just basically limited to those simple operations. So what about some operations that are more complex, like multiplication or subtraction, which are quite common in many general purpose applications, right? So if you cannot enable those applications efficiently, or process using DRAM substrates, it's not going to be widely applicable. Also, there is this problem of the number of operations that we have, that is to be of a limited set. So we can do all of those operations, copy, initialization, and or not, combinations of that, nor, and. But once we are exhausted, at least we are basically done. So what if I come up with a new operation that I want to do? How I implement this new operation using processing using DRAM primitives? There are prior works that proposes way of doing more complex operations like addition inside the DRAM array, but those works often require significantly changes to the DRAM array itself, and because of that, it's quite costly in terms of area. So basically, we need a framework that allows us to generalize processing using memory or processing using DRAM approach to implement complex operations inside the DRAM array, let's say multiplication, and allows the user to give the user the flexibility to implement a given arbitrary operation as needed in using processing using DRAM primitive. So basically, our goal is to propose this framework, right, that can efficiently implement complex operations, provide the flexibility to support new desired operations, and minimally change the DRAM array architecture. So in this end, we propose SimDRAM, which is an end-to-end process using DRAM's framework, which is going to provide the program interface, the instruction set architecture, and the hardware support for efficiently computing complex operations in DRAM, and providing the user the ability to implement arbitrary operations as required. Oh, it's important to also notice that SimDRAM, and we're going to understand this later, why, enable us to implement basically in DRAM massively parallel SIMD substrate with minimal modifications to the DRAM array, where each one of the DRAM sublines, bit lines, becomes one SIMD lane, and they can and then you can have all of those 65,000 bit lines that I mentioned before operating as a really massive SIMD engine. So the SimDRAM framework is built on two main techniques. The first one is to organize data in a vertical data layout. So originally, data is distributed inside DRAM rows in a horizontal data layout, where we have all of the bits inside a word is spread out across the different bit lines in a single row. But we're going to change that. We're going to flip that organization, or transpose that organization, and then we are going to place all of the bits of words across different word lines in the same bit line. So compared to the horizontal data layout, this enables us to do explicit shifting operation using row clone. So basically, if you want to shift one bit position to another, basically enable row clone from one row to another. And this is key to implement complex arithmetic operations which require data propagation, like rip carry adder, for example. And this also enables us to provide a massive parallel SIMD substrate inside the DRAM array. So the other thing that we're going to leverage here is majority-based computation. So Ambit proposes to do computation using and or not based operations, right? But the underlying mechanism that we have for Ambit itself, and I was presented before, is a majority majority gate implemented in the simplifier or implemented using the simplifier. So why we are going to use and or not representation where or base representation for doing this type of computation is not is majority based operations, right? So if we do our operations based on majority based computing, we can further reduce the latency of doing processing using DRAM operations, so we can have higher performance and higher throughput at a lower energy cost. So then, based on all of this, we propose the SimDRAM framework, which is a three-step framework for processing using DRAM execution. So SimDRAM takes as input desired operations of the user implemented using and or not logic. So this case here is the carry propagation logic of a RIP carry adder. And the first step is going to generate the efficient implementation of that design operation using majority and not logic. The second step is going to convert that majority not logic into a sequence of DRAM comments that implements that computation. And this is going to be called a microprogram. So the microprogram is stored in main memory and added to the CPU ISA for future use. So when the user wants to do processing using DRAM computation, it uses this new SimDRAM instruction to trigger a microprogram and to trigger a control unit which we co-designed together with the memory controller to issue the appropriate sequence of activate commands that implement that operation in DRAM. So let's look at each step in a little bit more details. So converting and or not representation of a gate to its majority operation or majority representation is quite straightforward, as I mentioned before for AiM, right? So if you have a majority gate and you set one of the inputs to 0, basically you have an AND gate. And if you have a majority gate and you set one of the inputs to 1, you have an OR gate. So basically, if you have a majority not representation of a circuit, we can basically go gate by gate and change the AND OR gates to the majority gate as needed. However, if you do that, doing this naive conversion, we are going to have an unoptimized circuit. And if you have an unoptimized circuit, this leads to more triple row activations inside the DRAM array, which incurs a higher latency. So our main idea here was to leverage prior work that proposed optimizations based on majority of algebra. I think here similar to what we learned in Boolean simplification with the Morgan laws and all of those simplification laws. So it's pretty similar to that, but tailored for majority gates. And we applied that to reduce the number of logic or the number of majority gates in or naive representation. So with that, we can generate a optimized majority not implementation of the desired operation. So here, the carry out propagation circuit from the RIP carry adder went from 4 transistors to only 1, 4 gates to only 1 gate. The second step is the generation of the microprogram, right? And again, the microprogram is just a series of microarchitecture operations, activate and pre-charge commands that SimDRAM is going to use to execute the operation in DRAM. So so we want to generate this efficient microprogram with the minimum number of activate and pre-charge commands if possible. So again, to improve latency and reduce energy. And to do that, we are going to generate the microprogram in 2 main steps. The first step or the first task is to allocate DRAM rows to operands, and the second task is to generate the microprogram itself. So let's look at the first step. So the first step needs to take 2 things into consideration. The first thing is that we have a limited amount of compute rows inside the subarray itself. Again, this is we are taking into consideration that optimization that AiM applies to with a single row address, we can activate 3 DRAM rows. And the second consideration is that when you do a triple row activation, the triple row activation is destructive. So basically, the output of the majority operation is going to overwrite the initial data store in the 3 original rows. So those things need to be taken into consideration. So based on that, the allocation algorithm to allocate the input gates to rows works in the following steps. So basically, it's going to take our location algorithm is going to take as input the majority not representation of the given operation generated in the first step, and then it's going to assign the inputs of the majority logic primitives to the available compute rows, one input at a time. So since the number of rows, the compute rows are limited, 3 in this example over here, this step of the algorithm only assigns as many inputs as the number of compute rows available in the DRAM subarray itself. Also, our algorithm is going to take into account those 3 input rows can be reused because of the destructive principles of the DRAM row, the triple activation. So if basically the next portions of the circuit also requires an input that also requires one of the outputs of a previous triple activation, we can use any of the 3 rows that was originally used as inputs for this location, which basically reduced the number of data copies that we need to do. So this is just a simplification of how this algorithm works. And then the next step is to basically generate the microprogram. So once that we have assigned DRAM rows to activations, inputs of the DRAM of the majority dot representations to DRAM rows, basically we need to traverse the graph of the circuit and generate row copy operations and triple row activations for one majority cell per time. So basically, we are going to issue activated row clone operations for each one of the inputs to copy the inputs operand to the designated rows inside the DRAM array. And then for a majority gate itself, we are going to issue a triple row activation to perform that computation. And later on, if there is output, we copy back the output to the destination row. So this is our initial microprogram, but this initial microprogram is an optimized microprogram. So we are going to further optimize this microprogram with using 2 steps. So the first step is to coalesce row copies together. This again is based on the principle of the specialized row decoder that we have inside the DRAM array itself, and also merge majority gates and row copy operations together and coalesce those in a single operation. So by doing that, we can have an optimized microprogram, which requires fewer DRAM operations to do computation. So the next thing that we need to do with this microprogram is to generalize this operation or this sequence of commands to execute n-bit computation, because this sequence here only performs a 1-bit operation. So if you want to do a n-bit addition, we need to repeat this microprogram n times. So then we have our final microprogram, which is optimized and is consider the operations of varying size computation. So this microprogram is stored in a reserved region of the DRAM array for future use, and also is added a new instructions to the CPU ISA, which you call BBOP. So the third step is a control unit inside the DRAM array itself, the memory controller itself, which basically is going to receive BBOP instructions, load the microprogram, and issue the sequence of DRAM activate commands storing the microprogram to the DRAM array to perform the required operation transparently from the user. So in the SimDRAM paper, we consider several system integration challenges and propose solutions for them. And here I'm going to talk about one of them, which is the data transposition. So as I mentioned before, SimDRAM operates on data stored in a vertical data layout, while the system operates in data stored in a horizontal data layout. So there is a challenge here of converting data back and forth between SimDRAM and CPU while incurring fewer performance drops or performance overhead as possible. So to do that, we propose a new hardware unit inside that's placed across the last revocation and memory controller, which is the transposition unit. So this transposition unit basically constitutes of object tracker, which is going to track memory regions where SimDRAM operates with, and transpose the memory regions from a horizontal to a vertical data layout, where the data moves from the last level cache to the memory controller doing evictions, and from a vertical data layout to horizontal data layout when the data is fetched from main memory to back to the last level cache. So this transposition unit incurs low impact on performance and low area costs on top of a baseline CPU die. So in terms of programming interface, we had 4 new ISA instructions to do SimDRAM operations. The first one is an initialization instruction to initialize the object tracker in their transposition unit. 1 inputs, 2 inputs, and predication BBOP operations for processing processing using DRAM operations. Here briefly, I have a code that shows how one can program SimDRAM. So in this paper, we don't have a compiler for automatically doing this, but we do it by rewriting code. So here in the example here, have a simple vector addition operation that depends on a condition, and SimDRAM implements this equivalent code by first issuing the registering the arrays that are going to be used for computation in the transposition unit, then issuing the addition, subtraction, the predication, and the result and the end of the result of the predication using the BBOP operations as I mentioned before. So this resembles programming a SIMD processor, similar, for example, to AVX, if you try to program an AVX instruction using an assembly language, for example. So there are more in the paper, more system integration results or solutions in our paper, and I invite you to check it out. So we evaluate SimDRAM using Gen5 and compare it against 3 baselines: a multi-core CPU, a high-end GPU, and Mbed. And we evaluate SimDRAM using DDR4 with varying numbers of SimDRAM-enabled DRAM banks. So 1 DRAM bank, 4 DRAM banks, and 16 DRAM banks. We evaluate 16 DRAM operations like addition, multiplication, value, predication, bit count, and 7 real-world applications from varying domains. So in terms of throughput, SimDRAM significantly outperform the CPU, also the GPU, depending on the number of DRAM banks that is enabled, and also Mbed. So we conclude that SimDRAM is a efficient processing using DRAM for a range of operations. So in terms of energy, SimDRAM significantly outperforms the CPU, the GPU, and Mbed. And in terms of real-world applications, we gain significant performance improvement compared to the CPU, also compared to the GPU, depending on the number of DRAM banks that is enabled, and also compared to Mbed. So we conclude here that SimDRAM efficiently and effectively accelerate many commonly used real-world applications. So in the paper, we evaluate other things. We evaluate reliability, data movement overhead, data transposition overhead, area overhead, and we also compare SimDRAM to prior in-cache computing mechanism. So basically, in conclusion, SimDRAM is an end-to-end processing using DRAM framework that provides the ISA, the program interface, ISA, and hardware support for efficiently computing complex operations inside DRAM, and provide the user the ability to implement arbitrary operations as required, all of that using a massively parallel in DRAM SIMD substrate. SimDRAM provides significant throughput and energy efficient results compared to CPUs and GPUs, and for micro benchmarks and also for real-world applications. So SimDRAM is a promising processing using DRAM framework that can ease the adoption of processed DRAM architectures and improve performance and energy efficiency for processed DRAM architectures. So okay, we have SimDRAM with Mbed and row clone so far. So if you want, we have basically a way of doing data movement using row clone and Mbed, right? We can do bitwise and or not operations using Mbed. We can do bit shifting using prior, which I didn't mention here, called RISA, or the implicit bit shifting that I mentioned in row clone. And we can do arithmetic operations like addition multiplications using SimDRAM. However, we are still limited, right? So if you want to implement transcendental functions, for example, like sine, cosine, none of those prior proposals can do it efficiently because we would have to approximate those sine, cosine computation using things like Taylor series. So in this work that we call Pluto, our goal was to extend processing using DRAM to provide further support to other complex operations, particularly transcendental functions. So the key idea of Pluto is actually a really old key idea, right? So the way many systems work, regular system works, is that there is an input, there is a processing engine, and there is output, and then basically what the processing engine is doing is mapping the input to the output. So instead of doing that, instead of doing this every time you do this mapping, we can pre-calculate the mapping between inputs and output using lookup tables, and then replace the computation. Instead of you doing the proper computation, we can replace that with memory access to fetch the pre-computed elements from this lookup table. So the key idea of Pluto is to replace computation with memory access using this Pluto loop query operations to enable, the execution of complex operations inside DRAM. So let's say that here, for example, you want to do a simple query from your process using DRAM engine, where we want the process using DRAM engine to return the second, first, second, and fourth prime numbers. And so that would be basically 3, 2, 3, and 7. This is what the result that we would expecting. So we are going to pre-compute those sequence of prime numbers, for example, and store this pre-computed number of functions, pre-computed prime numbers inside the DRAM array itself, and then we are going to index this table inside the DRAM array using input vector, which represents the indexes of the elements inside those tables. So basically, in the DRAM array, a substrate of that we are proposing in this Pluto paper is constitutes of an input vector, which stores the indexes of the lookup table query that you want to store, to read, and also the output vector, which is going to store the final value of the lookup table query operation. And then we have our DRAM or Pluto-enabled subarray. In this Pluto-enabled subarray is going to store the lookup table. We also modify the DRAM array with some matching logic, which is going to match the currently accessed row in the DRAM array with the index stored in the input vector. And based on the matching output, it's going to enable or disable some isolation transistors that connects the row buffer of the Pluto-enabled subarray to the output vector. So the DRAM array itself is going to store several copies of the Pluto loop query or the Pluto loop table, so that we can do lookup table operations with using the iDRAM internal parallelism. So let's see how this operation works. The main operation in Pluto is called Pluto row sweep, which is going to, with a single command, going to go through every single DRAM row, access every single DRAM row, row by row. So the first row is enabled, and basically, as I explained before, the word line is asserted. The data is copied from the row to the row buffer, and then Pluto is going to check the index of the current row with the index stored in the input vector that represents the lookup table query operation. So here we are basically going to check. So am I accessing the second prime number, which represents the first lookup table index here? No, right now I'm currently accessing the first prime number, right? Which is indexed using the lookup table index 0, right? So this is not a match, and then the matching logic is not going to be asserted. So then we check the next one. All of this is in parallel, but anyway, so I check if I'm accessing the next element of the input vector. So am I accessing the first prime number, which is the row index 0? In this case, yes. So it's a match. And then since the match, the position for the isolated transistor that connects the second position of the row buffer to the output vector is asserted, and then the data is copied. Then this repeats for the other one. So 1 is not equals to 0, 3 is not equal to 0. And then we have our final. We copy. They have the final values stored in the output vector that represents a match. Then we move to every single row one by one. So again, row 1, the same things are that the row is copied to the row buffer. I ask the matching logic which ones are matching, and then it's just the first one and the third one, and those elements are stored in the isolation transistors, and the data is copied to the output vector. And I move to the next row, there is no match, and then finally to the last row, and then there is a match in the last element. So in the end, in the output vector, we have the result of our Pluto lookup table query operation. So in the Pluto paper, we implement 3 different designs of Pluto with the varying trade-offs. So the first one is what we call buffer sense amplifiers, which is what I just mentioned, where we're going to use extra logic to store intermediate results, intermediate matches from the Pluto loop query operation. The second design is the gated sense amplifier 1, which we are going to use the DRAM cells themselves to store intermediate results, and then the third step is the gated memory cells. Sorry, the previous ones are going to use the sense amplifier for that operation. And the third one is the gated memory cell, which are going to use the DRAM cell itself to store the intermediate representation. So these 3 designs covers different trade-off space in terms of performance, energy, and area efficiency. So where the buffer sense amplifier design provide medium performance, medium energy efficiency, and medium area efficiency, the gated sense amplifier design provide high area efficiency, lower performance, and lower energy efficiency. And the gated memory cell architecture provide the highest performance, the higher energy efficiency, but that comes at the cost of low area efficiency. So the main takeaway here is that Pluto covers a broad design space exploration in design space in terms of performance, energy, and area efficiency. So in the Pluto paper, we also cover system integration of Pluto which involves C-like code using Pluto API calls, assembly code using Pluto ISA extensions, and also a controller placed in the DRAM memory controller to issue the activate and precharge commands required to do the Pluto lookup table operation. And you can check more on that in our paper. So we evaluate Pluto using 7 real-world applications, and we see that it significantly outperforms the CPU, and also significant, depending on the Pluto design, it also outperforms the CPU and prior crosshead memory architecture. So the main takeaway here is that Pluto significantly is outperform processor-centric and memory-centric architectures. In terms of performance per area, Pluto significantly outperforms the CPU and the GPU. And in terms of energy efficiency, Pluto significantly improves energy efficiency compared to a CPU and the GPU. So there are many more things in our paper. There are comparisons to GPU, to FPGAs, comparisons of sub-array level parallelism, area overhead analysis, and many other things. And we invite you to check our paper and our talk on Pluto for more information on this work. So now we are covering a bunch of applications and a bunch of operations that we can do using processes in DRAM. And the question that remains is that, is it feasible to do processes in DRAM, right? So fundamentally it is, right? Theoretically it is. We have proven that in simulation, but can commodity DRAM chips do processing using DRAM operations? And our prior works from actually other research groups have shown that we can do operations like row clone, for example, using off-the-shelf DRAM chips. So those are unmodified DRAM chips. So we apply row clone idea over there, but we're going to, instead of, basically we're going to violate DRAM time parameters to mimic row clone operations. So I'm not going to get into details on this here, but basically what is happening here is that we are not going to wait. So when you send the activate precharge activate sequence of comments, we are not going to wait for this precharge comment to finish up before sending the next activation. And then basically because of that, the bit line is going to have some voltage level from the first activate rows, and then row clone mechanism is applied. So the data is copied from the first row to the second row. Likewise, we can do majority end operations again by varying the timing delay between the activate, precharge, activate commands, and that works by changing the row address in a particular pattern. So the authors of ComputeDRAM have tested this approach using common off-the-shelf DDR chips, and using a SoftMC platform, which is a FPGA-based platform that enables us to basically to change the DRAM timing parameters with a custom memory controller. So they evaluate several DRAM chips, DRAM models for very DRAM manufacturers. So 32 DDR3 and 256 DRAM chips on total. And again, they use the SoftMC experiment setup to figure out which were the time delays that they should incur so that they can have row clone and book bitwise operations in DRAM. And then basically they show here in this plot, it represents the ratio of success that we can get for doing different operations like row copy of AND and NOR operations in those DRAM cells. So it is not this operation is not always successful because again, this is using off-the-shelf unmodified DRAM chips. So there is not a super reliable operation, but for several DRAM chips, we can actually copy and do those operations without any change to the DRAM array itself. We further extend this idea of using off-the-shelf DRAM chips for processing using DRAM with the PiDRAM infrastructure, which is an end-to-end FPGA-based framework that encapsulates the required DRAM, the required operations to do this processing using DRAM frame operations in off-the-shelf DRAM chips. So again, we are using here FPGA-based platform with a RISC-V machine, and to dispatch those processing using DRAM instructions to the DRAM chip itself, and transparently from the user execute, like for example, a row copy operation for a user application. So we open source PiDRAM in our GitHub repository, and we see that using PiDRAM we can do in-DRAM row copy initialization and improve throughput for quite significantly compared to a processor-centric approach. Again, feel free to check our GitHub on PiDRAM, and also our talk on PiDRAM that Atabek gave at one of the computer architecture lectures. So processing using memory is not restricted to DRAM. Processing using DRAM is also possible to do it in caches, and also so using SRAM arrays, and also in non-volatile memory, right? So one of the first work that shows that how to do row copy and bitwise operations in non-volatile memories is the Pinatubo works, and basically here they are doing some modifications in the simplifier design so that we can do bitwise operations. Also other ways of doing processing using memory in non-volatile memory, and this is a little bit different from the processing using DRAM approach that I mentioned before, is by again using the analog principles of these non-volatile memory devices to do computation. And since those the way that those processing those memory devices operates is a bit different than DRAM, so they are based. Those are resistive based devices that operate on based by applying some current on the word line, and if you do the math, basically by applying Kirchhoff laws, we can actually do a dot product operation between the resistance level stored in the cell and the current level that we apply in the word line itself. And this is quite useful when you're accelerating things like neural network inference, because the main operation in convolution neural networks, for example, is dot product. So those architectures are fundamentally really good at accelerating these convolution-based applications. There are some needs, of course, to some peripheral circuitry to convert the data from a digital domain to an analytical domain and vice versa. So here is an example. I'm going to move to this one, so it's more informative. So here I have a 2D array of resistive cells. And again, those cells are storing information based on resistance levels. By applying some voltage to the word lines over here, the output current that is going to be generated is going to be the following Kirchhoff law is going to be the dot product of the inverse of the resistance of the cell and the applied voltage level in the word line itself. And basically, this is a dot product operation. And if you map these to neural networks, basically, we have some inputs and some weights that are stored as resistance levels in the DRAM array itself, and then we have the output of the convolution in a intuitive way or in a low overhead way. So again, many prior works have shown how to accelerate neural networks using this type of architecture. And actually, quite important for this real PIM tutorial, there are actually startups working or creating products for neural network inference based on resistant based memory arrays. So also this is like a real product that is becoming more and more commercially available these days. Not only these not emerging non-volatile memories can do dot product, but like the storage devices like flash NAND cells can also do book bitwise operations similar to Mbed. So really briefly, again, we need to understand a little bit of the background of the how this NAND flash operates, so we can understand how they can do computation. So flash cell stores data by adjusting the amount of charge in the cell. So low charge level operates like a resistor, and high charge level operates as an open switch. So a series of NAND cells are serially connected to form a NAND string, and a series of NAND strings are connected together, forming a NAND block. So if we can apply a similar approach at Mbed to do AND and OR operation, right? So for example, and this here, instead of being triple activation, we are going to do multiple sensing of the data in a NAND flash block. So when we apply when you actually activate or the multiple word lines in the same block, the output of the bit line is going to be 1 only if all of the DRAM of the flash cells are operating as a resistor. So if one of them are operating as an open switch, the output is going to be 0. So basically what we have here is a AND operation where the bit line is going to read 1 only when all the target cells store 1. So, and based on that, we can do AND operations of multiple pages in the same block via this single sensing operation. So a similar thing can be done with the cell, the cells store across different DRAM blocks. So when you access multiple DRAM, the cells in multiple DRAM blocks, sorry, a flash block, a bit line is going to read 0 only when all of the target cells store 0. So if one of them are 1, the output is going to be 1. So likewise, we can do OR operation of multiple pages in different blocks via a single sensing operation in flash code. So in conclusion, basically the key idea of processing using DRAM, or all of those approaches that I mentioned here, is STOC, row clone, Mbed, SimDRAM, Pluto, the resistant crossbar arrays, flash cosmos. All of them are using the analog principles of the DRAM array, of the memory array itself to do computation. We are indeed change some of the peripheral logic to do some efficient to support these operations efficiently, but these changes are not to do they are not fundamental to do the computation. The computation is performed by manipulating the cells themselves. So this allows us to exploit higher internal connectivity of the memory arrays themselves, to exploit higher bandwidth and parallelism, again, because of the way that array cells are connected. And based on that, we can do simple operations like AND or XOR operations, or more complex operations like addition, multiplication, or transcendental functions. And there are still a lot of research being conducted on processing using DRAM architectures. I didn't put it here in this presentation, but we have several papers coming up in the upcoming HPCA 2024 application conference, which we are further in studying several systems challenges that are still needed to be fixed or propose solutions for making processing using DRAM efficient in current systems, and including programmability. And in today's micro, in tomorrow in micro, I'm going to present, for example, a poster that allows us to solve one of those system challenges for processing using DRAM, which is related to virtual memory and data allocation. So yeah, so it's a really exciting time to do research on processing using memory, because it's a really edge at the edge of what we can do in terms of fundamentally change the way that we do computation. So this is quite a good time to think about those problems and work on those processing using memory problems. So hopefully I managed to convey the message and to motivate the audience to this important new and exciting field inside processing memory. So I'll be glad to take any questions, and thanks so much for your attention.
Yeah, I think you did, Geraldo. Thank you very much for the talk. I think it was a very, very good lecture. Very good summary of all the different works where you have been involved in processing using memory. We have had the prior talk before the break was by Dr. Abu Sebastian, and he already talked about processing using memory, but the research that they do at IBM Research Zurich with non-volatile memories, it was a very interesting talk. And at the end, as you also mentioned, the PiDRAM work, we are going to have Ataberg Odgun as well, talking about the PiDRAM framework that you also mentioned in your talk. I don't see any questions for you in the chat, either in YouTube or in Zoom, but I would like to ask you something, because I mean, related to what you said at the end, new works that are coming. Why don't you give us a very brief summary, a very brief, let's say, abstract of your MIM DRAM that will appear at HPCA?
Yeah, I'll be glad to give that. I'm not going to try to pull up some slides, but I can briefly try to convey the summary of it. So in processing using memory, in particular, like we saw in SimDRAM, right? I keep talking about this number, 65,000 number of operands that we can operate at once in a SIMD fashion using a single micro program, right? So this is really good. So provides a lot of high throughput for applications, and further accelerate those 7 real applications that we saw in the SimDRAM paper. But the question is a real application, does the majority of real applications have this type of large bulk parallelism that can be accelerated by processing using DRAM? And we did a lot of analysis in our paper, in MIM DRAM paper, and we saw that actually not. So basically the amount of SIMD parallelism inside real application varies in granularity. So there are applications that have a larger and smaller SIMD parallelism. And also if the amount of parallelism is not a multiple of the DRAM row size, that is also problematic, because now if all of this happens, we have underutilization of the processing using memory substrate, and this underutilization leads to waste in throughput and waste in energy. So that is the problem. One of the first problem that you are trying to solve in this MIM DRAM paper, and the second problem is programmability. So how we program SimDRAM? So I showed the code here, right? That we actually were writing assembly line code to program SimDRAM, which is not efficient, right? If you are a programmer, you don't want to have to think about composing operations at that low level. So the MIM DRAM papers try to solve those two approaches using a really simple key idea. So the way that the DRAM is organized, inside the DRAM subarrays, we have other substructures that I didn't mention, which are called METs. And those METs are arrays of 512 rows by 512 columns, which are accessed together to accessing a DRAM row. By breaking that structure into different granularities, so by enable us to individually address each one of those METs, now we have a finer granularity for computation. So instead of have 65,000, we still have the 65,000 bit lines, but now they are distributed into 512 groups of 512 bit lines that we can individually control, and then map the required throughput or the required SIMD parallelism from the application to these groups of 512 bit lines. In this way, we can save throughput and not waste bandwidth and energy for an application that does not have book bitwise parallelism, or have a limited book bitwise parallelism. On top of that, these granularity maps really nicely to the granularity of SIMD code from that is generated by auto-vectorizer compilers. So other compilers can automatically vectorize loops depending on the complexity of the loop. So we take that approach, and then based on that, we generate let's say SimDRAM-like code automatically from the user using those auto-vectorizer engines. And on top of all of this, there is a reason why MIM DRAM is called MIM DRAM. All of this gives us a new opportunity. Since now we have some DRAM portions of the DRAM array that are doing computation, and some portions of the DRAM array that are idle, we can collocate different operations across the DRAM array concurrently, so we can accelerate applications in the multiple instruction, multiple data way. So we also provide the hardware support to do that computing orchestration efficiently. So I'm really excited to talk about PIM DRAM in the upcoming HPCA conference, and soon, hopefully, the paper is going to be available in our websites. And if you are curious about it, just send me an email. I'll be glad to talk about it.
Okay, great. Yeah, thank you very much for the summary. Also,
thanks, Juan.
Yeah, really looking forward to learning more about that work in the upcoming HPCA.
Thanks
Thank
a lot.
you for your participation, Geraldo. You are welcome to stay in the tutorial. Now we are going to switch gears. We are going to move to back to processing near memory, and we are going to talk about what current processing near memory systems can do for different applications that we are implementing on the UPMEM PIM architecture. Yeah, the title of this lecture is Accelerating Modern Workloads on a General Purpose PIM System. And as I said here, we are going to provide a summary of different works that we have been doing recently on accelerating workloads from the UPMEM PIM architecture. And this is important for sure, because we need to develop new applications. We need to develop a new software for processing in memory systems. And this is one of the potential barriers for adoption that Geraldo mentioned in the initial talk of this tutorial. And we will briefly talk again about these barriers in the next lecture. Over the past several years, we have been doing a lot of work on benchmarking and workload suitability of the UPMEM PIM architecture. And this is what, the first work that we carried out was the PRIM benchmarks. It was an large set of workloads, 16 in totals, workloads from different domains like sparse, dense and sparse linear algebra, databases, data analytics, graph processing, neural networks, bioinformatics, etc. With all these workloads, we evaluated the UPMEM PIM architecture to check what was the suitability of these workloads for the suitability of this real PIM system for modern workloads. All the workloads that we evaluated fall in the memory bound area of the roofline. So that's why, in principle, they were good candidates for processing in memory, as well as they had different characteristics in terms of diversity. They have different memory access patterns, operations and data types, and also communication and synchronization needs. In fact, in terms of communication, they use different primitives for intra-DPU synchronization or communication, but also different ways of doing inter-DPU communication. And remember that this is important to evaluate in the UPMEM system because there's no direct communication channel. The result of this was the PRIM benchmark suite. It's publicly available and it has been widely used in further research works. One thing that I would like to do is to jump into more, let's say, specific analysis that we did with these UPMEM, with these PRIM benchmarks, such as, for example, the comparison to CPU and GPU. For example, in terms of comparison to CPU and GPU, we found that there are more PIM-suitable workloads, less PIM-suitable workloads, or less UPMEM-suitable workloads, and that show different characteristics in our analysis. We evaluated two different UPMEM systems, one with more than 2,500 DPUs, the other one is a smaller one with only 640 DPUs. And the first observation here is that both PIM systems outperform the CPU for all workloads except three of them: SPMB, BFS, and NW. And it's for different reasons. In the case of SPMB, it's because the implementation of SPMB that we created uses floating point data type, and floating point is not natively supported by the UPMEM hardware. So that's why, because it's emulated, this floating point operation is emulated, the performance is so far from the performance of the CPU and, of course, of the GPU as well. In the case of BFS and NW, Needleman-Wunsch, the main reason is related to the inter-DPU synchronization. There is a lot of back and forth communication between the PIM cores, the DPUs, and the CPU, and this is what made them performance go down due to all the necessary inter-DPU communication. But still, both PIM systems were able to outperform the CPU by 93 times and 27.9 times for 13 of the PRIM benchmarks. Well, we also compared to the GPU. In this case, we compared to an NVIDIA Titan V GPU. And what we observe is that 10 of the PRIM benchmarks outperformed the GPU by an average of 2.54 times. And even the smaller PIM system with only 640 DPUs, the performance of the workloads, these 10 PRIM benchmarks is within 65% of the performance of the GPU. These are observations that I already mentioned in the beginning of in the second talk of this tutorial about what are the three key characteristics that make a workload more suitable for the UPMEM PIM system: streaming memory accesses, no or little inter-DPU synchronization, and no or little use of integral multiplication, integral addition, or floating point operations. So those are the main characteristics that a workload needs to have, or implementation needs to have, in order to get the most of the UPMEM PIM architecture. And based on this initial analysis, we continue doing studies of the suitability of different workloads to the UPMEM PIM system. The next important workload that we targeted in much more detail, as we did in the previous work, is sparse matrix vector multiplication. Sparse matrix vector multiplication is a very good candidate for processing in memory systems because it's a highly memory-bound kernel, as we can observe in the roofline model. So that's why we wanted to evaluate this PIM system, this application and on real PIM systems. We perform a comprehensive analysis of SPMB on the first commercially available PIM system, which is the UPMEM PIM system, implementing 25 SPMB kernels for different compressed matrix formats, different data types, different partitioning techniques, and also different load balancing and synchronization approaches. And we also tested for many different operations, like for example, for many different sparse matrices, 26 sparse matrices, and compared to the CPU and the GPU state-of-the-art systems. I'm not going to go into the details of this sparse P work because we have covered it extensively in prior lectures and also in prior tutorials. But I would like to, show you some, let's say, more relevant analysis. Something that I consider pretty interesting when comparing to a CPU and a GPU is that the PIM system achieve a significantly higher fraction of the peak performance of the system itself. If we compare that to CPU and GPU, we see that they are not even able to reach 1% of the peak performance, which clearly shows that these PIM systems, which clearly shows that these it clearly shows that these conventional processor-centric systems, CPUs and GPUs, are not nicely designed for sparse computations such as SPMB. However, the UPMEM PIM system is able to achieve up more than 50% of the peak performance that the DPUs can provide. And that's, I think, extremely relevant outcome, or extremely relevant takeaway of our analysis. So yeah, that's with respect to sparse P. As I said, if you are interested in this work, well, in this slide, you have a link to a longer talk delivered by Cristina Gianola, Dr. Cristina Gianola, who is the first author of the sparse P paper. But as I said, in prior works, in prior tutorials, we have also had lectures from her. Now I'm going to focus on something different, a different type of workloads. These are machine learning training. Is something that we presented this year at the ESPAS conference as an experimental evaluation of machine learning training on real processing in memory systems. In this slide, you can find the link to the paper, to the source code, and also to a lecture about this this work, PIMML. It's called PIMML for short. For the executive summary, let me start with the executive summary. Training machine learning algorithms is computationally expensive because it's frequently memory bound and requires to repeatedly access large training data sets. Memory-centric computing systems, or systems with processing in memory capabilities, can alleviate this data movement bottleneck. These some real-world PIM systems that we are talking in which in this tutorial have already been manufactured and commercialized. UPMEM is the first one of them. So the goal of this work was to understand, or try to understand, what's the potential of modern general-purpose PIM architectures to accelerate machine learning training. Main contributions of our work are the PIM implementation of several classic machine learning algorithms. In particular, we targeted linear regression, logistic regression, decision tree, and k-means clustering. The workload characterization in terms of quality, performance, and scaling, and the comparison to their counterpart implementations on processor-centric systems, CPUs and GPUs. For the summary or highlight of results, the PIM version of Decision Tree is 27 times faster than the CPU version and 34% faster than the GPU version, and the PIM version of K-means is 2.8 times and 3.2 times faster than the CPU and the GPU versions respectively. Our source code is publicly available in our repository, and as you will see, we perform an evaluation on a real-world processing in memory system with 2,524 PIM cores. Outcomes of our work are key observations, takeaways, and recommendations for ML workloads on general-purpose PIM systems. So this is the outline of this talk, or this part of the talk. First of all, we are going to talk about very briefly machine learning workloads and what are their characteristics. Then we will talk about processing in memory systems, PIM implementation of the ML workloads that we targeted, and finally the evaluation with quality metrics, analysis of PIM kernels, performance scaling, and comparison to CPU and GPU. So as I said before, machine learning training needs to access large amounts of data, and this is a computationally expensive process that requires many training iterations. The main problem is that there is a lot of data movement between the memory and the processing elements, and sometimes the amount of computation is not enough to amortize the cost of moving the training data to the processing elements. There is a low arithmetic intensity, low temporal locality, and sometimes irregular memory accesses. So that's why our goal in this study is to study and analyze how real-world general-purpose PIM can accelerate machine learning training. And in order to do so, we chose 4 representative ML algorithms: linear regression, logistic regression, decision tree, and K-means. And as the roofline model shows, these 4 workloads fall in the memory bound area of the roofline. About processing in memory, there is not much to say. Remember that we are targeting real-world PIM architectures with some common characteristics. There is a host processor, there is a PIM memory with multiple PIM processing elements. These PIM processing elements are relatively wimpy, but we have many of them, so we need to exploit parallelism, and they typically need to communicate via the host processor, and this might be a problem for some applications. So that's why this is one of the things that we wanted to evaluate for the ML workloads. In particular, we focused on the UPMEM PIM architecture. Remember that this UPMEM PIM architecture deploys general purpose processing cores called DRAM processing units, or DPUs. These are fine-grained multi-threaded. They can run up to 24 PIM threads, and they support 32-bit integer arithmetic, but they don't support natively multiplication or division or floating point computations. Remember as well that the UPMEM PIM system, or the UPMEM PIM cores, they have DRAM memory bank that is called MRAM of size 64 megabytes, and a scratchpad memory of size 64 kilobytes that is called WRAM. This is how the system looks. You have already seen this picture before, the dual socket CPU with the DRAM DIMMs and PIM enabled DIMMs. So now let's talk about the PIM implementation of the machine learning workloads that we have used: linear regression, logistic regression, decision tree, and K-means clustering. And they are diverse in terms of memory access patterns, computation pattern, and communication and synchronization. For linear regression, which is a supervised learning algorithm where the predicted output variable has a linear relation with the input variable, we have used gradient descent as the optimization algorithm. In our PIM implementation, what we do is dividing the training data set equally among the PIM cores. The host sends these parts of the training data set to the different PIM cores or DPUs in the UPMEM PIM architecture that we are going to use. And then inside each of the PIM cores, we have PIM threads. Remember that the name of the PIM threads in the UPMEM architecture is tasklets. We compute dot products of row vectors and weights. And then each dot product result is compared to the observed value y to compute a partial gradient values. these partial grading values are then sent to the host for final reduction, and we continue next with the next iteration. We generated 4 versions of linear regression. The first one is training data sets of 32-bit real values. Second one uses the same training data sets, but in this case, we are using a fixed point representation of 32 bits values. And then we have a version that uses hybrid precision. It starts computing with 8-bit values and then moves to 16 and then finally 32-bit values. And we also have a hybrid version that uses custom multiplication that is based on the 8-bit multiplication that the PIM cores can execute. This custom multiplication, by the way, is in this slide. I'm not going to go into the and all the detail. I will leave this slide for your own study if you are interested. But here we are basically comparing the default integer multiplication that is generated by the compiler with to a custom integer multiplication that we generated using these built-in operations. And as we see, it ends up being a lower number of instructions, so we can hopefully expect some performance improvement from using it. This custom multiplication is based on the knowledge that we are using a hybrid implementation, so we know what's the precision that we need for each of the quantized values that we are using. For logistic regression, also supervised learning algorithm, which is used for classification. In this case, we use sigmod as a function to map predicted values to probabilities, and our PIM implementation follows a very similar approach to linear regression in the way that we partition the training data set and distribute the computation over the PIM cores and the PIM threads. In logistic regression, however, we have 6 versions. The first one uses training data sets of 32-bit real values, and in this case, sigmoid is approximated using Taylor series. Second one also uses Taylor series, but in this case, we use a 32-bit fixed point representation. The next version uses lookup tables. So instead of computing sigmoid with the Taylor series, we compute sigmoid with a lookup table. And this lookup table might be in MRAM. And remember that this is the DRAM bank, the PIM DRAM bank, and or it might be in the WRAM if it fits, which is the scratchpad of the PIM cores. We also have a version with hybrid precision, same as in linear regression, and also a version that uses the same custom multiplication. With regards to the LUT-based sigmoid calculation, we take advantage of the fact that sigmoid is symmetric, and basically what we are doing is storing either in MRAM or in WRAM certain values that might be needed for the computation of sigmoid, and hopefully accelerate the performance in this way. A good thing is that the sigmoid, the lookup table-based sigmoid that we are using is, or the lookup table is relatively small, is about 40 kilobytes, so it can fit in WRAM, and gives us the possibility of evaluating both implementations in MRAM and in WRAM. The next workload is the decision tree. The decision trees are tree-based methods used for classification and regression. In this case, our PIM implementation partitions the training data set among the PIM cores, and then each PIM core computes partial gene scores to evaluate the host's split decisions. The host sends commands to the PIM cores, and these commands might be a split commit or split evaluate or min-max to query the minimum and maximum values of a feature in a leaf tree. Important optimization for decision tree is to use the proper data layout in order to maximize memory bandwidth with the streaming memory accesses. And this is something that we already knew from our prior work, where we observed that the most well-suited workloads for the UPMEM PIM architecture were those with the streaming memory accesses. So yeah, By using streaming memory accesses, we can accelerate the split commit and also split evaluate. And finally, K-means clustering, an iterative clustering method that is used to find groups in a data set. In our pre-implementation, again, we distribute the data set over the PIM cores, and then PIM threads are going to evaluate what's the closest centroid to each point in the training data set. To do so, we require a counter and accumulator per coordinate and per centroid. And after the PIM cores and the PIM threads have gone over all the data points in the training set and evaluating how close they are from the different centroids, the host gathers this information and recalculates the centroids. At some point, there will be convergence to a local optimum when the updated centroids coordinates are within a threshold. And now let's go with the evaluation. So first of all, we have used synthetic and real data sets for the different experiments that we perform. We evaluate an UPMEM PIM system with more than 2,500 PIM cores, an Intel Xeon CPU, and an NVIDIA A100 GPU. In this case, we evaluate quality metrics, performance of PIM kernels, performance scaling, in comparison to CPU and GPU. This is the UPMEM PIM system that we have used in our evaluation. And let's first go with the quality metrics. For linear regression, as you can see here, the training error rate flattens after 500 iterations for the different implementations. Remember that we had 4 different versions. One interesting observation is that the training error rate of the version that uses real numbers is the same as the CPU version. For the integer versions, the training error rate increases, but it still remains low and close to that of the version that uses real values. For logistic regression, again, the training error rate of the version that uses real numbers is the same as the CPU version. For the other versions that use 32-bit integers, they obtain obtain lower training error rates than so the versions that use lookup tables obtain lower training error rates than the version that doesn't use Taylor series, because the Taylor series are approximations. And then we see that there is relatively large loss in accuracy or increase in training error rate for the versions using hybrid precision. However, it depends on the number of decimal numbers that we need to use. For example, in this case here, where we only need 2 decimal numbers for the data sets that we use, we see that the training error rate is significantly lower and closer to what we have observed in the versions with 32 bits. Then for decision tree, we observe training accuracy that is only slightly lower than that of the CPU version. And for K-means clustering, kind of the same thing when we compare PIM and the CPU versions. They have same scores, and this basically represents that we are able to maintain the accuracy of all workloads, or at least keep it close to the CPU baseline. Now let's take a look at the analysis of PIM kernels. For linear regression, one first observation, and we will go back to this later, is that all versions saturate 11 or more PIM threads, and the fixed point representation accelerates the kernel execution by an order of magnitude over the version that uses 32-bit floating point numbers. This is something that we could expect because floating point numbers or computational floating point numbers is emulated is significantly worse than operating on integers. That is the data type that we are using for the fixed point representation. So first key takeaway is that workloads with arithmetic operations or data types that are not natively supported by the PIM cores run at low performance due to instruction emulation. So one recommendation is to use fixed point representation without much accuracy loss if the PIM cores do not support floating point. We also observe for linear regression that there is a significant speed up for the hybrid version of over the 32-bit integer version, and this is because we are able to use the we are able to read less amount of data from the memory, so quantization and hybrid precision are producing significant performance improvement. Another recommendation here is to use native instructions as much as possible, and this is what we observe when we use the built-in functions, when we use the custom multiplication that we implemented that provides a 25% additional speed up. For logistic regression, we see that there is very high kernel time for the two versions that use sigmoid approximation with Taylor series, and we see very interesting speed up when using lookup tables, more than 53 times faster than the versions that use the approximation. So one recommendation for PIM systems is to convert computation to memory access by keeping pre-calculated operation results in memory. There is additional performance improvement from the hybrid version and from the version with the custom multiplication, as you can see in the slide. And there is one common observation to all these workloads and all the different versions that we implemented is that in all cases, the performance of all kernels saturates at 11 or more PIM threads. In the UPMEM PIM architecture, this means that we keep the entire pipeline busy, and this way the pipeline latency can hide the memory latency. All these kernels are compute bound on the UPMEM PIM architecture, and this is the outcome from the prior observation. If the pipeline latency hides the memory latency, that means that the workload is compute bound on the UPMEM PIM architecture. So ML workloads that are memory bound due to low arithmetic intensity in CPU and GPU become compute bound when running on PIM. One recommendation that stems from that takeaway is that we should maximize the utilization of the PIM cores by keeping their pipeline fully busy. Now let's take a look at some performance scaling results. We did strong scaling and weak scaling analysis. For example, for weak scaling, we analyzed the performance for inside an entire rank of DPUs from 1 to 64 PIM cores. And one thing that we can observe is that for linear regression, logistic regression, and decision tree, we see linear scaling with a number of PIM cores. That's why it's weak scaling, right? So that's why we see that the execution time in all these plots here is basically flat. However, for k-means, that's not the case. And the point here in k-means is that we see that the total execution time goes down when we increase the number of DPUs, but this is because we have larger data sets, and when we have larger data sets, k-means also converges faster, converges with fewer iterations. So that's why we observe this behavior here. Interestingly, the sum of all data transfers that need to happen, remember, through the host CPU takes less than 7% of the total execution time in all cases. So these workloads are can pretty well tolerate what's the cost of moving the data from the main memory to the PIM memory, and also moving data between PIM cores when inter-PIM core communication is needed. We also did analysis for strong scaling, and we can see similar observations here. The first one is that we see basically that kernel PIM time, the PIM kernel time scales linearly with the number of PIM cores, and there is little overhead from the inter-PIM core communication and the communication between host and PIM cores. And only in k-means, it's a little bit noticeable here, but still maximum number of PIM cores performs the best. So key takeaway number 3 is a machine learning training workloads, which need large training data sets, benefit from large PIM-enabled memory with many PIM cores. And even if the PIM cores need to communicate via the host processor, the amount of data movement needed for intermediate results is tolerable. Finally, let's take a look at the comparison to state-of-the-art CPUs and GPUs. For linear and logistic regression, we can see that CPU is relatively easy to outperform, not the same for the GPU. The problem is that the PIM versions are heavily burdened by those operations that are not natively supported. For example, the integer multiplication or the floating point computations. Let's say positive side of this slide is that at least the different optimizations that we applied improved significantly the performance of the PIM implementations and closed the gap with the GPU performance. Results are more positive for CPU and GPU. So with respect to the comparison to CPU and GPU, when we compare decision tree and k-means, and as you can see in the slide, the PIM version of decision tree is 27 times faster than the CPU version and 1.34 times faster than the GPU version. The PIM version of k-means is 2.8 faster than the CPU version and 3.2 times faster than the GPU version. In the long version of our paper, you can find additional analysis. For example, the analysis that we did using a significantly larger data set, the Criteo 1 terabyte data set for both decision tree and k-means. Because the data set is larger, in the case of decision tree, we ended up obtaining the best performance with a larger number of PIM cores, and this allowed us to see or to obtain more speed up in the comparison to CPU and GPU, like 62 times faster than the CPU and 4.5 times faster than the GPU version of decision tree. However, for k-means, because for the previous data set, the Higgs boson data set, we were already obtaining the best results of the PIM system with the largest number of PIM cores. The speedups for the Criteo dataset are more or less along the same lines. So key takeaway number 4, ML workloads that require mainly operations natively supported by the PIM architecture, such as decision tree and k-means, they can outperform the CPU and GPU counterparts. As I said, you can find many more details in the extended version that is in archive. There is also a shorter version with just the key takeaways that you can find as well in archive, and this is the version that we presented in ISPAS 2023. This source code, as I mentioned before, is publicly available in our repository. So for an executive summary, again, we wanted to evaluate what's the potential of modern general purpose PIM architectures to accelerate machine learning training. As we said, machine learning training is suffers from the data movement bottleneck because there is a need frequently or repeatedly accessing large training data sets. We have contributed in this work with the PIM implementation of several classic machine learning algorithms, workload characterization, comparison to CPU and GPU, and evaluation on a real PIM system, out of which we came up with some key observations, key takeaways, and recommendations. You can check a longer version of this lecture in our PIM course, and yeah, that's one of the works that I wanted to cover today. Another thing that I wanted to talk about is the work we did on genomic sequence alignment, this high throughput sequence alignment using real processing in memory systems that we presented, or it's published in the Bioinformatics Journal. Here you can find links to the archive versions of the paper and also the source code. For an executive summary, genome sequence alignment is typically memory-bound on conventional processor-centric systems like CPUs and GPUs, but processing in memory has the potential to overcome this data movement bottleneck by placing compute capabilities near or inside the memory arrays. In this work, we presented Alignment in Memory, a PIM framework for genome sequence alignment on general-purpose PIM systems. AiM, the alignment in memory, supports multiple alignment algorithms like the Needleman-Bunch, the Smith-Waterman-Goto, GenASM, and the Wavefront algorithm. And it's implemented for the UPMEM PIM architecture. In our evaluation, as you will see, we showed that sequence alignment on processing in memory can be significantly faster than on CPUs and GPUs. So let's just start with a little bit of background and motivation. Sequence alignment on CPU. Next, processing in memory as a promising technique to alleviate the data movement bottleneck. Then I will talk about how alignment in memory or framework works. And finally, the evaluation. So genome is the complete set of an organism genetic instructions. The DNA is composed by a string of base pairs A, C, G, and T. In total, the human genome contains 3.2 billion base pairs. And the goal of genome analysis is to understand genetic variations, predict the presence or abundance of microbes, monitor disease outbreaks, develop personalized medicine, etc. The problem with sequence alignment, or the need for sequence alignment, is that sequencing machines only provide randomized fragments of the genome of a person or another living entity. And we need to map these fragments that are called reads to the reference genome. There are different sequencing technologies. Some of them provide shorter reads, others provide long reads. In the end, sequence alignment is necessary in all cases. Over time, several algorithms have been developed. There are popular ones that are quadratic time dynamic programming algorithms, such as Smith-Waterman or Needleman-Bunch. But there are also more modern, fastest algorithms like GenASM, WFA, and WFA Adaptive. For an example, I'm going to talk briefly about the Smith-Waterman. In a Smith-Waterman, the goal is basically to create a scoring matrix that we use to compare two sequences A and B. In each element of the scoring matrix, we calculate a similarity score based on what's the, so we calculate the value, the corresponding cell of this scoring matrix based on a similarity score that compares the specific elements of the two sequences that correspond to this cell here, and we make use of the neighboring cells as well. So if these two cells are the same, so if the two characters that we are comparing are the same, we will add the similarity score. If they are different, we will subtract with respect to this element in the previous anti-diagonal, and we will also check the elements at the top and at the left, and we'll apply a gap penalty and compare to 0 as well. So basically, we use this formula here to obtain each element of the scoring matrix. When we compute the scoring matrix, as we can observe here, we need to make use of the the two previous anti-diagonals, and by using the two previous anti-diagonals, we can compute each diagonal and make progress when computing the scoring matrix. After we have the scoring matrix, we have to perform an operation that is called traceback in order to figure out what's the exact comparison, the exact similarities and differences between the two sequences that we are aligning. So as we see, this process just requires very simple computations, just comparisons, additions, or subtractions. But at the same time, we need to access large amounts of data from memory because the sequences, there are many sequences for sure, and sequences might be very long as well. But we also need to access the table itself or parts of the table itself. And this is something common in different sequence alignment algorithms like Needleman-Bunch, Smith-Waterman-Goto, Hynix AiM, or the wavefront algorithm. So what's the problem with all these algorithms is that when we run them on CPUs, the execution time tends to saturate, even though we might increase the number of cores that we use and the number of CPU threads that we use. And that's something that we have observed in our analysis, in our study. As you see here, execution time for the 4 different algorithms that I presented in the previous slide, including a version of WFA that is called WFA Adaptive. In all cases, when changing the number of threads from 1 to 48, what we see is that the execution time tends to go flat, meaning that performance doesn't scale anymore. Performance tends to saturate when the number of threads, CPU threads, grows. And this can be explained because as the number of threads grows, the IPC, the instructions per cycle that these CPU threads can execute, decreases. So threads spend more time being idle. And this mainly happens because when the number of CPU threads grows, the threads spend more time waiting for memory. There is a memory bottleneck, and the more threads we have, the more we have to wait until the data comes from memory. So processing in memory is a good way of alleviating this data movement bottleneck. Instead of accessing data, instead of using CPU cores where we access the memory banks through a narrow memory channel, we can have direct access from PIM cores to the DRAM banks, and this way have a much larger aggregated bandwidth. We take advantage of that in alignment in memory, which is our framework for sequence alignment on PIM systems. Alignment in memory supports the algorithms that we have already presented before: Needleman-Bunch, Smith-Waterman-Goto, Hynix AiM, and the wavefront algorithm. And there are several steps in this framework for sequence alignment on PIM systems. First of all, we need to get the sequences. They might be coming from somewhere else. They might be coming from the storage, and we need to load them first in the main memory of the host CPU. So that's the first thing that the CPU is going to do, is reading the sequence pairs from an input file and storing them in main memory. Next, the CPU transfers the sequences to the PIM cores, to the MRAM banks of the different DPUs. So the sequence pairs are evenly partitioned across PIM cores and transferred to the DRAM banks in the PIM DIMMs. And next, in each PIM core, we will have several PIM threads that will perform different sequence alignments. So it's a, let's say, embarrassingly parallel approach where each thread can work independently and there is no need for inter-thread or inter-PIM core synchronization. So inside each PIM thread, the thread is going to first copy a sequence pair from the DRAM bank to the scratchpad using the DMA transfers that we discussed before in the second lecture of this tutorial. And then the threads align the sequence pair and extract the alignment operations using traceback. Then, when the threads are done with that, write the alignment score and the operations to the DRAM bank over a DMA write transfer. And finally, once the execution on the PIM cores has finished, the host CPU reads the alignment score and the operations of each sequence pair. And finally, the CPU can write the alignment results to an output file if that's the desired. So something interesting is we have 2 different implementations depending on whether we can fit all the necessary data structures in the WRAM, in the scratchpad, or not. There is one approach that uses WRAM only for intermediate data structures, but this scratchpad or WRAM is fast, but it has limited capacity. So at some point, larger sequences need larger intermediate data structures, such as the scoring table in the Smith-Waterman algorithm, or the wavefronts in the other algorithms that are the wavefront algorithm, for example, and these may limit the number of concurrent PIM threads. So the other approach to avoid that, we need to reduce the number of PIM threads, and at some point we could not use even a single PIM thread, is to use WRAM and MRAM for the intermediate data structures. So we use the scratchpad as a data cache, as a software, as what exactly is a programmable or a software-based cache. So we load these data structures on demand, and on average, the latency is going to be longer because we need to go to MRAM to load the pieces of the intermediate data structures that we need, but at least we ensure that we can run more concurrent PIM threads in all cases. For WFA and WFA adaptive, they use intermediate data structures that are of varying size. These are the wavefront components, so they require dynamic memory allocation. However, the memory allocator that the UPMEM SDK provides is not great, and is shared across all PIM threads. So we designed a custom per thread memory allocator for low overhead dynamic memory allocation. Now let's take a look at the evaluation. We have used real and synthetic data sets for the different analysis on an UPMEM PIM system, and 3 CPU systems with different characteristics. As you see, they have different number of threads, but interestingly as well, they have different sizes of the L3 cache. And let's take a look at the results. First of all, the analysis or the evaluation on the 3 CPU systems for the 4 different algorithms, including the 2 versions of the WFA. One interesting observation is that the CPU system with the largest L3 cache is performing the best, is the fastest one, and these definitely align, even though it's not the one with the larger number of cores. But this definitely highlights the fact that these sequence alignment operations are memory bound. Now, when we compare to CPU, so we compare to the PIM implementations, we have a first comparison that the execution time that you see now in the slide for the different algorithms includes CPU PIM and PIM CPU transfers, and we can see that the PIM system outperform the CPU systems in the majority of experiments. But if we don't take into account the PIM CPU, CPU PIM transfers, we will see significantly higher speedups, more than 25 times for WFA and more than 28 times for WFA adaptive. So hopefully there will be a future PIM system where the PIM DIMMs can be used as main memory, and this way we will save all this data, all this time from the transfers from the CPU to PIM and vice versa. Or at least there will be a PIM system where we can overlap data transfers and computation. That means having the CPU transferring data, or transferring, in this case, sequence pairs from the main memory to the DRAM banks, while at the same time the PIM cores are computing. We have additional observations for the algorithms that have more regular access patterns. That's the case of NW and SWG. PIM does not outperform CPU for those algorithms when they are using a small read lengths. But that's because typically, well, the cache hierarchy of the CPUs and prefetchers are working pretty well. However, yeah, for WFA and WFA adaptive, there are some additional observations for very large read lengths. In this slide, you see the execution time for read lengths of 5,000 and 10,000 base pairs for different edit distance values. And one thing we see is that PIM continues to outperform the CPU systems for large read lengths. Only scalability is a problem at some point when it's limited by the actual WRAM capacity. Yeah, there are possible software solutions for even larger sequences, but the easiest solution for sure will be to have future PIM cores with larger WRAM capacity. And we also compared the WFA algorithm to the state-of-the-art GPU implementation of this algorithm, and we see that PIM outperforms the GPU in a majority of experiments. We have some additional results here for intermediate data structures. For large data structures that are those used in NW and SWG, WRAM only does not scale. As you see, at some point we cannot evaluate larger reads when in the WRAM only implementation, and even if we can evaluate them, it's with a limited number of PIM threads. As you see, this number here, 1, represents the number of PIM threads that we used. Remember from our prior part of the talk where we mentioned the need for filling the entire pipeline, so using as many PIM threads as possible, or at least more than 11, which is the minimum number to keep the entire pipeline busy. For algorithms with small data structures like GenASM, for example, WRAM only is always better, so there is enough WRAM for all the threads that are running there. And for medium-sized data structures, such as those in WFA and WFA adaptive, WRAM only is better for short reads, but when the reads tend to be longer, it's better to go with the WRAM plus MRAM approach that we explained before. You can find many more details in the paper published in Bioinformatics this year, and the code is also publicly available, as you can see. So this is one more example of the promises of processing in memory for different applications, for different modern workloads, for example, these sequence alignment algorithms. And you can watch a longer version of this lecture as well from our PIM course. Well, another thing that we covered, or another work that we have recently targeted, is transcendental functions. Why is this necessary? And this was also presented in ISPAS 2023 this year. Why is this necessary? It's necessary because the current real-world processing in memory systems have very constrained hardware. So this results in limited instruction sets and makes very difficult or impossible to evaluate certain operations, for example, transcendental functions or other hard to calculate functions such as a square root. That this is something that Geraldo in the previous talk also mentioned. When he talked about the Pluto proposal. It's difficult to have your complex operations in DRAM, either if it's near memory or if it's using memory. So in this work, we wanted to come up with some solution to be able to perform transcendental operations and other hard to calculate operations on general purpose PIM systems. And this is TranspIM-lib, which is a library for transcendental and other hard to calculate functions. As you will see, TranspIM-lib is based on CORDIC and LUT-based methods for trigonometric functions, hyperbolic functions, exponentiation, logarithm, square root, etc. Our source code is publicly available, and we implemented the first version of TranspIM-lib for the UPMEM PIM architecture and evaluated it comprehensively in terms of performance, accuracy, memory requirements, and setup time. And also with 3 real-world workloads, Black-Scholes, Sigmoid, and Softmax. This is the outline, very brief introduction to PIM and the transcendental functions. Then we will talk about the TranspIM-lib, or library for transcendental and other hard to calculate functions, and finally the evaluation. So how do we calculate, or how should we calculate transcendental functions in a PIM system? In principle, we can see 3 possible alternatives here. The first one would be ideal one, to have a transcendental function executed on a special PIM unit or a special PIM transcendental unit, where if we have a PIM kernel running on a PIM core and we eventually need to execute some transcendental function, we just send the relevant data to the transcendental unit, perform the transcendental function there, and then we continue running on the regular PIM core, let's say. Second possibility, more realistic because it's unlikely that we'll have this transcendental unit, is to send data back to the CPU, perform the transcendental function there, and then from there go back to the PIM kernel if it's possible to continue the execution on the PIM cores. The last possibility, and this is what this work is about, is emulate the execution of the transcendental functions in the PIM cores themselves. And we hope that we'll be able to save time from the saving time from the data movement from the PIM cores to the CPU and vice versa. So this third option is TransPIM-lib, an open source library with Cordic and loop-based methods for trigonometric functions, hyperbolic functions, exponentiation, logarithm, etc. So let's talk a little bit about TransPIM-lib. As I mentioned, there are different ways of calculating transcendental functions. For example, in the work that I explained before, for machine learning workloads, the first thing that we tried was approximation with Taylor series, but there are other ways of doing them that can be more efficient. For example, Cordic, which is an iterative method that uses bit shifts, addition, and table lookups. In its rotation mode, Cordic computes the function value for an input angle by rotating a vector iteratively. And this rotation is done by multiplying the vector and a matrix. The matrix represents the rotation algorithm, the rotation angle, which decreases in each iteration. The other possibility that we also explore in this work is the use of FASTC lookup tables that will return an approximate output for each possible input. In this case, we have first to use a function that is called a of x that returns an address to access the loop, returns the index that we need to access the lookup table, and when accessing the table, we will obtain is the content of the lookup table for that index, which approximates the real result for the input x. To generate the lookup tables, we also use a helper function, which is basically the inverse of the address function a. And when using LUTs, we can also improve their accuracy by using interpolation. And this is something that we have explored in this work as well. So first, with respect to the Cordic-based methods, we have in TransPIM-lib Cordic implementations of trigonometric, sine, cosine, tangent, hyperbolic, also sine, cosine, and tangent functions, and exponentiation, logarithm, and square root. For an example, the sine function, we first need to perform a range reduction in order to restrict the range of inputs from 0 to 2 pi. Then we perform a floating point to fixed point transformation. Then we further reduce the range. Specifically for sine, we can do this because the values in each quadrant, the results in this quadrant are the same. So here we restrict the inputs from 0 to pi over 2. Then we perform the Cordic computation, and then by using the quadrant that we stored separately, we can obtain the final result finally when transforming from or moving from fixed point to floating point representation again. For the LUT-based methods in TransPIM-lib, we have tried different LUT-based methods. The first one is multiplication-based. In this case, we have a regular spacing between table entries. This is the expression or the formula that we use for the address function, where k represents the LUT density. For example, if we want to map the interval 0 to 5 to a 12-entry lookup table, we would have something like this, representing the density and the inputs here. Another possibility is to call what we call the LDX-based lookup table. In this case, we replace the multiplication with multiplications by powers of 2. This results in less precision, but avoids the multiplication. Remember that the multiplication is very costly in real PIM systems, such as the UPMEM PIM architecture. So this is the expression that we use for the address calculation. So in this case, the density is lower, as you can see, but we can in principle extend the range. Another possibility that we explored as well here is a direct float conversion-based dilute. In this case, A of x uses the last m bits of the exponent and p bits of the mantissa, and this results in a piecewise linear density of 2 to the n steps of 2 to the p addresses. The problem with this dilute is that there is a gap here, as you can see. So that's why we also try combined methods. For example, the direct conversion plus LDX-based LUT is called DLUT. In this case, we use an LLUT between 0 and the smallest exponent, and a DLUT for the larger inputs. And we also have another combined method, Cordic plus LUT, that replaces the first few iterations of Cordic with a lookup table in order to accelerate the execution. And this provides a flexible trade-off between computing cost, table size, and precision. These are the functions that are supported in TransPIM-Lib. We base our preliminary analysis in SIGN. We implemented all methods for SIGN, and then based on that, we implemented the methods that we expected to be most suitable for the rest of supported functions. Now we can take a very brief look at the evaluation. PIM system that we have compared to, we also use that we have using in the analysis. We have compared to a dual socket Intel Xeon CPU, and we have micro benchmarks for performance evaluation, measuring the execution cycles, accuracy evaluation with the root mean square absolute error. We also measure the setup time, which is the time to generate whatever needs to be generated in the host CPU and then transferred to the PIM side, for example, generating lookup tables in LUT-based methods, and memory consumption. Those are the tables and variables that we allocate in the PIM cores, in the DRAM banks of the PIM cores. In our analysis, we have used SIGN as the representative function in the next slides, as you will find, but also we have real-world benchmarks such as Black-Scholes, Sigmoid, and Softmax. So let me show you some results first. For the in terms of performance, we have measured the execution time, and as you see in this plot, we are representing the execution cycles with respect to the root mean square absolute error. And there are some interesting observations here. First of all, the performance of the LUT-based methods is independent of the accuracy. The fact that we just need to access a table that resides either in the scratchpad or in the DRAM bank is independent of the size of the lookup table. So the larger a lookup table is, the best accuracy we will obtain, but the execution time is basically the same. It doesn't matter if the table is larger or is smaller, we are just accessing one entry in that table. The number of execution cycles specifically depends on the number of multiplications that we need for each of the different methods. For example, for the interpolated MLUT, we need 2 floating point multiplications. For the non-interpolated MLUT and the interpolated LLUT, we need 1 floating point multiplication, and for the non-interpolated LLUT, we need no floating point multiplication. So this explains that the slowest of the LUT-based methods is the MLUT implementation, this line here, while these ones are faster, and the fastest one is the non-interpolated LLUT. What is, the trade-off here is in terms of the accuracy, because the non-interpolated LLUT is non-interpolated, the accuracy cannot be as high as for the interpolated LLUT. As you see, we also have a version of the LLoot that uses fixed point representation, and this can double the performance of the interpolated LLoot. That's the significant reduction in the execution time that we observe here, basically because it's using fixed point representation, and fixed point multiplication or integer multiplication is faster than floating point multiplication. For CORDIC-based methods, for example, one thing that we observe is that CORDIC increases the accuracy in each iteration, but the more iterations, the more execution time we will need as well for the CORDIC methods. The CORDIC plus LOOT method is faster. The red line is faster than the blue line because it replaces the initial iterations with a lookup table query, as we already know. And at some point, more iterations don't really improve the accuracy. One other observation that we see as well is that there is very little performance improvement from using the scratchpad memory or the WRAM instead of DRAM to store the lookup tables. And that's kind of fine. It's kind of a good observation because we likely prefer to use the scratchpad or the WRAM to store all the data. So key takeaway number one is that interpolated LLoot methods, lookup table based methods, and in particular the one that uses this LDX operation offer the best trade-off in terms of performance and accuracy. I don't have time to go into all the details of this work. As you can see, we also have an analysis of the setup time that is also important to take into account. Usually setup time is larger for the LLoot-based methods because we need to create the table and then we have to transfer those tables from the memory of the CPU to the PIM DRAM banks. And also these transfers and the time we need for this setup tends to be longer when the LLoots are larger. So we will see that with the improved accuracy will also imply higher setup times. However, that's not a problem for CORDIC. In CORDIC, regardless of what's the accuracy, the times are flat. We also evaluated in terms of memory, again here, the lookup table based methods. In order to achieve higher accuracy, they will need larger tables as well, where that's not a real problem for CORDIC based methods. And well, there are other supported functions, though we don't have time to go into the details. There are also additional considerations to take into account with respect to range reduction and range extension that might take a few cycles as well for some of the methods, and also other methods that are not so let's say evaluated in so much detail in this presentation, like DLoot or DLoot, that are pretty nice for hyperbolic tangent or for GELU. And finally, you can find the comparison to a CPU, to a baseline CPU for Black-Scholes, sigmoid, and softmax. We really see performance improvement with respect to Black-Scholes, not that much for sigmoid and softmax if we stick to the, say, raw performance of the kernel itself. But when we take into account the data movement and this time that we can save from going back to the CPU to perform the transcendental function, as I said in the beginning, we see that we can save a lot of time. Our estimates are that it could be between 6 and 8 times faster than the execution on the host CPU. But you can find many more details in the paper. Just before I finish this lecture, or this talk, I would like to show you one of the most recent works that we have published, because it's on a topic that is also very, I'd say, trending one, homomorphic operations. So this work is titled Evaluating Homomorphic Operations on a Real-World Processing in Memory System, and has been recently presented at the ISWOC symposium. So, well, the scenario that we are considering here is homomorphic encryption being used for users to send data to some central or cloud server that performs operations on encrypted data without decrypting it in order to maintain the security and the integrity of data. And the encrypted results are sent back to the users where in the local machine where the result will be decrypted. But the problem with homomorphic encryption and with homomorphic operations is that they suffer from large memory capacity and data movement bottlenecks. So we are doing research, the community is doing a lot of research on acceleration techniques. However, approaches that we have seen so far face challenges in resource limitations, data movement, and practical implementation. So that's why our goal in this work was evaluating the suitability of real-world general-purpose processing in memory architectures to perform homomorphic operations. And we focus on the UPMEM PIM architecture in order to first evaluate homomorphic addition and multiplication, and then evaluate these operations in the context of statistical workloads like mean, variance, and linear regression, and perform a comparison to CPU and GPU. We have custom CPU and GPU libraries and an optimized CPU library that is called SEAL. I'm going to show you very briefly some results. This is the evaluation of homomorphic addition on CPU, the processing in memory system, the CPU SEAL version, and the GPU version. And interesting observation here is that the homomorphic addition is significantly faster than CPU and GPU versions, providing between 50 and 100 speed up over the CPU, and between 2 and 15 times speed up over the GPU. For homomorphic multiplication, that's not the case. And as you can see, the CPU SEAL and the GPU outperform our implementation on the PIM system. But the key reason for that is that, as you already know, there is no native multiplication support on the UPMEM PIM architecture. And that's why, for example, in linear regression, the results are not that great. The results are better for mean and for variance, as you can find in our paper. But yeah, that's but these are the key takeaways of this work. First of all, the native support of the integral addition allows the UPMEM PIM system to outperform the CPU and the GPU for homomorphic addition. For the multiplication, for the homomorphic multiplication, it happens the other way around, exactly because of the lack of native support, and the computational power of the PIM system, as we observe, scales with the memory capacity because we have more memory banks and we have more PIM cores. So our goal in this work was to evaluate extensive homomorphic operations on a real-world processing in memory architectures. Or contributions are the novel implementation, or the first implementation, of homomorphic addition and multiplication on a real PIM system, the performance evaluation that we did for the two operations themselves, and also 3 real-world workloads, and we generated some interesting key insights with respect to PIM systems and homomorphic encryption. And we perform an evaluation with comparison to CPU and to GPU, and in some cases we see more improvement. In other cases, we see that it would be desirable to have more, I'd say, sophisticated, more capable PIM cores that can run multiplication faster in order to be more efficient for homomorphic operations. Well, this is all for now with respect to this part of the tutorial on accelerating modern workloads on general purpose PIM systems. I wanted to share quickly some of these works that are recently published, and I think that they have some interesting insights and recommendations that people working on processing in memory can find interesting. Okay, yeah, we are consuming our time. We are not going to have a lot of time to go over the next presentation in detail. It's about PIM adoption issues, as you can see in the slide, how to enable PIM adoption. And this is about a lecture. Well, first of all, Geraldo already talked about this in the beginning of today's tutorial about how to enable the processing in memory adoption and different things that need to be done in, for the adoption of PIM in real systems. But there are also like several lectures that we have delivered in the past. So I'm going to point you to some of these so that you can learn more about the different works that are mentioned in this presentation if you are interested on that. Just to be brief, let me recap on what are potential barriers to adoption of PIM systems. First of all, we need applications and software for PIM. That's why we're talking about real workloads or modern workloads and how we can use processing in memory to accelerate them. Another important thing, and this is going to be the topic of the next talk, is ease of programming, interfaces and compiler and hardware support. How can we make processing in memory systems easier to program? There are also system and security support considerations like coherence, synchronization, virtual memory, isolation, communication interfaces. And there are also runtime and compilation systems that are needed for adaptive scheduling, for data mapping, for sharing control and access, and infrastructures as well to assess benefits and feasibility of PIM systems. All of these can be solved, all these different barriers can be overcome with a change of mindset, but this change of mindset requires us to revisit the entire stack. From the problem and the algorithm to the devices and the electrons. We covered these challenges to enable processing in memory in detail in or the book chapter that we have mentioned before. Actually, there is an entire section 8 of this chapter where we talk about all these different topics, and you can find also some of these in the shorter versions of this book chapter. One of the things that we mentioned is the need to access real systems in order to evaluate them, to explore them, and to figure out how we could make them better, how we could make them faster. And that's why that's one main motivation for organizing this PIM tutorial, where we are talking with a lot of detail, or as much as we can, about the real PIM systems such as UPMEM or those prototypes from Samsung, from Alibaba, from SK Hynix, etc. We are also talking about programming models and code generation. I mentioned in lecture 2, or I talked in lecture 2 about how to program the UPMEM PIM system. I'm going to keep talking about how to program the UPMEM PIM system, but using a high-level programming framework that is SimplePIM. That's exactly what I'm going to talk about in 5 minutes. And Geraldo as well talk about how to program a processing using DRAM substrate, such as SimDRAM as well, using SIMD instructions. There are many more things to deal with, for example, scheduling and data mapping. There are multiple works that are targeted that. I would like to briefly mention the PIM enable instructions work, where well, some fine-grained instructions are offloaded to the memory side for computation there, but depending on where the data resides, because data might be in DRAM or might be already in the cache hierarchy of the CPU, we need to have a locality monitor that checks where data resides, and based on that, perform the computation where it makes more sense. Data mapping is also important. Memory coherence is key. This is a word that Geraldo also talked about. Conda is memory coherence protocol for systems with concurrent execution on the CPU and on the PIM cores or the PIM accelerators. Synchronization is also necessary in PIM systems because we needed to design a new way of doing synchronization for near data processing architectures or for PIM architectures, because usually these PIM cores don't have access to a shared level of cache that can be used for synchronization. So that's why the Synchron work that was presented in HPCA 2021 proposes as method passing solution with a specialized hardware support to accelerate the synchronization of PIM cores. But there are some other things that we still need to figure out what to do with them. For example, virtual memory support. There have several works attempting to solve virtual memory, at least for the problems or the specific setups that they were targeting. But for sure, there is more work to do in that direction. Security considerations are important as well. For example, how to share the access to real PIM system with multiple PIM cores that could potentially be accessed by different processes. That's a problem yet to solve. It's not a real problem in the UPMEM PIM architecture, for example, because there is a large number of PIM cores. So what the vendor recommends is that simply each process reserves, allocates its own DPU set, and this way they are working on completely separate cores. That benchmarks and simulation infrastructures are also necessary. That's why in our group, we keep working on generating new benchmark suites. For example, the PIM benchmarks for the UPMEM PIM architecture, or methodologies such as the move that are useful to identify data movement bottlenecks. And also the move comes with a simulator that can be used to evaluate PIM systems. So these are some of the things that still need to be done in order to adopt processing in memory in real systems. And hopefully, well, we will keep doing research, and many other people will keep doing research as well on how to enable PIM in the real world. And now, let me go to the last part of my talk, is this SimplePIM framework that we recently presented. Actually, last week, we presented it at PACT 2023. This work is called SimplePIM, is a software framework for productive and efficient processing in memory. Is the first high-level framework for programming real PIM systems. We know already that processing in memory promises to alleviate the data movement bottleneck, and the reason why we are here is because real PIM hardware is now available, for example, the UPMEM PIM architecture. However, programming real PIM hardware is challenging. For example, we need to distribute data across PIM memory banks. We need to manage transfers between the host cores and the PIM cores, and between the PIM cores. Remember that, for example, in UPMEM, this communication between PIM cores needs to happen through the host CPU, so that makes the overall execution, the overall problem more complex. We need to launch PIM kernels on the PIM cores. We need to handle how many PIM threads we are using running on the PIM cores, etc. So SimplePIM, is our proposal, is a high-level programming framework for real PIM hardware. SimplePIM uses iterators such as map, reduce, and zip, and collective communication primitives such as broadcast, scatter, or gather. The implementation on the UPMEM PIM architecture with 6 different workloads: reduction, vector addition, histogram, linear regression, logistic regression, and k-means. And these implementations resulted in 4.4 times fewer lines of code compared to hand-optimized code, and between 15% and 43% faster execution than hand-optimized code for 3 of the workloads, and comparable performance for the other 3. SimplePIM is publicly available in the repository. So this is an outline of this presentation: processing in memory and PIM programming. I'm going to give you some examples of why PIM programming is kind of difficult. Then I will talk about SimplePIM, a high-level programming framework for processing in memory. And finally, we will see the evaluation. So this is the state-of-the-art PIM system. You're already familiar with this. In this work, we are using the UPMEM PIM architecture. As you know, we will talk about PIM cores, which are the DPUs. Each DPU is a fine-grained multi-thread, can run up to 24 PIM threads, and they support addition and subtraction of integers natively, but multiplication and division as well as floating point operations are emulated. Remember as well that these PIM cores have their own DRAM bank of 64 megabytes and their own scratchpad of 64 kilobytes. If we take a look at how to program this UPMEM PIM system with the UPMEM SDK, for example, here in this slide, we have a hand-optimized histogram calculation. We will need to perform multiple actions that are, well, at least cumbersome and tedious. For example, we need to reset the heap, we need to initialize variables and histogram, we have to allocate buffers in scratchpad memory, we need to distribute the computation over the threads, in this case with this for loop that we see here. We need to perform boundary checking, load data from the DRAM to the scratchpad, to the WRAM, and then we have to perform the calculations using the data in WRAM at some point, because this is a fine-grained multi-thread execution, in particular in this implementation of histogram calculation. Each thread has its own local histogram, but at some point we need to synchronize and merge those histograms into a single histogram per DPU. And finally, we will have to write results, the histogram, the final histogram, from the scratchpad to the DRAM. And this might require a few more instructions. And then we'll have to read the histogram from the DRAM banks, from the PIM DRAM banks to the standard main memory of the CPU. So PIM programming is challenging for different things that we have to do, like managing data movement between host DRAM and PIM DRAM. And in the UPMEM PIM architecture, we have parallel, serial, broadcast transfers, also scatter-gather transfers that are new in the more recent version of the SDK. Manage data movement between PIM DRAM bank and scratchpad, and this has some requirements. For example, data transfers need to be 8-byte aligned and have a maximum of 2048 bytes. It's a multi-thread programming model, single program, multiple data programming model, which is not extremely complex, but is also not straightforward. And threads may synchronize. For example, in UPMEM PIM, we have barriers, handshakes, mutesigs, and semaphores. So our goal in this work is to lower the learning curve for PIM programming by designing a high-level programming framework that abstracts these hardware-specific complexities and provides a clean yet powerful interface for ease of use and high program performance. This is called SimplePIM, a high-level programming framework for processing in memory, which is based on standard abstractions to build and deploy applications on PIM systems. It has a management interface for the metadata of PIM resident arrays. It has a communication interface with abstractions for host to PIM and PIM to PIM communication. It has a processing interface with iterators such as map, reduce, and zip to implement workloads. And we are going to see each of these in more detail. First of all, the management interface. As I said, it's metadata for PIM resident arrays. It's based on two data structures, one to describe each PIM resident array and another one for managing the PIM resident arrays. And we can access these data structures with the corresponding APIs, like lookup to retrieve all relevant information of an array, register to register the metadata of an array, and free to remove the metadata of an array. In the communication interface, we have abstractions for host to PIM communication. For example, SimplePIM broadcast that transfers a host array to all PIM cores in the system. This is how the API looks. There is an identifier of the arrays in the PIM memory. There is a pointer to the array that we are going to, or the buffer that we are going to broadcast in the main memory, and then we have the length, and we have the data type size. This is how the SimplePIM broadcast looks. If we have this array in host DRAM, we are copying the entire array or the entire buffer to the PIM DRAM bank of each PIM core. Then we also have, for host to PIM or PIM to host communication, we have scatter and gather. Scatter distributes an array to the PIM DRAM banks, while gather collects portions of an array to the from the PIM DRAM banks. This is the API for scatter. This one is for gather, and this is the operation that they perform. If we have this array in host DRAM, when we scatter, what we are doing is partitioning the array and distribute it to the PIM DRAM banks. And when we are doing gather, we do it exactly the other way around. We are collecting these pieces of the red array and put them all together in the host DRAM. We also have PIM to PIM communication abstractions, for example, all reduce and SimplePIM all reduce that is used for algorithm synchronization. The programmer specifies an accumulative function, and this is the computation that all reduce, or the operation that all reduce performs. In the figure, you see how the PIM DRAM banks look before the PIM to PIM communication and after the PIM to PIM communication. In this example, the accumulative function is sum. So what we are doing is taking these arrays in the different PIM DRAM banks and performing the addition or the sum of all the elements, so that after the PIM to PIM communication, all PIM DRAM banks have the result of the accumulative function. Another PIM to PIM communication primitive is called all gather. In this case, we combine array pieces and distribute the complete array to all PIM cores. So before the PIM to PIM communication, each PIM DRAM bank has certain values, sort of a sub buffer after, or sub array after performing the all gather communication. All PIM banks have the entire, the complete array. And then we're going to take a look at the processing interface. In the processing interface, we have iterators, map, reduce, and zip to implement workloads. In array map, what we are doing is applying a function called mapfunc to every element of the data array. So that's basically what we have. We have a source array with its own ID. We have a destination array or output array with its own ID. And we are applying this map function element-wise. We also have reduction. In reduction, we need to use two functions. The first one is called map2valfunc, transforms an input element to an output value and an output index. And the accfunc is a function that accumulates the output values onto the output array. So the basic idea is that we have this source array. For each element of the source array, the map2val function gives us one index and gives us one value. So depending on the index, we will accumulate the corresponding value to the corresponding element of the output. For example, here the index is 1, so we accumulate this value onto the element 1 of the destination array. And the next iterator is array zip. In this case, we take two input arrays and combine their elements into an output array. So yeah, basically that's the operation that is being performed. In this case, we have two input arrays, SRC1 and SRC2, and we will have one destination array with these tuples of elements coming from the source arrays. SimplePIM has and the current implementation of SimplePIM is for the UPMEM PIM architecture. So there are some specific optimizations that we need to apply in order to have an efficient implementation of SimplePIM for the UPMEM PIM architecture. The communication interface, for an example, and in SimplePIM automatically handles the alignment requirements and padding when it's needed, or the processing interface, depending on what's the iterator, for example, for map, invokes the PIM cores and PIM threads and handles the PIM DRAM to scratch pad transfers, the array reduction. SimplePIM offers two different implementations. One is called shared accumulator reduction, and the other one is thread private accumulator reduction. In the shared accumulator reduction, we have a single output array, destination array for all threads running on the same core, while in the thread private accumulator reduction, we have one of these destination arrays per thread, and we will merge them at some point. This is the case of the histogram calculation example that we covered in the beginning. And we are going to compare these two implementations of array reduction at the end of this presentation. And for array zip, we follow a lazy approach to minimize data copying. There are also some general code optimizations, such as strand reduction, loop unrolling, avoiding boundary checks, function inlining, or adjustment of data transfer sizes that SimplePIM applies automatically. And indeed, that's the reason why SimplePIM outperforms some of the hand-optimized codes, because these hand-optimized codes may not apply these general optimizations in all cases. But you can find more details about these optimizations in the paper. Now let's go with the evaluation. Okay, so we have evaluated an UPMEM PIM system with more than 2,400 PIM cores and 6 real-world benchmarks: vector addition, reduction, histogram calculation, k-means, linear regression, and logistic regression. And we compare SimplePIM codes to hand-optimized codes in terms of programming productivity and performance. Remember the code of the hand-optimized histogram that we saw earlier. It's relatively long, relatively complex, while SimplePIM just requires, first of all, define init function that is simply initializing the histogram bins by making all them equal 0, then defining the accumulation function, in this case using addition, and then the map to bold function. Remember that we need these to calculate the output index and the output value to accumulate. And then from the host side is as simple as, first of all, creating a handle, and then performing the scatter operation to transfer. In this case, is a histogram calculation for an image, transferring the different parts of the image to the different PIM cores, and finally run the histogram to produce, so run the calculation, the array reduction to calculate the histogram. In terms of productivity, as we see, it significantly requires significantly lower number of lines of code. The SimplePIM implementation, and here in this table you can see the lines of code reduction, which is the way that we use to evaluate the productivity improvement for SimplePIM, and hand-optimized codes with the corresponding reductions in lines of code that are between 2.98 times and 5.93 times fewer lines of code for SimplePIM with respect to the hand-optimized code, with an average of 4.4 times. So significant reduction in lines of code. Then we perform weak scaling analysis and strong scaling analysis. As we see, the execution time for weak scaling for different number of PIM cores is quite flat, so there is good scaling in all cases. But more interestingly, SimplePIM achieves comparable performance for reduction, histogram, and linear regression, but is able to outperform the hand-optimized implementations for vector addition, logistic regression, and k-means, because SimplePIM applies general optimizations by default that were not applied in the specific hand-optimized implementations that we used for comparison. For strong scaling analysis, one thing we observe is that SimplePIM scales better than hand-optimized implementations for reduction, histogram, and linear regression. For example, here, if we compare the bars, the solid bars or white bars correspond to SimplePIM, these pattern bars correspond to the hand-optimized implementations. And one thing we can see is that the speed up of the execution on the highest number of PIM cores is higher than that of for SimplePIM than that of the hand-optimized implementations, and that's why we can say that SimplePIM codes scale better. SimplePIM also outperforms hand-optimized implementations for vector addition, logistic regression, and k-means, same as we observe in the weak scaling analysis. We also evaluated the two variants of array reduction in the context of the histogram calculation, that are the shared accumulator version and the thread private version. In this plot, as you can see, we have the execution time on the left y-axis, and we have the number of threads on the right y-axis, the number of PIM threads that we use per PIM core, and this is for different histogram sizes, histogram size in number of bins, from 256 to 4098. And there are some interesting observations here. The first one is that the thread private version is up to 70% faster than the shared accumulator version for histograms of 256 to 1024 bins. And the other observation is that the number of active PIM threads of the thread private version, this blue line, reduces after 1024 bins due to the scratchpad size. Remember that in the thread private version, each thread has its own histogram, its own local histogram or subhistogram. And the larger the histogram is, the more the more scratchpad memory, more WRAM we need per thread. So at some point, those histograms might be so large that we cannot have the desired number of PIM threads running on the PIM cores. By default, in our experiments, we have used 12 PIM threads because that guarantees that we are filling the entire pipeline. But after 1024, we have to go to lower numbers of threads for the thread private version if we want to be able to run it. And this is what makes that the overall execution time increases for the versions that use the thread private implementation. Okay, so for a little bit of discussion and summary, SimplePIM is devised for PIM architectures with a host processor with access to standard main memory and PIM-enabled memory. The PIM processing elements communicate via the host processor, and the number of PIM processing elements scales with the memory capacity. SimplePIM emulates the communication between PIM cores via the host processor, and in that sense, it makes programmers' life much easier. And in the future, we could incorporate other parallel patterns to SimplePIM. For example, prefix sum and filter can be easily added. For stencil or convolution, we would require finer grain scatter gather for the hollow cells, and random access patterns in irregular applications would be much harder to support, but hopefully there will be other ways of, let's say, generating high-level programming frameworks that can hopefully deal better with irregular applications. You can find more in the archive version and also in the code that is publicly available in our repository. And just to conclude, again, the executive summary, we have presented SimplePIM, which is the first high-level programming framework for real PIM hardware using iterators such as map, reduce, and zip, and collective communication primitives such as broadcast, scatter, and gather, is able to perform comparably to hand-optimized code in terms of performance, or even faster, because SimplePIM applies by default some interesting general code optimizations, and all of that with significantly fewer lines of code. So this is all from my side about this talk on SimplePIM. I don't see any questions in the YouTube chat or in Zoom, but please let me know if you have any questions. Feel free to also reach out to me offline if you want to ask anything about this SimplePIM work or any other work that we have presented in this PIM tutorial. Now I'm going to hand over to Ataberk Olgun for the last presentation, the last talk of this PIM tutorial. Hello, Ataberk. Are you ready?
Hi, can you hear me, Juan?
Yes, I can hear you.
Just a second. I'm turning on my camera. Okay.
I can see you. I can see you now.
Yeah.
Feel free to share your screen, and thank you very much for joining the tutorial, even though it's so late here in Zurich. I just want to very briefly introduce Ataberk. He's a PhD student of the Safari Research Group. He's doing great research on DRAM and Rowhammer as well. And last year, he implemented this PiDRAM framework for evaluation of processing in DRAM techniques that I think is a very nice complement to what we have covered so far, because it's probably the closest thing that you can find to a real processing using DRAM system, or a real end-to-end processing using DRAM system. So now, Ataberk, if you're ready, please go ahead. The stage is yours.
Yeah, thanks, Juan, for the kind introductions. I'll just get started with an executive summary like usual. So commodity DRAM-based PIM techniques improve the performance and energy efficiency of computing systems without incurring any DRAM hardware cost. However, there are challenges in integrating these techniques into real systems, and these challenges are not yet solved. And we cannot use general purpose computing systems, special purpose testing platforms, or system simulators to efficiently study these system integration challenges. I'm so sorry, just getting rid of some noise. Our goal is to design and implement a flexible framework that can be used to solve these system integration challenges and analyze the trade-offs of end-to-end implementations of commodity DRAM-based PIM techniques. And to that end, we develop PiDRAM, an FPGA-based framework that will enable system integration studies and end-to-end evaluations of PIM techniques using real unmodified DRAM chips. And we evaluate PiDRAM using two PIM techniques that can be performed in real DRAM chips. For our first case study, we show that in DRAM, data copy operations provide almost 120 times speed up over CPU copy operations, even when we include system support for these new fancy in-DRAM copy operations. And to conduct this case study over PiDRAM's extensible code base, we only add 198 lines of Verilog code and only 500 lines, in the order of 500 lines of C++ code. In our second case study about an in-DRAM true random number generation technique, we show that end-to-end implementations of real DRAM-based true random number generators can provide high throughput true random numbers at very low latencies. And implementing this true random number generator takes us only 190 lines of additional Verilog code and 78 lines of C++ code over PiDRAM's code base. PiDRAM is open source, completely open source, and you can find it at this link on the bottom of the page. This is the outline for PiDRAM. I'll start by quickly introducing commodity DRAM-based PUM techniques after giving you a background on DRAM organization. This is a processor's memory controller. It communicates with a set of DRAM chips within a DRAM module through a memory channel. And each DRAM chip contains multiple DRAM banks that share a common interface. And DRAM banks are organized into subarrays that consist of a set of word line drivers and sense amplifiers. And these are partitioned into DRAM mats, which are collections of DRAM cells that are separated from each other by DRAM word lines. And DRAM cells are laid out onto a two-dimensional array of word lines and bit lines within a DRAM mat. And a row of DRAM cells is referred to as a DRAM row. And finally, this is a simplified diagram of a DRAM cell. Now we will look at how DRAM operates at the scope of a single subarray. And because memory controllers typically access DRAM cells in the granularity of a cache line, or 512 bits typically, we combine consecutive cells to form cache lines in this diagram. And on the bottom, we have a timeline of DRAM commands. To access a cell in one of the rows, we first need to send an activate command, which will copy the cache lines in this row to the sense amplifiers. Once the data is in the sense amplifiers, we can send read commands to read data at the granularity of a cache line from the sense amplifier array. And to access another row, we must first precharge the DRAM bank, which will close the open DRAM row and set the bit line voltage to half VDD so that we can initiate the next activate operation. And at the precharge stage, we can now activate the second row before we read data from it, like we did for the first row. Now, to ensure correct operation, we must obey certain timing parameters that define intervals between subsequent or consecutive DRAM commands. And three important timing parameters for our work is TRAS, TRP, and TRCD. That's the activation latency. TRAS is the time we need to spend between consecutive activate and precharge commands so that the charge can be restored in the cell that we just opened. And TRAS dictates the amount of time that we need to wait between consecutive activate and precharge commands. TRP, or precharge latency, is the time it takes for a bit line to become precharged to half VDD so that a new activate command can open a new row. And successive precharge and activate commands on the DRAM command bus must be separated by at least a precharge latency or a TRP amount of time. The last timing parameter that's relevant to us is TRCD, or access latency. This is the time it takes a sense amplifier to correctly amplify the bit line voltage to an IO readable value. That's to say a value that makes sense for us to read. And successive activate and read commands must be separated by a TRCD amount of time. Now, commodity DRAM-based PIM techniques use operational principles of commodity DRAM chips to move data and perform computation inside the DRAM chip. Two examples of such techniques that are relevant to our work are in-DRAM data copy and in-DRAM true random number generation. But as you can see on this slide, there are more techniques. We will focus on these two, and I'll try to give the key ideas of these words to you. So I'll first start with the key idea of row copy, in-DRAM row copy operations based on row clone. This diagram shows a simplified view of the DRAM subarray that I showed in the previous slides. We see a set of DRAM rows and an array of sense amplifiers. And our goal is to copy the orange source row to the gray destination row. We can do this in two steps. First, we copy the source row to the row buffer, and then we move the data from the sense amplifiers to the destination. So current DRAM chips, real DRAM chips, already support the first step of this operation. In fact, we saw it in the background slides. It's an activate operation. We can use activate commands to copy data from a source row to the sense amplifiers. Now, we don't have DRAM chips that quite support the second operation. So I will describe how we can move data back from the sense amplifiers to the destination row without relying on standard or supported DRAM commands. And the key idea in our row clone operation is to perform in-DRAM copy operations by using carefully crafted DRAM command sequences. We will use this activate, precharge, and activate command sequence with greatly reduced timing parameters. That's to say, we will violate the time parameters that are set by the standard or the manufacturers. And this is also demonstrated by a prior work, Compute DRAM, that was published in Micro 2019 that demonstrated in-DRAM copy operations in real DDR3 chips. So I will try to show you what happens when we issue this this command sequence with standard timing parameters. We will send an activate command to the source row S, then a precharge command, then an activate command to destination row D. This will tell the DRAM chip to perform these three operations in sequence correctly. Now, if we violate DRAM timing parameters, or we bring these commands together in the timeline, this will essentially cause the DRAM chip to ignore the precharge command. We will activate the source row. We will move its data to the sense amplifiers, but without pre-charging the bit lines back to half VDD values. While the bit lines still retain the data of the source row, we will enable the destination row. And this will allow us to copy data from the sense amplifiers to the destination row. Now I'll give you the key idea of derange. This is a diagram. This will be a diagram that shows you a bunch of DRAM cells in a subarray. This, we color the cells here, and we color and size the cells according to their failure probabilities when they're accessed with a reduced access latency. That is the TRCD parameter. This means the red cells, the smaller cells, fail with a higher probability when we access them with a reduced latency, and the green cells fail with a very small probability when we access them with reduced latency. Now, the derange's goal is to find, or its key idea is to continuously sample these yellow cells that fail with 50% chance. That's to say they fail randomly. They will produce either a logical 1 value or a logical 0 value when we access them with a reduced access latency. And this will allow us to generate true random numbers quite fast in DRAM chips. Now, commodity DRAM chips can already perform derange because we don't need a specialized command for this or a fancy command sequence. We will do this by just reducing the TRCD timing parameter. So we've seen some applications like row clone and derange at very low level that are at the bottom of this computing stack. And here I'm showing an example again. As an application, we want to enable bulk data initialization at the very top level. And at the bottom level, we have the in-DRAM data copy support to back this operation up. Now, how do we bridge the gap between the application and the device level or the electrons that we need to move around to perform this operation? We likely need support for custom timing parameters, support for issuing custom timing parameters to our DRAM chips. We need some sort of control logic to execute PIM operations. And then at the software level, we need some software interface to convey to hardware that we want to perform some PIM operations. And then we need some supervisor software for very basic system support, such as data mapping, specialized for row clone operations that I will describe later on my slides. PiDRAM's goal is to bridge this system gap with customizable hardware and software components. And its goal in doing so is to allow users to rapidly implement new PIM techniques and then solve the system integration challenges that are associated with these PIM techniques and analyze their end-to-end implementations. PiDRAM's goal is to provide this flexible framework using 4 key components. At the hardware level, we have a component to control PIM operations and a memory controller that supports custom timing parameters. And the software side, we have an interface for applications to use in form of a library, and then a custom supervisor software that will provide the basic system support. Now, we attach these key components to a real RISC-V-based computing system to develop PiDRAM's system design. We implement the PIM operations controller and the PiDRAM memory controller as hardware modules. The custom supervisor software runs on these hardware modules, and the extensible software library is used by the supervisor software and runs on the hardware system. Now, I will describe each component using this diagram, starting with the PIM operations controller. This component decodes and executes PiDRAM instructions to perform PIM operations. It's connected to the hardware system as a memory mapped module, meaning that it receives the PiDRAM instructions over the memory bus from the RISC-V core, and the 3 registers it implements that I depict here as instruction flag and data registers, they're accessible over the memory bus. And this makes it easy to port PIM operation controller to another system that might have a different CPU ISA. And the PIM operations controller communicates with the PiDRAM memory controller over a very simple interface where it sends a request to the memory controller for a PIM operation, and then waits until this operation is complete, and then reads the results, if there's any, back from the memory controller to complete the execution of the PIM operation. The PiDRAM memory controller performs processing and memory operations by using timing parameters that are smaller than manufacturer recommended values. And the command scheduler component in this controller supports conventional operations like loads and stores, or reads and writes to DRAM. And we implement one state machine in its command scheduler, to control the execution for every memory operation. This makes PiDRAM memory controller easy to extend to support new PIM operations, as developers of PiDRAM can simply replicate the state machine in its hardware design to implement a new command sequence. And the physical interface simply controls the physical signals on the DDR3 interface. It receives DRAM commands from the command scheduler, and it drives the interface signals using these commands. So PiDRAM users don't have to deal with the low-level interface details and how to bring up the DDR3 module, how to calibrate it, how to initialize it, and so on. On the software side, the PIM Operations library encapsulates customizable functions that interface with the PIM Operations controller, and it's essentially the software interface to perform PIM operations. Typically, it will execute a bunch of load and store instructions in the RISC-V CPU core to communicate with the PIM operations controller. And I'll later describe the communication protocol that PIMolib uses while communicating with the controller. Finally, the last component, the custom supervisor software, exposes PIM operations to the user via system calls, and we implemented necessary operating system primitives to develop end-to-end PIM techniques in the custom supervisor software, such as memory management and allocation for row clone operations. I'll now describe an execution flow for a PIM operation in the PiDRAM framework. Starting, as an example, we will look at what happens when the user calls the copy function to perform an in-DRAM copy operation. And first, the user makes a system call to the copy function to copy n bytes from array A to array B. The custom supervisor software will find the physical addresses corresponding to virtual address arrays, virtual addresses that point to A and B. And then it will call the copy PIMolib function with the semantics that I show here. It takes two arguments. The S is the source DRAM row, and D is the address of the destination DRAM row. The copy function in the PIMolib library will execute two store instructions in the CPU. The first store instruction will update the instruction register with a PiDRAM instruction that instructs the memory controller to perform an in-DRAM copy operation from row S to row D. And the second store will set the start flag in the flag register to initiate the PIM operation. When the start flag is set, the PIM operations controller will instruct the memory controller to start performing the in-DRAM copy operation. And when the memory controller acknowledges this request, it will set the ACK flag in the flag register. This will indicate that the PiDRAM memory controller has started executing the last valid PIM operation. And to finish executing this PIM operation, the PiDRAM memory controller will issue DRAM commands, activate, precharge, activate commands with violated DRAM timing parameters to the DDR3 module. And when the memory controller issues the last DRAM command, it will set the finished flag. And this will indicate that the memory controller is now done with executing the last valid PIM operation. Meanwhile, the PIMolib copy function periodically checks either the acknowledge or the finished flags based on a user-specified argument, and it will block until either is set until the end of the PIM operation. And in other words, it will return when any of the flags are set. Now, in this example, we did not make use of this data register. This is not useful to us because the results of a copy operation resides in main memory. However, we will use this in our DRAM to random number generation implementation, and I will talk about that later. Yes. To summarize these, we implemented 4 key components that you see here, numbered from 1 to 4, and these components together orchestrate PIM operations execution in PiDRAM's system design. Now we implement the system. We develop a prototype, full system prototype on the Xilinx ZC706 FPGA board. The RISC-V system implemented alongside PiDRAM contains an in-order pipeline, simple RISC-V Rocket CPU core with some level 1 data and instruction caches and a TLB. And we enable the processing in memory operations in this DRAM module that I show you here. Now I'll continue with the case studies that we performed on our full system prototype, but I'll just take a 10-second break in case there are any questions.
I don't see any questions, Odaber. I think you can continue.
Okay, thanks. Yes, so I'll continue with our case study. This is just to remind you how we perform row clone operations. We send activate, precharge, and activate command sequences with greatly reduced timing parameters. We extend PiDRAM memory controller with a new state machine that controls the activate, precharge, activate command sequence, and expose this operation to PIMolib by implementing the copy PiDRAM instruction in the PIM operations controller. And all of these modifications takes us 198 lines of Verilog code over PiDRAM's flexible code base. We then study the challenges in integrating row clone end-to-end in a real system. The first challenge we identify is proper memory allocation for row clone operations. Because row clone operations can only copy data inside a subarray, the data structures must be allocated properly to benefit from fast bulk data copy operations in DRAM. The second challenge is maintaining memory coherency. Because computation is done in memory, or we move data in memory without taking it through the cache in the system, any cache copies of the data we operate on, that is to say the source and the destination rows, must be evicted and the data must be up to date in DRAM prior to us copying data. To address the second challenge, we implement the CL flush instruction, cache line flush instruction in the RISC-V CPU. This instruction will take a memory address and it will evict the cache lines that are cached in CPU caches to main memory. We use this to evict all the cache lines of the source and the destination rows before we perform row clone operations in the DRAM chip. I'll now explain the first challenge in more detail. We identify 3 memory allocation requirements for operands of row clone operations. This is a simplified diagram of a DRAM chip with 2 banks, bank X and Y, distributed horizontally in this figure, and 2 subarrays depicted as subarray W and subarray Z. Now, the first requirement is the granularity requirement. This says that the operands must occupy their DRAM rows completely. Otherwise, row clone operations may overwrite the data that we did not intend to overwrite in the destination row. The second requirement is called alignment. Operands must be placed at the same offsets in the respective DRAM rows. This relates to how DRAM cells share a common bit line. And we can only copy data to another operand if their bits share the same set of sense amplifiers at the same offsets. The third requirement is called mapping. Because row clone operations can only be performed inside a DRAM subarray, the operands must be placed or allocated in the same DRAM subarray in the same DRAM bank. In contrast to the previous 3 operand allocations, the fourth one here shows an allocation that satisfies the requirements, and it can be used in row clone operations. Now we implement a new memory allocation function in the custom supervisor software to overcome the challenges, the memory allocation challenges of row clone operations. The goal of this function is to allocate virtual memory pages that are mapped to the same DRAM subarray, and they're also aligned with each other. This is the semantics of our function. It's called alloc-align. It takes 2 arguments. The size argument is the number of bytes we need allocated, and ID is used by the programmer to indicate which data structures which data structures do we intend to copy between each other. So to give an example, if we have 2 alloc-align calls with ID 0, that means we have created 2 different memory allocations for two different data structures, and we can freely copy one to another using row clone operations. Now I'll give the key ideas of how this works at a very high level. This all depends on the subarray mapping table data structure that we implement in the supervisor software. Is an example allocaline call that would like to allocate 4 kilobytes in subarray 0 will get the physical address that points to a DRAM row in subarray 0 by consulting the subarray mapping table. And then it will update the page table to map the virtual address that it allocated to subarray 0. Now, for more details, I will refer you to our paper that you can find at this link. And I will link this at the end of the slides. So there will be a link over there as well. I'll move on to how we evaluate PiDRAM, our first case study. We evaluate the performance of row clone operations with system support in our PiDRAM prototype in the real system. This table shows the full system configuration of our prototype. And we run two sets of micro benchmarks called CPU copy and row clone copy. To perform bulk data copy, in the CPU copy micro benchmark, we execute load and store instructions in the RISC-V core. And in the row clone copy micro benchmark, we execute in-DRAM copy instructions using the PiDRAM memory controller. We do these operations with and without CL flush. That's to say, we assume that the data in DRAM is completely up to date and there are no cached copies. And we make other assumptions on how large of a fraction of the cache lines in a DRAM row is cached in the system caches. We estimate the performance benefits provided by row clone copy and initialization operations using two copy and initialization heavy workloads, fork, bench, and compile. And finally, we run the libquantum workload from spec 2006, where we replaced zero initialization calls or calloc calls in the program with in-DRAM initialization calls. The final remark here is that we have an in-DRAM copy granularity of 8 kilobytes because in our prototype, a DRAM row is 8 kilobyte large. This means that the minimum amount of data we can copy using row clone operations is 8 kilobytes. This plot shows the throughput improvement provided by in-DRAM copy operations for bulk data initialization and copy over CPU-based initialization and copy operations. We don't execute any CL flush instructions here, and we assume that the data is up to date in the DRAM chip. The x-axis shows the size of the arrays we copy or initialize. The dark gray bar shows the improvement sorry, I'm gonna bring my pointer up. The dark gray bar shows the improvement we have for initialized operations, and the lighter gray bar shows the improvement for copy operations. We observe that in DRAM copy and initialization can improve throughput by 119 times and 89 times respectively, even when we include the overheads of system support required for row clone operations. Now, I didn't go into details of the system support in my slides, but it involves page table lookups, multiple page table lookups to find the physical addresses that point to the DRAM rows, the source and destination DRAM rows. Now I will discuss the overheads of CL flush operations and describe them. This plot shows the throughput improvement provided by copy and initialization, again, the same operations over CPU-based copy and initialization. When we copy 8 megabytes of data, and the x-axis here indicates the fraction of cache blocks that are dirty in the caches. We assume that all 8 megabytes of data is cached. And if, for example, we're looking at the first 2 bars, all 8 megabytes of data is cached in the CPU caches, but it's not dirty. So it doesn't need to be written back, but it still needs to be evicted. In the rightmost bars, we assume all data is cached and all cache lines are dirty, meaning that a write back to DRAM must be performed. Now we observe here that CL flush operations can dramatically reduce the potential improvement of copy and initialization operations that can be performed in DRAM chips. Now I'll summarize our results for other workloads in this slide. This plot shows the speedup provided by row clone operations for the fork bench workload, when the row clone copy operations are used instead of CPU-based copy operations. And the x-axis here shows different configurations of the fork bench workload, where the number after the hyphen indicates the amount of 4 kilobyte pages copied after each call to fork. We observed that as the fraction of time spent on copy operations increase, that's the blue line, and the secondary y-axis, the speedup provided by row clone operations also increase. And we see improvements up to 42.9% for the fork 2K configuration. We observed 9% reduction in execution time for the initialization heavy compile workload, which is expected as compile spends an estimated 17% of its time on initialization. Finally, we make a similar observation for the lib quantum benchmark or workload. We observe 1.3% end-to-end execution time reduction here. And similarly, this is because in our experiments, the quantum spends only an estimated 2.3% of its time on bulk data initialization. Now I'll describe our second case study. And this is to remind you the key idea of DRange, or the in-DRAM true random number generation technique that we're interested in. The key idea is to reduce DRAM access latency below manufacturer recommended values and exploit the resulting error patterns as true random numbers. And we're trying to find cells that fail with 50% chance when we access them with a reduced latency. To implement this technique, we first identify a DRAM cache block that contains 4 cells with failure probability of 50%. Then we use these cells to produce true random numbers, as accessing them with a reduced access latency will output random values. We periodically generate true random numbers by accessing these 4 cells. And to store the periodically generated random numbers, we implement a 1 kilobyte large random number buffer in the PiDRAM, in the PIM operations controller. And the programmer reads a random number from the data register using the rand-DRAM function call that we implement in the PIMolib. And modifying PiDRAM to implement DRange took us only 190 lines of Verilog and 74 lines of C++ code. We evaluate our implementation of DRange using a simple micro benchmark that continuously reads true random numbers from the DRAM chip. And this plot shows the true random number generation throughput we observe. On the x-axis, we show the TRNG period, which we can dynamically configure for PiDRAM's DRange implementation. And we observe that our DRange implementation can generate true random numbers at 8.3 megabits per second throughput. I'll conclude with a summary. So commodity DRAM-based PIM techniques can improve performance and energy efficiency of our computing system with no additional DRAM hardware cost. But there are challenges of integrating these techniques into PIM systems, and these are not yet resolved. And using infrastructure available to us, we cannot properly study the system integration challenges and analyze trade-offs of their end-to-end implementations. For that purpose, we develop PiDRAM, which can be used to perform these studies and analyze the trade-offs. We evaluated using 2 case studies. The first one on row clone, we show 119 times speed up for copy operations compared to CPU copy operations. And row clone can be implemented with minimal hardware changes to our extensible code base. And in our second case study, we implement DRange, a true random number generator, and we show that it can provide high throughput and low latency to random number generation. PiDRAM is open source at this link, and an extended version of our journal publications available on arXiv. Finally, there is a longer version of this talk, and mixed with a tutorial that's available on YouTube that I would like to refer you if you're interested in using PiDRAM. Thank you very much for listening. This is it about PiDRAM, and if you have any questions, I'll be happy to take them.
I do not see any questions, Adalbert, so I think you can go to the last part of your presentation.
Yeah, sounds good. This is just going to be a very brief introduction to another infrastructure that we developed in our group. This is called DRAM Bender, an extensible and versatile FPGA-based infrastructure to easily test state-of-the-art DRAM chips. And we would like to discuss this in this tutorial, in this workshop or tutorial, because it's been, I guess, very relevant, as you will understand as I present some of the later slides, relevant to commodity DRAM-based PIM operations, discovering them and characterizing them. There are many factors that affect DRAM reliability and latency, such as DRAM timing violations, interference between DRAM cells, manufacturing process variations, temperature and voltage variations, and so on and so forth. And these factors that affect DRAM reliability and latency cannot be properly modeled in simulation or analytically using maths. And then therefore we need to perform experimental studies of real DRAM chips. There are DRAM testing infrastructures that allow experimental studies of real DRAM chips, such as the SoftMC infrastructure or the LiteX Rowhammer tester. These are open source FPGA-based testing infrastructures. They're publicly available. We can start using them today, and they're relatively low cost to their more closed alternatives because they require only an FPGA board and a set of DRAM modules. These are relatively easier to obtain. Now, there are limitations of these existing infrastructure, such as the fact that they impose restrictions on the DDR interface, and this limits the number of or types of experimental studies you can perform using these infrastructures. And they're difficult to set up because they're based on discontinued hardware or software, and they're difficult to use because they require you to develop a new hardware module every time you develop a new experiment. And finally, for SoftMC only, SoftMC has a monolithic hardware design that makes extending it to new standards or to new to new FPGA prototypes difficult. And our goal with DRAM Bender is to overcome the limitations of these prior infrastructures. It needs to be, our design goals for DRAM Bender is flexibility. DRAM Bender has the ability to test any DRAM operation with any combination of timing parameters between each command, each DRAM command. It's very easy to use. It provides a simple programming interface so the developers or users can spend minimal amount of time on programming the infrastructure. And it's accessible to a wide range of users because the users don't need to know or they don't need to be experienced in hardware development. The final goal is extensibility, and we developed DRAM Bender from the ground up with modularity as a goal so that it's easy to extend to new DRAM standards or to new FPGA boards or prototypes. This is an overview of our infrastructure. It's the first publicly available FPGA-based DDR4, 3, and a closed version of it allows testing HBM2 characterization infrastructure. And it's easily programmable using the DRAM Bender C++ API. This is one of our 5 FPGA-based prototypes, and these prototypes are supported by our open source repository out of the box. DRAM Bender is flexible. We evaluate 3 case studies in the paper to show how it's a versatile infrastructure that allows us to perform different types of experiments. The first case study is about Rowhammer, where we look at the effects of interleaving patterns of activations to aggressor rows on Rowhammer bit flip rate. In the second case study, we'll look at the new 512-bit random data pattern support provided by DRAM Bender, and how it allows us to uncover more bit flips than 8-bit random patterns that's supported by SoftMC. an earlier version of this infrastructure. And in the third case study, we demonstrate in DRAM bitwise and OR operations in real DDR4 chips. And therefore, we conclude that DRAM Bender is flexible, so it supports many different types of experiments. Now, DRAM Bender is also easy to use. It's easily programmable using the DRAM Bender C++ API. Here, I'm showing you an example from our third case study. This is the 3 lines of code that we need to write to create our DRAM Bender program that will send an activate, pre-charge activate command sequence with different timing values that we sweep in our experiments that are here defined as N and M to uncover new functionality in DRAM chips. This allows us to perform row call operations. And later, I will show you how we use this to find NOT operations in real DRAM chips. We conclude that it's easy to devise new experiments to uncover new insights using DRAM Bender. There are more details in our paper that I will show a link in the end. There are more details on its design, such as its instruction set architecture, its hardware and software modules, how it's designed, its prototypes, and we also have a temperature controller set up, and we describe how to set it up also. More details on its application programming interface, detailed results for the 3 case studies that we perform, and we describe some future work and improvements to our infrastructure. You can find the QR code to our paper here, and I'll show this in the end of the slides also. Now, I'll show you this set of works that DRAM Bender enabled, and I'll kind of highlight the first one, row press. Here in row press, we show that keeping a DRAM row open for a very long time will cause bit flips in adjacent rows. And these bit flips don't require many row activations like row hammer does. And we have seen extreme cases where only one activation is enough to induce bit flips in neighboring rows. And here are 2 timing diagrams that show the difference between a row hammer aggressor row and a row press aggressor row. As you can see, the row hammer aggressor row is more frequently activated and is kept open for shorter. In contrast, row press keeps a row open for longer, and it issues much fewer activations to induce bit flips. And here are some numbers to quantify that effect. If we open a row for only 36 nanoseconds, we observe that 47,000 activations are needed to induce a bit flip. However, if we keep a row open for 7.8 microseconds, that's almost 200 times longer than 36 nanoseconds. Only 5,000 activations are enough to induce bit flips. And we have more results in the paper, and our work is fully open source and artifact evaluated. And you can find more resources on row press in this slide. And DRAM Bender and its previous version, SoftMC, collectively enabled many more works from other research groups as well. And here's an updated list of them. Finally, a recent work of ours is going to appear in HPCA next year. It's called Functionally Complete Boolean Logic in DRAM, and an experimental characterization and analysis of real DRAM chips. And this was also this shows that we can perform NOT operations in real DRAM chips. And this was possible because an infrastructure like DRAM Bender existed. So in summary, DRAM Bender is the first publicly available DRAM characterization infrastructure to test DDR4 chips. It's flexible and easy to use. And the source code of DRAM Bender is available on GitHub at this link. And you can use the QR code to reach it also. It enables many new studies, ideas, and methodologies in the design of future memory systems. There are more resources on DRAM Bender, and you can find all of them in this slide. And these slides are also uploaded to the tutorial website, so you can look at them over there. Thank you very much for listening to my second part of my presentation, DRAM Bender. And I'm on time, and I can take questions if there are any.
You are perfectly on time after a perfect talk.
Thank you.
Thank you very much, Atterberg. Thank you for staying until so late. I don't see any questions in the chat. I would just like to ask you some question about DRAM Bender naively. The first thing that you presented is PiDRAM, first end-to-end framework for processing using memory techniques. And the idea of working on PiDRAM came after the publication of the Compute DRAM paper. The authors of Compute DRAM had used SoftMC, which is the let's say initial DRAM vendor, the old DRAM vendor. So in terms of system integration for processing using memory, how do you think that DRAM vendor could contribute to make further steps with respect to what SoftMC and PiDRAM represented?
I see. Yeah, that's a good question. Thank you. And thank you for your comments on my talk. And it's my pleasure to be here also. And for the question, I think DRAM vendor plays a different role. I think also SoftMC and PiDRAM play different roles. The timeline was definitely correct. So SoftMC used by Compute DRAM, and then we were inspired to develop PiDRAM. If you look at Compute DRAM, you will see that they characterized many DRAM chips using SoftMC or their modified version of it. But they couldn't evaluate those end-to-end, they couldn't evaluate those PIM operations they uncovered end-to-end in a real system. That means the evaluation lacked basically the full system view that we developed in PiDRAM, where we have a RISC-V core next to a memory controller that supports row clone copy operations, row clone initialization operations. And that's the gap PiDRAM filled. Now, if you want to build on PiDRAM, you can, maybe you want to implement a new PIM operation that you found. Now, finding that you will need to use DRAM vendor or SoftMC or a similar infrastructure, but evaluating it, you're better off using something like PiDRAM, where you can execute real workloads along with PIM operations, I think. And DRAM vendor, I think, is going to play a role based on the trends. We're going to probably uncover more in the real DRAM chip, commodity DRAM-based PIM operations. And if we uncover more of them, that will be likely with the help of DRAM vendor or a similar infrastructure. And if we evaluate them in real systems, that will require something like PiDRAM or some improved version of it. Yeah.
Mm-hmm. I see. But hopefully, I mean, it would be possible to build a PiDRAM that based on DRAM vendor that can even target more types of memories and so on, right? That would be potentially possible and hopefully could enable a lot more research in the future.
Yeah, definitely. I think because I developed kind of both infrastructures or heavily participated in development of both, I can say that PiDRAM reused some stuff from DRAM vendor. Now, before DRAM vendor was published, I couldn't say that. And that reused portion can be again reused to implement PiDRAM in a DDR4 framework or any new standard that DRAM vendor supports. You can code from one repo, add it to another one, and you can support new standards.
Okay, yeah, that sounds very good. Thank you very much, Ataberk. Yeah, I don't want to take more of your evening or night time. Yeah, it was a pleasure to have you here.
Yeah, my pleasure. Thank you a lot. Goodbye.
Yeah, thank you again. So now we are about to conclude this PIM tutorial after a few hours. I think it has been, as usual, a very interesting experience with really nice talks from people from the Safari Research Group and also wonderful invited speakers. Today we had Professor Kim from Yonsei University and Dr. Sebastian from IBM Research Zurich. Just to conclude, I'm going to give you a very brief introduction to the hands-on lab that is optional, is available in the course website. And if you really want to have the experience of working with a real PIM system, is a very good opportunity. So yeah, let me very briefly go over this hands-on lab, programming and understanding a real processing in memory architecture. You can find the handout in the website. In total, there are 7 pages. This is the first one. It explains with a lot of detail how to access the UPMEM PIM server that is available until tomorrow noon Europe time. And it basically explains how you need to configure your computer in order to access the server, and then what are the different tasks that you are invited to try in order to have your own experience programming a real PIM system. First of all, with respect to how to access the UPMEM PIM server, you would need to paste the configuration that is provided in the handout, and here in this slide in your .ssh/config file. And then there is a private key that we provide in the website, and you will need to place it in the corresponding folder. You may need to change permissions, but don't worry, this is explained in the handout. And right after that, go to your terminal and type SSH UPMEM Cloud 5, and you will directly access the server. Keep in mind that the server is open to everyone who wants to access right now. So please, if you want to run your own programs, create your own folder with your name or whatever folder name that you want to choose, and work only on that. Try not to interfere with folders that might have been created by other users. With the handout, we provide as well some template files, because obviously in the amount of time that you have, you could not write the program from a completely blank slate. They can program completely from scratch. So it's mostly like a pretty complete template where you need to fill some gaps, essentially 4 the different tasks. The first of the tasks is to evaluate CPU, DPU, or CPU PIM and PIM CPU or DPU CPU transfers, the different types of transfers that we explained in the second lecture of this tutorial, serial, parallel, and broadcast transfers. These are the corresponding slides that you have already seen, and they can definitely help you to type the exact and correct syntax for these transfers, and then compile and run your program. Second task is implementing your first kernel. It's pretty similar to the vector addition kernel that we briefly explained in the lecture 2, but in this case you need to create the AxPy operation. But again, it's 2 main arrays, Y and X. You need to access them. First of all, copy them from the main memory to the PIM memory, then from the PIM cores, from the DPU cores, copy chunks of these X and Y, move them to the WRAM or the scratchpad, and perform the corresponding computation accessing data from the scratchpad. In task number 3, similar to that, you are going to use a vector addition, and similar to that, so the code is going to be very similar. Importantly, or interestingly, what you're going to do is try different operations and different data types. So we are going to replace the addition with a subtraction, multiplication, or a division, also for the different data types. And the idea here is that you measure the execution time or the execution cycles to see what are large variations in the arithmetic throughput for different operations and data types. If you want to have a reference on the results that you need to obtain, I would recommend you to check the paper that we published in last year in IEEE Access, where we basically did this analysis to figure out what was the arithmetic throughput of addition, subtraction, multiplication, and division for integers and for floating point numbers. And in task number 4, it's a little bit more complex. In this case, you will need to exercise on the synchronization of PIM threads. We didn't have time today to cover that part, but I can refer you to past tutorials and also our past lectures on programming the UPMEM system, where we explain the use of barriers or handshakes. And well, ideally here you are going to create several different implementations and compare them and see what are the trade-offs and evaluate the corresponding implementations of the vector reduction. So this is the last task, and well, this is the last page of the hands-on lab. Sorry, of the handout, because I wanted to show you this appendix that talks about how to install the AppM SDK and invites you to also use the Docker file. The good thing is that installing the AppM SDK or using the Docker file that we provide with the template files, you can simply, well, you can continue working on programming this PIM system even if you don't have access to the real server, because the AppM SDK comes with a simulator where you can simulate up to 24 DPUs. It's not an entire system with more than 2,500 DPUs, but it's a a tool that you can use to continue learning on how to program real PIM systems. And this is all from my side. I don't see any questions in YouTube. I guess there are no questions from the audience in Zoom. I really appreciate everyone watching today's tutorial. It was the first time that we made it fully virtual. I think that the experience is even nicer if we see each other in person in a room at the conference venue, but this time it wasn't possible to do it that way. I think it's still pretty nice that we had this opportunity to have several speakers or great invited speakers that we have today, and keep learning a little bit more about PIM systems and about the state of the art of real PIM systems. Thank you very much, everyone, and I hope to see you again in the next Safari event. Bye-bye.